Good morning, everyone in Turkey, and also good night, Professor Zermanov and the other participants in the world. I would like to invite Professor Efim Zermanov from University of California, San Diego in USA. Professor Zermanov, again, thank you. It's a great pleasure for all of us to have here Professor Efim Zermanov for the valuable talk on groups with torsion. Professor Zermanov, you are welcome to do your presentation, please.
Thank you very much. Thank you for this opportunity to speak here. I would much prefer to do it personally in beautiful Istanbul, but so my talk will, where I have been several times, my talk will consist of two parts. In the first part, I will talk about general properties of torsion groups, and in the second part, I will talk about torsion groups of particular type. So a group is called a torsion group if an arbitrary element has a finite order. So if you take an arbitrary element and take it to the sufficiently big power, you get the identity. Okay. In 1902, William Bernstein formulated maybe the first problem about infinite groups, even two problems. The first one was, suppose that a group has finitely many generators, and suppose that it is torsion. Does it imply that the group is finite? It became known as a general Bernstein problem, because a finite group clearly has finitely many generators, and by Lagrange theorem, an arbitrary element is torsion element, has finite order. So is it enough to make a group finite? And the second problem formulated in the same paper, the group G is still finitely generated, but now we demand that orders of all elements are uniformly bounded from above. So they exist the same n such that for an arbitrary element G, G to the power n is equal to the identity. Does it imply that the group is finite? This problem became known as the Bernstein problem. The smallest number n with this property is called the exponent of the group. Bernstein himself, well, it is obvious. For n equal to 2, it is obvious. The group is abelian, everything is obvious. Bernstein himself did it for exponent 3. It was not difficult. Ivan Sanov did it for exponent 4. It was pretty difficult in 1940. Then Marshall Hall did it for exponent 6, and it was very difficult. Since then, for no other exponent, a positive solution was found. So, for example, for n equal to 5, the question is still open. Bernstein and Isaiah Schur proved that if G is a finitely generated linear group, so it is a group of matrices over some field, then this problem has positive solution. So a finitely generated torsion linear group is finite. This theorem had very far-going generalization by Jacques Tits. Jacques Tits proved that for every finitely generated linear group, either this group has a solvable subgroup of finite index, or it contains the free group of rank 2, well, and therefore cannot be torsion. It became known as Tits alternative. This problem stimulated a lot of research in the 20th century. In 1964, Golod constructed counterexamples to the general Bernstein problem. He constructed finitely generated infinite torsion P groups So for a fixed prime number P, every element had an order which was a power of that number P. His examples were based on some criterion of Golod and Shafarevich. So sometimes these examples are attributed to Golod and Shafarevich. In 1968, Pyotr Novikov and Sergei Adyan constructed counterexamples to the Bernstein problem. They constructed infinite, finitely generated groups of bounded exponent n, where n is odd and huge. And the paper, the proof was on more than 300 pages long, and it contains simultaneous induction on more than 100 parameters. Now, an important definition. We say that a group G is residually finite if there exists a family of homomorphisms on two finite groups, such that the intersection of kernels is trivial. It means that for any two distinct elements, there exists a homomorphism that distinguishes between them. You know, every homomorphism, every projection is like a photo. With every photo, we lose some information. But when a group is residually finite, it means that we took photos from all sides. And altogether, they give a pretty good information about the group G. The kernel of every such homomorphism is a subgroup of finite index. Since the intersection is trivial, we can view these subgroups as basis of neighborhoods of the identity element. So the group G becomes a topological group. Every residually finite group is automatically a topological group. If this topology is complete, so if every Cauchy sequence has a limit, then we say that G is a profinite group. In this case, it can be represented as an inverse limit of finite groups. If a residually finite group is not profinite, so the topology is not complete, we can consider the completion, which will be a profinite group. So every residually finite group is embeddable into its profinite completion. Now let P be a prime number. We can consider homomorphism, we fix that prime number, and consider homomorphisms only into finite P groups, such that the intersection of kernels is trivial. If there exists such a family of homomorphisms, then we say that the group is residually P. Again, we can take these subgroups as basis of neighborhoods of the identity element. G is a topological group. If the topology is complete, then we say that G is a pro-P group or an inverse limit of finite P groups. Every residually P group is embeddable into its pro-P completion. Now, all infinite groups can be subdivided into two classes. There are hopelessly infinite groups, like examples of Novikov and Adyan. And usually these groups appear in geometric group theory. Or there are profinite groups, residually finite groups, let us say. And these residually finite groups, they appear, Golod groups are residually finite, and they appear in number theory and combinatorics. It's like philosophically, it's like two kinds of infinity, hopeless infinity, and infinity, which is a limit of finite. Now, and these two families behave differently. For example, the most clear example of that. In 1930s, a new version of a Bernstein problem was formulated. It became known as the restricted Bernstein problem. it can be formulated in many ways. One of them, it's a very strict Bernstein problem, but for residually finite groups. Initially, it was discussed as a way to prove the Bernstein problem in positive. This program was outlined in the plenary talk of Graham Higman at the International Congress in Edinburgh. But after counterexamples, it became clear that this is not a way to prove the Bernstein problem. This is the positive part of the Bernstein problem. It became so popular that once I have seen a survey on the Bernstein problem properly, and it was called on unrestricted Bernstein problem. Okay, now the first big achievement was reduction theorem of Philip Hall and Graham Higman. They reduced the restricted Bernstein problem only to groups of prime power exponents. But they did the reduction modulo certain assumptions about finite simple groups, certain conjectures. And after the classification, these conjectures became theorems. So they did the reduction. Then Kostrikin proved the restricted Bernstein problem for prime exponent. And finally, 30 years ago, I did it for p power exponent and therefore for all n's. Okay, I talked about infinite groups. Now let us talk about ring theory. In 1941, Alexander Courage decided that the Bernstein problem was such a great problem. It stimulated so much of research. Why don't we formulate something similar for algebras and rings? So let A be an associative algebra over a field F. Again, it is finitely generated. What is the analog of B in torsion? Okay, let us say that it is a nil algebra. So an arbitrary element is nilpotent. In a sufficiently big power, it is equal to 0. Does it imply that the algebra A is finite dimensional and nilpotent? It became known as Courage problem. And it also stimulated a lot of research. The whole structure theory of infinite dimensional algebras wasn't developed as a response to this problem. But in 1964, the same examples of Golat provided counterexamples to this question. In fact, Golat first constructed counterexamples to the Courage problem, and then he used them to construct counterexamples to the general Bernstein problem. Now, if you want a big class where this problem has positive solution, so where should we look? Kaplansky introduced PI algebras. So what is a PI algebra? Let F be a non-zero element of a free associative algebra. So sometimes I could say a polynomial in non-commuting variables. Let A be an associative algebra. If whenever you plug arbitrary elements for this axis and you always get 0, if this is true, then we say that this equality holds identically on A. And A is a PI algebra. So a PI algebra is an algebra with some identical relation. Then there was a long development. Levitsky, Kaplansky, Jacobson, Shershov got various versions of a positive solution of Courage problem in the class of PI algebras. Fine. Now let us talk about Lie algebras. Well, I won't give a definition of Lie algebra. I'm assuming that the audience is familiar at least with the definition of Lie algebra. No, in a Lie algebra, every element to the power 2 is equal to 0. So how can we define an nilpotent element in a Lie algebra? We do it as follows. An element is said to be ad-nilpotent if the adjoint operator, that is the operator of commutation with this element, is a nilpotent operator. And now we can formulate the Chorosh problem. Let L be a finitely generated algebra and an arbitrary element is ad-nilpotent. Does it imply that L is nilpotent and finite dimensional? Well, the answer is no. Again, the same Golod's examples are counterexamples. However, in 1991, I proved that if L is a finitely generated Lie algebra, every element is ad-nilpotent and all these n's are uniformly bounded from above, so they exist the same n for all elements, then yes, the Lie algebra L is nilpotent and finite dimensional. And actually, this theorem implied the positive solution of the restricted Bernstein problem, because when it has been Hall and Higman reduced to p-power groups. Now, if a group is residually p, then we can construct a certain Lie algebra. Lie algebras were introduced by Sophus Lie. They correspond to Lie groups. If a group is residually p, then again you have some kind of Lie correspondence. It's not as good as the initial correspondence of Sophus Lie. In this way, you lose a lot of information. You cannot recover the group G by this Lie algebra. And this Lie algebra is over a finite field. But using this theorem and using this correspondence, the group theory problem was solved. Now, what is a PI algebra? What is the Lie algebra for Lie algebras? Again, we take a non-zero element of the free Lie algebra, and we say that it is identically zero on the Lie algebra L if whichever elements you plug in, you always get zero. This is the recent theorem that was published recently, and this is the most general positive result in the direction of Chorosh problem for Lie algebras with quite a complicated proof. Let L be a finitely generated Lie algebra. Suppose that it is PI, and I'm not asking that an arbitrary element be ad-nilpotent. No, only commutators and generators. And that is enough to say that L is nilpotent. Now let's talk about groups. Let F sub M be, I have some chats. Okay, no. Let F sub M be the free group in M free generators. It is easy to show that for an arbitrary prime number P, it is residually P. Okay. If it is residually P, then we can consider its pro-P completion. And it is called the free pro-P group, because an arbitrary mapping of the free generators, x1, x2, and so on, into an arbitrary pro-P group uniquely extends to a continuous homomorphism from this group to the pro-P group. So it deserves this name. We say that a pro-P group is PI if there exists a non-identical element of the free pro-P group such that whenever you plug arbitrary elements, you get one. If a pro-P group is PI, then the corresponding Lie algebra is also PI. The reverse is not true. And from the previous theorem, it follows that if G is a finitely generated residually P group, which is torsion. It's like in Golod's example. But now we assume that the pro-p completion is pi, then the group is finite. So this is the most general positive part of the Bernstein problem. Okay, now I will talk about a particular class of groups. And this is a joint work with Oksana Bezushchak and Anatoly Petrovchuk, both from Kiev, Ukraine. So all new theorems that I formulate in this section are joint theorems. In case I forgot to say it, I'm saying it. Okay. Let F be an associative commutative ring with an identity element. Let V be an affine algebraic variety over F. So we consider the polynomial algebra, we consider some ideal, and we consider the set of all zeros of that ideal. This factor algebra is called the algebra of polynomial or regular functions on this affine variety. No, in this case, we usually get reduced algebras, the algebras without nilpotent elements, but I consider arbitrary finitely generated algebras. It also makes big sense in algebraic geometry. So the group of automorphisms of this finitely generated commutative algebra is called the group of polynomial automorphisms of the affine variety. And the group of all derivations of this algebra is called the Lie algebra of vector fields on this affine variety. For some reason, if V is an irreducible variety, well, in which case A is a domain, then we can consider the field of fractions and yes. And the group of automorphisms of that field is called the group of birational automorphisms of the affine variety, and the group of derivations of that field is called the Lie algebra of birational vector fields. Of particular interest is the case when the algebra is the polynomial algebra over field of complex numbers. Then the group of birational automorphisms is a famous celebrated Cremona group, and the group of automorphisms is a polynomial Cremona group, and we can consider Cremona Lie algebras and so on. This algebra of polynomial automorphisms, generally speaking, is not linear. It's not difficult to prove. It's not embeddable into any matrices. But it is kind of next to linear groups. There is a class of linear groups, and then there is a class, well, they all can be realized as groups of automorphisms of some finitely generated commutative algebra. So this is a bigger class, and these groups are not linear. And there is an old program that attracted a lot of attention that started, that is certainly older than me. The program to extend theorems for linear groups to groups of polynomial automorphisms. So which properties of linear groups extend to groups of polynomial automorphisms? Well, for example, explicitly, this program was formulated by Jean-Pierre Serre, but it existed before. I will mention some highlights of this program. Well, there is a famous theorem of Jordan about linear groups. It says that all finite subgroups of the general linear groups, all finite groups of matrices have an abelian subgroup, and the index is bounded in terms of the size of matrices. If we want to extend it to this algebra, it would say that finite subgroups of this group have an abelian subgroup, and the index is bounded in terms of this algebra. In this generality, this is an open problem. It is not known. There were important results in this direction due to Popov, Zarhin, Prokhorov, Shramov, Birkar, et al., et al. Yeah. So in full generality, it is not, it is still open. Again, Jean-Pierre Serre classified finite subgroups of the Cremona group by rational automorphisms in two variables. Another problem, well, you know, for linear groups, there is a very important result, Tietz alternative, which is a generalization of Bernstein's theorem on torsion groups. In 2011, Cantat proved Tietz alternative for Cremona group again in two variables. So the first theorem that I will formulate, it's a new theorem, is the extension of the result of Bernstein and Schur on torsion groups. Let A be a finitely generated, associative, commutative F algebra. And unfortunately, I have to make an assumption that it does not have additive torsion. So in some way, we talk only about zero characteristic. Let G be a torsion subgroup of the automorphism group. Then the group G is locally finite. Corollary, the first. If A is the polynomial algebra, so Jordan theorem holds. If we have a locally finite subgroup in a group which has Jordan properties, then it has an abelian subgroup of finite index. And the second corollary, that if A is a finitely generated ring, so it is kind of finite dimensional over integers, then every torsion group is not only locally finite, it is finite. In fact, this assertion follows from the result of Prokhorov, Shramov, and Birkar. But this proof is extremely complicated, and our proof takes 2 pages. Now, some open questions. What about prime characteristic? More generally, I talked about propy groups with identity above. No, in these groups, there are natural propy subgroups, like Silov subgroup. Do they satisfy propy identity? If that is the case, that would do it for prime characteristic. And in any case, that would have many consequences. If you consider automorphism of infinite series, the answer is no. It doesn't satisfy any propy identity. But of polynomials, it would be interesting even to do it positively under the assumption of Jacobian conjecture. Okay, now let's talk about Lie algebras and about vector fields on these affine varieties. If you have an algebra A derivation is said to be locally nilpotent if for an arbitrary element a sufficiently big power of the derivation kills that element. So if you apply this derivation sufficiently many times, you get 0. But of course, how many times should depend on the element. Motivation, if the characteristic is 0, then you can take exponents of locally nilpotent derivations and get automorphisms. Now, the algebra of all derivations of polynomial algebra, so-called polynomial Cremonali algebra, is a very well-known algebra. It's one of the algebras of Cartan type, described by Elie Cartan in a different context. Now let L be a Lie algebra that consists only of locally nilpotent derivations. You see, it's kind of analog of a torsion subgroup. The following question has been around for quite a while. Is this Lie algebra locally nilpotent? This is also a part of the above mentioned program because it extends the classical angle theorem. In 2017, Petrovchuk and Sisak proved it, well, under some additional condition. And last year, Skutin proved it for the case of the polynomial algebra over a field of zero characteristic. Now, the theorem. Let A be a finitely generated commutative algebra over an associative commutative ring. Here, no restrictions on characteristic. Let L be a Lie algebra of derivations that consists of locally nilpotent derivation. Then, yes, this Lie algebra is locally nilpotent. The assumptions on finite generation of Lie algebras in theorems 3 and 4 are essential. There are counterexamples. No. The assumptions on finite generation of the associative algebra A are essential. There are examples of, if you consider the algebra of polynomials and countably many variables, it has an infinite dimensional non-nilpotent Lie algebra of derivations, and all derivations are locally nilpotent. It also comes from Golod's examples. Now, birational vector fields. Let A be a commutative domain. Let K be a field of fractions. Then, of course, every derivation of the algebra A can be extended to a derivation of the field K. So you have this inclusion. Theorem 5. Let A be a commutative domain. Now we don't assume that it is finitely generated. Let K be a field of fractions. Let L be a Lie algebra that consists of locally nilpotent derivations. And now we weaken the assumption on finite generation as follows. We demand that this dimension is finite. If A is finitely generated, then it holds automatically. And in this case, the Lie ring L is locally nilpotent. And from this extension, we can get the theorem for birational vector fields. Let A be a finitely generated domain. L is Lie algebra that consists of locally nilpotent derivations, then L is locally nilpotent. We apply this theorem to K, and K is not finitely generated. Now, we could consider non-commutative versions of the above theorems. One way to extend the results of polynomials to non-commutative context is to move to PI algebras. I already talked a lot about it. And yes, theorems 3, 4, and 5 all hold for PI algebras. I did not mention them separately, just the same theorems. But instead of commutative algebras, we consider PI algebras, the same ideas of the proofs. Basically, I finished. Thank you.
I would like to thank Professor Zermanov for his valuable talk. Is there any comment? Okay, there is no comment. Thank you again, Professor Zermanov.
Thank you for your
Now,
patience.
thank you. Please stop your screen sharing.
Yes, stop sharing the screen.
Thank you.
Done?
Yes. Now we will continue with the next talk moderated by my colleague Hande Uslu. Oh, sorry. We have time. We have 20 minutes break for the next section. Thank you again.
Hello everyone, good morning, good afternoon, and good evening. Today we are in the second day of the webinar. We started with the Professor Evim Zalmanov. He gave a nice presentation for us. Now we will continue with regular session. Our first speaker is the Yasin Küçükarıkan. I saw Professor Küçükarıkan between our panelists. Can you hear me?
Okay, yes, do you hear me?
Yes, we can hear you very well. Welcome to our second day of the webinar. Let me introduce you before starting the presentation. Professor Yasin Küçükarıkan is attending from the Yozgat, Turkey. Today, he is going to give a presentation titled by On Bohr's Theorem of Surfaces. If you are ready, you can share your screen.
Okay. Do you see a screen now?
Yes, we can see. Can you make a little bit full screen? Yes, it's perfect. If you are ready, you can start.
Thank you. Welcome, dear participant. Today, I will talk about on Bohr's theorem of surfaces. Firstly, I want to give summary of presentation, the motion of surfaces, the history of Bohr's theorem, definition of surfaces, Bohr's theorem for space-like surfaces, Gauss map of isometric surfaces, examples. Now we give the motion of surface. In the lab, examples of surfaces can be seen everywhere, such as balloons, inutubes, cans, and soap films. Rotation surfaces are one of the most well-known surfaces. Since they are found in many places in nature, they are also used in geometric modeling. For example, bottle, glasses, furniture leg, etc. A natural generalization of the rotational surfaces are helicoidal surfaces. Also, we have often come across examples of helicoidal surfaces in nature, science, and engineering, such as creeper plants, helicoidal stairs, parking garage ramps, helicoidal towers, and skyscrapers. In 1862, Bohr gave the following statement about in isometry between a helicoidal surface and rotation surface in Euclid 3 space, which is called Bohr's theorem. Bohr's theorem, a generalized helicoid, is isometric to a rotational surface, so that helices on the helicoid correspond to parallel circles on the rotational surface. Nowadays, a lot of others have studied on Bohr's theorem in three-dimensional Euclidean and Minkowski space. For example, Bohr gave us the theorem above. Ikawa applied force to surface in Euclid 3 space and studied Gauss map of this surface. Then Ikawa moved this work to Minkowski 3 space. And Güler and et al. Studied on Bohr's theorem in both Euclid and Minkowski 3 space. Finally, he and Teng studied on Bohr's theorem in Euclid 4 space. Why will we study in Minkowski spacetime? Because Minkowski spacetime is strongly related to Einstein's special theory of relativity, and it was proposed as a model for spacetime in special theory of relativity by Minkowski in 1907. The Minkowski spacetime has more complicated and richer geometric structure than the Euclidean 4 space due to the difference between their metric, angle, and the motion of particles. Then, in Minkowski spacetime, there are three types of rotation with two-dimensional axes called elliptic, hyperbolic, and parabolic rotation, which leave the space-like, time-like, and degenerate invariant. By using these rotations and the definitions of helicoidal surface, Babarsan and Sönmez gave the following definitions: helicoidal surfaces. We assume that beta is a smooth curve in a hyperplane H and P is a plane in H. If beta is rotated about P, then we have a rotational surface in Minkowski spacetime. Also, we assume that when beta rotated about P, it simultaneously translates along a line L parallel to P, so that the speed of the translation is proportional to the speed of rotation. Then we have a helicoidal surface in Minkowski spacetime. According to this definition, we will give the following three types of helicoidal surfaces, respectively. Firstly, helicoidal surface of type 1 is given by equation 1. X1 leaves time-like plane invariant and it is translated along the time-like axis which is parallel to this plane, where lambda is positive real number. Simply, we have induced metric of x1 equation 2. If lambda equals 0, then the helicoidal surface is reduced to the rotational surface equation 3. And the induced metric of R1 is equation 4. Similarly, helicoidal surface of type 2 and type 3 as follows. Helicoidal surface of type 2 is given by equation 5. X2 leaves space-like plane invariant and it is translated along the space-like axis, which is parallel to this plane. And we have the induced metric of X2 equation 6. Then the helicoidal surface is reduced to the rotational surface equation 7. And induced metric of R2 is equation 8. Finally, helicoidal surface of type 3 is given by equation 9. X3 leaves light-like plane invariant and it is translated along the light-like axis which is parallel to this plane, where eta 1 space-like, eta 2 space-like, X3 light-like, where X3 eta 4 minus eta 3 divided by square 2. Finally, X4 light-like and X-like eta 4 plus eta 3 divided by square 2. And we have induced metric of X3 equation 10. Then the helicoidal surface is reduced to the rotational surface equation 11. And the induced metric of R3 is equation 12. Now we give the Gauss map for later use. Let X be an isometric immersion of an oriented n-dimensional Riemann manifold M into a Euclidean space e to the power m. The classic Gauss map B is a smooth map which carries each point P in M to the oriented n plane in e to the power m, obtained by parallel translation of the tangent space to xm at xp in e to the power m to the origin. And the same definition is given similarly as for the normal vectors of this surface. Does a helicoidal surface in Minkowski spacetime have an isometric rotation surface? Let's start give Bohr's theorem for the surface of type 1. X1 space-like helicoidal surface is isometric to the R1 space-like rotation surface equation 15. So that helices on the space-like helicoidal surface of type 1 correspond to the parallel circles on the space-like rotational surface, where AU and BU are differential functions satisfying the following equation. 16. Now we give proof of this theorem. We consider equation 2 and it in the orthogonal condition we get equation 70. By solving the equation 70, we find equation 80. Subsetting the equation 80 into, thus the induced metric of x1 becomes equation 90. Then comparing the equation 90 and 4, we get an isometry between x1 and r1. Thus we have equation 20, and then we find equation 21. Thus we get the space-like rotational surface R1 given by 15, which is isometric to x1. If we choose a helix, it corresponds to parallel circles. Also, we can give the following theorem. Let x1 be a space-like helicoidal surface of type 1 given by 1 and R1 be a space-like rotational surface of type 1 given by 15 in Minkowski spacetime. If they have the same Gauss map, then they are hyperplane at minimal. We give proof this theorem too. The Gauss map of surfaces is equation 22 and 23. Then comparing the equation 22 and 23, then as u equal constant, thus the surfaces are hyperplanar, and also we get the following equation 24 and 25. Then on the other hand, equation 16 gives, we have equation 26. Using the equation 26 in 25, we get equation 28, 27. Moreover, we have equation 28. As a result, equation 25 and 27 equals 0 from equation 28. In addition, the surfaces are minimal, since the mean curvature of the surfaces is 0. Thus, we get the desired result, and the parameter of surfaces becomes as follows. If isometric x1 and r1 have the same Gauss map, then their parameterization are given by equation 29 and 30. Finally, we give the following example for the surface of type 1. Then this surface figures as follows: x1 and r1. Similarly, we have consequence of type 2 and type 3 surface. X2 space-like helicoidal surface is isometric to the R2 space-like rotational surface equation 31. So that helices on the space-like helicoidal surface of type 2 correspond to parallel ellipse on the space-like rotational surface, where AU and BU differential function satisfy the following equation. Next theorem. Let X2 be a space-like helicoidal surface of type 2 given by 5 and R2 be a space-like rotational surface of type 2 given by 31 in Minkowski spacetime. If they have the same Gauss map, then they are hyperplanar and minimum. Then theorem. If isometric x2 and R2 have the same Gauss map, then their parameterization are given by equation 33 and 34. Finally, we get the following example for the surface of type 2. Then the surfaces figures as follows: x2 and R2. Finally, Bohr's theorem for surface of type 3. A space-like helicoidal surface of type 3 in Minkowski spacetime given by 9 is a isometric to a space-like rotation surface, equation 36. So that helices on the space-like helicoidal surface of type 3 correspond to straight lines on the space-like rotational surface, where AU and BU are differential functions satisfying the following equation. Next theorem. The Gauss map of a space-like helicoidal surface of type 3 in Minkowski spacetime given by 9 and the space-like rotational surface in Minkowski spacetime given by 36 are definitely different. Finally, we give the following example for the surface of type 3.
Sorry for interruption. You have last 2 minutes.
Okay. The figure of the equation 38 and 39 as follows. This work is able to at Archive number this. Finally, we have references. And thank you for your attention.
Okay, thank you very much for this nice presentation, Professor Küçükarıkan. Let me ask our audiences about the questions. Is there any question or any valuable comments? If you have any question or comment, you can use the question and answer window, and you can write your messages from here. Okay, I think there is no question. I would like to thank one more time Professor Küçükarıkan. It was an interesting presentation. Thank you for your attention and your contribution to our webinar.
Thank you.
Okay, let me stop your sharing. Now we will continue with the next speaker. He is the Manchov Manev from the Plovdiv, Bulgaria. Now I couldn't see him. Let's wait a couple of minutes. If he has some connection problems, then we will continue our program. Hello again. Our break is over. Now we are continuing our program as scheduled. Our next speaker is Beyor Benomor. Professor Benomor, can you hear me?
Yes, we are here. I am here.
Okay, let me introduce you. Our professor from Mascara, Algeria, and today he is going to give a speech with titled by Ricky Solitons on Sasaki manifolds under a new deformation. If you are ready, you can share your screen.
Yes.
If you are available, also you can open your video.
Yes, wait a minute.
Yes, now we are seeing your presentation. Can you make it a full screen?
Yes. We start?
Yes, you can
Yes.
start.
Yes. I am Beyor Benomor from Algeria. My presentation, firstly, ladies and gentlemen, hello. My presentation title is Ricky Soliton on Sazakian manifold under a new deformation. Introduction. The object of this presentation is to introduce a new transformation of almost contact metric manifold. Firstly, starting from a Sazakian manifold, we constructed another Sazakian manifold and we prove some geometric property. Secondly, we study Ricci Soliton in Sazakian manifold under this deformation. Concrete examples are given. We know that the deformation of Tano preserves the Sazakian structure. In this work, we use the deformation of almost contact metric structure presented in reference 2. Review of needed notions on an odd dimension Riemannian manifold MG is said to be an almost contact metric manifold if there exists on M one tensor field phi bar, vector field xi, and one form eta such that the system one verified. We also have phi xi equals 0 and eta v far equal 0. The almost contact metric structure of manifold M is said to be normal if crocus phi bar equal minus 2 differential eta xi, where crocus phi bar denote the Nijen-House torsion of phi bar. A normal contact metric manifold is called a Sazakian manifold if can be provided that a Sazakian manifold is K-contact and that an almost contact metric manifold is Sazakian if and only if the formula 2 is verified. For a Sazakian manifold, the following equation 3 and 4 is odd, where R is the curvature tensor and S denote the Ricci tensor. Deformation of Sazakian structure, let phi var xi eta d be an almost contact metric structure on M. Riemann change of structure tensor of the firm system 5, where theta is a closed one form orthogonal to eta on M. Remark, note that the simplest case for this deformation is for theta equal differential function f, where f in C infinity m and Cf equals 0. Here there is two propositions. Firstly, the structure phi var tilde eta tilde xi tilde g tilde is an almost contact metric structure. The second present the related between lambda nabla tilde and nabla, where nabla and nabla tilde denote the Riemannian connection of G and G tilde, exactly where phi tilde xi eta G is a Sazakian structure. Theorem: if phi xi eta G is a Sazakian structure, then the new structure is a Sazakian too. Here there is the example, exactly example of Blair. The manifold R dimension 2n plus 1 with the structure G phi var xi and eta presented in the following related is a Sazakian manifold. There is an infinity number of possibility to choose theta under the two conditions: differential theta equals 0 and theta xi equal 0. Theta, let us take theta equal half differential y e, and using the formula 5, we obtain the new structure G tilde phi var tilde xi tilde eta tilde. So one can check that the new structure phi var tilde xi tilde eta tilde G tilde is a Sazakian structure. Curvature formulas and main reason that M, G, Xi, eta, G be a Sazakian manifold. By a direct computation, we obtain the following proposition is the related between R tilde and R, where R tilde and R denote the curvature tensor for G tilde and G. Proposition: if M tilde, if the structure M phi xi eta G is a Sazakian manifold of sectional curvature C equal 1, then the new structure phi tilde xi tilde eta tilde G tilde is a Sazakian manifold of sectional curvature C equal 1, 2. Here is the example. Let S the spheral of dimension 2n plus 1 equipped with the canonical Sazakian structure phi var xi eta G of constant sectional curvature 1. One can check that the spheral equipped with the new structure is also a Sazakian manifold of constant sectional curvature equal 1. Finally, Ricci-Souliton in deformed Sazakian manifold. Ricci-Souliton introduced by Hamilton in reference 30 are natural generalization of an Einstein metric. A complete Riemannian metric G on a smooth manifold M is a Ricci solidon if there is a vector field V and a constant lambda such that the formula 7 is verified where the LV G denote the Lie derivative of G along with vector field V and lambda a constant and arbitrary vector fields x, y on M. Theorem: let GV lambda V Ricci solidon on the Sazakian manifold M phi var xi eta G. If the relation 8 is verified for all vector fields field x on M, then the G tilde V lambda is a Ricci solidon on the deformed Sazakian manifold M phi var tilde xi tilde eta tilde G tilde. Here, here is the example. We will employ the example above for dimension 3. The Sazakian manifold R3 phi var xi eta G, where G phi xi eta presented with the following equation, admit Ricci solidon. GV lambda such that V equal minus 4 multiplied x dirham x plus y dirham y plus 2z dirham z and lambda equal 6 for the one form theta, we have theta equal ax plus by multiplied d differential x plus ay plus d bx multiplied d differential y, where a and b are real numbers. Now, using the formula 5, we obtain the Sazakian manifold G tilde, phi var tilde, xi tilde, and eta tilde, which admit the Ricci solidon G tilde, V, and 6. And here there is the the reference which use it in our work. Thank you.
Thank you very much, Professor Ben Omar. Let me ask for questions. Is there any question or valuable comments from audiences? If you have any anything to say, you can use the question and answer window, and you can use the screen. Okay,
sorry for my question. Sorry for my poor English.
No problem. We understood you very well. I would like to thank one more time. It was a well-designed presentation, and you use your time very well. Thank you very much again. I think there is no question. We would like to thank you for your contribution to this webinar. Now, let me stop your sharing, and let's wait 5 minutes for the next speaker, Muhammad Abdulmalek. Hello again. Now we will continue as scheduled with our new presenter, Muhammed Abdulmelek.
Yeah,
Professor Abdulmelek, can you hear me?
yes.
Okay, welcome to our webinar. Now your turn. It's your turn. If you are ready, you can start sharing your screen and you can open your camera if you are available.
It's okay.
Yes, your presentation is okay. If you are available, open your camera. Let me introduce you. Professor Muhammed Abdulmelek is attending from the Tlemcen, Algeria. Today, he is going to talk about some results for constant H sub-R hypersurfaces embedded in pseudo-Riemannian manifolds. If you are ready, you can start your presentation, Professor.
Okay, thank you. First of all, I want to thank the organizer committee for giving me the chance to present my work. Some results for constant higher order mean curvature hypersurfaces embedded in pseudo-Riemannian manifold. So in this work, we will deal with what we call the Alexandrov conjecture, spherical cups conjecture, which says that any compact connect hypersurfaces of constant mean curvature and spherical boundary must be a planar disk or spherical cups. Many works gave a partial answer to this result. One of the remarkable result is the theorem of Rosenberg, which says that if we take a compact hypersurfaces embedded in real space with a boundary strictly convex and include in an hyperplane of Rn, then if M and this hyperplane are transverse along the boundary sigma, then M is in one of the half space of Rn plus 1 obtained by the hyperplane, and M has all the symmetries of sigma. In particular, if sigma is a sphere, then M is a spherical cup. So our idea now is to try to generalize these results in the case of the pseudo-Riemannian case. So we will replace the hyperplane by totally geodesic hypersurface, and we will try to give a sufficient condition that M and this totally geodesic hypersurface will be transverse. This result from this result we can deduce this new theorem, which says that the only compact hypersurfaces embedded in real space with constant higher order mean curvature and spherical boundary are the planar disk when HR is equal to 0 and the spherical cups when HR is identically null. So we define what we call the Newton transformations. So given M an oriented and connected hypersurfaces in an oriented pseudo-Riemannian manifold, and we put A its corresponding shape operator. So the Newton transformations are defined inductively by this formula or equivalent to this relation. And the characteristic polynomial of A is defined by this relation, where sigma R is just the elementary symmetric function defined by this formula, and x1 to xn is the eigenvalue of the shape operator. We define also what we call the higher order mean curvature. It's defined by this formula. In particular, for R is equal to 1, we have the classical mean curvature in pseudo-Riemannian case. And for R is equal to 1 to n, we have the definition of the Gauss curvature for the pseudo-Riemannian case. Now we define the generalized Newton transformation. So, if we take A is a family of two endomorphisms, define the length of U by this relation and the factorial of U. And for T equal to T1, T2, we define the product TA. So the Newton polynomial PA is defined by this formula. Is a polynomial of two variables, T1 and T2. And we have PA to T is equal to this relation, where sigma U is depend only on the value of A1 and A2. So we can see that sigma of 0 is equal to 1, and we put sigma U is equal to 0 when the length of U is strictly superior to n. For example, if A is equal to BC, then we have the element, the symmetric functions of A, or the symmetric functions. To find these symmetric functions, we can just calculate, here the calculus of PA de T, and sigma U is just the coefficient of, we can do the equality, and we find sigma U is just the coefficient of TU. For an integer alpha, we define the musical function alpha b mod and alpha ds by these relations. For example, if U is equal to this relation and alpha is equal to 2, then we will work just by for the second coefficient, which equal to 3, and we have the definition of the functions. So the generalized Newton transformations of two endomorphisms T1 and T2 of A are defined by these relations. So in our work, we have this hypothesis. We can we given a manifold, oriented, connected, and compact hypersurfaces in an oriented pseudo-Riemannian manifold with smooth boundary sigma. We take P a totally umbilical hypersurfaces of M bar such that the boundary of M is included in P. For a point of the boundary, we denoting by E1 to En minus 1, an orthonormal basis of the tangent space of sigma. Here, because sigma is included on P, in P, we can complete this basis by an orthonormal, a normal vector field to get a basis of the tangent space of P. And because P is also included in M bar, we can complete par another vector normal to P in M bar to get a basis of M bar. The same thing, because sigma is the boundary of M, we can complete this basis by another vector normal to sigma in M to get a basis of M. And because M is an hypersurfaces of M bar, we can complete it by another vector, a normal vector to M in M bar to get another basis of M bar. So for each vector normal, we consider the fundamental operator corresponding to these inclusions, where these vectors are the unit normal vector field of the inclusion. So the vector which we work with this, and it is not difficult to see that we can see the article of Alias, Malak, and Lopez, that we have this relation. Now, our idea, we will try to find the matrix of the operator A. So our idea is we will write the covariant derivative of EG in the two bases and do the equality of the two quantities. So we use also the definition of the shape operator. We can find this relation. So suppose now that P is totally empiric, so there exists a smooth function lambda such AP is equal to lambda times identity, and putting to simplify these relations. So this formula, you can see that this formula give a partial answer of our problem because it realizes the geometry of M in M bar given by I, and the geometry of the inclusion sigma and P given by A sigma, and the geometry of the inclusion P in M bar given by mu. So we will use the two Newton transformations. In the left, we have the classical Newton transformations, and in the right, we have the generalized Newton transformation. So our objective is to find these two results. So here we use just the property of the elementary symmetric functions. Now we can choose the basis of the tangent space of sigma by the eigenvectors of A sigma. So we have A sigma of EI is 2I EI, and we have now, we can write our matrix of the shape operator. So now we will calculate the characteristic polynomial of A and to find the elementary symmetric functions. So putting for simplify I is equal to this relation. Our first proposition is under the above hypothesis, we have sigma R of A is equal to this relation. And for the proof, it's not difficult. We can just calculate the polynomial characteristic of A and the polynomial characteristic of this quantity, and take the equality of the coefficient of the same puissance. The second proposition is, if we have A is equal to this relation, this quantity, and A bar is a family of these two endomorphisms, then we have sigma R of the restriction of A in sigma is equal to this relation. You see here in the left that we have the classical elementary symmetric functions, but in the left we have the generalized elementary symmetric functions. The Newton transformation on the boundary. So here we will work on the boundary. If we have all these hypotheses, then TR VV is equal to sigma R, the restriction of A on sigma. Now replace this quantity in here. We will find these relations. And if now we take P a totally geodesic, then lambda is equal to 0. And here we have just the quantity 1 L is equal to R. And we have this relation where rho is equal to this quantity. Now, our theorem is under the above hypothesis. M and P are transverse along sigma if for some R the Newton transformation is positive defined. Here we gave a partial answer of or the first part of the proof of the Rosenberg theorem. The problem now is to prove the second part of the Rosenberg theorem, which till now is an open problem. If we can prove the second part of the Alexandrov of Rosenberg theorem, we can generalize the Alexandrov conjecture for the case of the pseudo-Riemannian manifold. So here we have some references, and thank you for your attention.
Thank you very much, Professor Abdulmelek. It was a nice presentation. Is there any question or comments for Professor? If you have anything to say, you can use the question and answer window, or you can write from chat, of course. I'm controlling my windows. I think there is no question. Thank you very much again, Professor Abdulmelek. We would like to thank you for your nice and interesting contribution to our webinar. Thank you very much. Now we have a little break for 4 minutes, and we will continue with the next speaker as scheduled. Hello again, dear participants. Now we are continuing with our next speaker, the Professor Tülay Yıldırım Turan from the Karabük, Turkey.
Sorry, I'm here, Manchumane.
Yes, I can hear you, but you missed your turn, so please wait for the next empty space. Because we need to continue as scheduled, okay? Thank you very much. Hi, Professor Tülay.
Hi.
Welcome to our webinar.
Thank you so much. Let me first of all thank you for this nice organization, and of course thank you to all members of committee. I appreciate joining here and being with you. Thank you so much.
We do thank you also. Let me introduce you. Professor Tülay Yıldırım Turan is attending from the Karabük, Turkey. Today, she is going to give a speech titled by Linear Skew Cyclic Codes over FPR. If you are ready, you can share your screen.
Thank you. Is it fine?
Yes, it's perfect. If you are ready, the microphone is with you.
Thank you. Thank you so much. Today I'm going to talk about my subject. My main subject is about the codes. Special subject is a linear skew codes over the FPR ring. First of all, let me introduce to my context. Our context include our objectives, preliminaries, the gray map of the code, and this is the one of our main subject is the generator polynomial to find the generator polynomial of our skew cyclic codes, and it will be ended with our references. First of all, why we study this subject? Because our aim is to characterize the skew cyclic codes over the new defined ring, which is FPR. Here R is FP plus VFP. FP is a finite field with the prime number P, and V square is V. In the present study, we also investigated the algebraic structure of this code in details. Then describe the main map, which is called gray map of the skew cyclic codes over the R new ring FPR, and also determine it's the generator polynomials. Our study is ended with the defined non-degenerate inner product. I mean, it's called also Euclidean inner product, Hermitian inner product, and provide a criterion for the test to test the self-orthogonality. First of all, let me introduce our rings. Here, we are specially study over the FPR. Here, the FP is a finite field with the prime number P. And R means that FP plus VFP. Here, our elements are B plus VB, B and D elements of FP with the property that V square is V. This is a commutative ring. And we also know that it has two maximal ideals. That's why it's called semi-local ring with the V and V minus 1 minus V. And there are over maximal ideals isomorphic to FP. By the uniquely express, we can express elements of R in this form. By using this form, we define two codes. C1 is the coefficients of the V, C2 is the coefficients of 1 minus V. And also by using the C1 and C2 codes, we can uniquely express any code over R in this form. And also, of course, if you are talking about the ring R, we should always describe an automorphism, theta. Here, theta is the composition map of automorphism P and theta 1 defined in the R references tree. And it sends B plus VB to the B to the P 1 minus VD to the P. And also, its elements are defined as AX and BXN is elements of Rx theta. This is the polynomial ring, I mean. This multiplication is defined by using the automorphism over R. Also, this is, as I said, that it's the polynomial ring. Its elements are coefficients are coming from R. And what about the R new ring, FPR? FPR we denoted FPR with a binary. I mean A, B plus V. Here the A is elements of FP, B plus VB, VD is elements of R. Also, if C is a skiff cyclic cos over R new ring, and alpha is the set of FP, shows it's the coordinate positions. Any code from C over FPR are denoted in this form with the binary operations. Also, let me introduce the cyclic shift. What is the meaning of cyclic shift for our new ring? We define PC and theta automorphisms of FP and R respectively. Then we said that a code C over FPR is skiff cyclic code of length alpha plus B if C is an R modulo of FPR and C is closed under this cyclic shift, and we introduce this cyclic shift in this form. And if you want to give the relation between the ring and a finite field FP, we define the map delta, which sends B plus VB elements of R to the B. It has also scalar multiplication by star. We said that if you multiply any elements of R with the FPR, you should take the first binary under the delta homomorphisms. And we give this some basic and well-known notions for our new ring FPR. We said that the code C is FPR linear skiff cyclic code of length alpha plus beta if and only if C is a left Rx theta submodule of R alpha beta. Then we define the Euclidean inner product for our ring. We said that X and Y is defined in this such a summation form. And of course, after the earlier Euclidean inner product, we have to give the duality definition. Duality is the well-known definition, except we take our elements here, FP alpha, R beta. And if C is an FPR skiff linear code of length alpha plus beta, with the beta is an even integer numbers, then we show that dual of C is also skiff cyclic code of length n. Also, then we start to define and introduce gray map over the ring FPR. We said that we always know that gray map satisfies relation between the ring and field for the codes. So we said that if C is a code over R, we can move these codes to the field from R to FP to N. Why we took to N? Because here R is FP plus VFP. For any code, we define gray map as which sends C to the BC, BC plus DC. Why? Because here C we took as a n-tupes. What about the gray map over FPR? FPR has two elements, A and B plus VB. Now we said that under the phi map, we can define gray map as A, B, B plus B. This is the extension version with the n-tupes of the gray map. If C is FP linear code, under the gray map, it's easy to say that phi C is also FP linear code. And we define the basic proposition, and we show that if phi is an FP linear distance preserving map, I mean from Lie distance to the Hamming distance, it is preserving under the map of gray map. Let's see be a linear self-orthogonal code over FPR. Then we show that under the gray map, which is still self-orthogonal code over FP. And if we take C as a FPR skiff cyclic code of length n, I mean alpha plus beta, then phi C can be written as a direct product of C1, C2, C3, where C1 denotes cyclic cut of length alpha in FPX, alpha minus B1. C2 and CTR denotes skiff cyclic cuts. And for the new definition about the quasi-cyclic cut over Fp, C is a linear cut over Fp and it is summations of Mi. We denote Fi in this form. We said that if F is a product of Fi, then C is skiff generalized quasi-cyclic cut. For this cut, we define a new map as a lambda. By using this definition, we prove that if phi is a gray map, then phi cyclic shift equal to the lambda phi. And then if C is a linear cut of length alpha plus beta over FPR, then C is an FPR linear skiff cyclic cut, or if and only if it's the gray map is a generalized skiff cyclic cut over Fp with the length alpha plus 2b. When we come to the generator polynomials for the R new ring FPR, first of all, we said that here the zero vector or zero polynomials are denoted by 0. If we are talking about these notions, which means that f of x is a right or left divisor of x to the alpha minus 1. First of all, we prove that. Let I1 be an ideal of FPR. It means that for any polynomial gx taken from this polynomial ring, then I1 is generated by left divisor of x to the alpha minus 1. And now we take another ideal which belongs to the R x theta, such that it's the polynomial coming from R x theta over x to the beta minus 1. Then we show that this ideal is principally generated left Rx submodel of this polynomial. This is one of our main theory we prove. We show that, let's see the FPR skiff cyclic cut of length alpha plus beta, then this C is generated by these polynomials. Here f of C is a generator polynomial of Fp, x, Pc, C, Jx and Hx is the Jx also polynomial of Fp, Hx is polynomial Rx theta. Also Ra, Hx can be written V H1x 1 minus V H2x. And after the theory, it's easy to give this corollary. I mean C over FPR can be written with these also generator polynomials. This theory also are another but the main theory, because by this theory we also decided basis of the code. We said that if C has such a generator polynomials, then C for these spanning sets, C has such a minimal spanning set. And also by using the previous corollary, we show that these bases can be seen in another forms. For the generator polynomial gx0, it has such a minimized spanning set form. For the generator polynomial jx hx, we have such a polynomial, such a minimized spanning set. And for the generator polynomial union of g of x0, j of x hx, it has union of these minimized spanning sets. Also, we still continue to improve our study with given some examples nowadays. These are our basic references. There we go. Thank you for your all patience and attention.
Thank you very much, Professor Tülay Yıldırım Turan. It was a very nice and well-organized presentation. Let me ask for question and answer. Is there any question or valuable comments for Professor Turan? Okay, I think there is no question. I would like to thank one more time for your contribution to our webinar. Thank you very much.
Have a nice day. Thank you.
Thank you very much. Now we can continue our program with our invited speaker talk. It is going to be at 10:45. So now we are giving a little break till the 10:45. Then we will continue with Professor Tekin Dereli. See you soon. Hello Professor.
Merhaba, merhabalar.
Merhaba hocam.
Tamam, ben screen share'e hazır olayım.
Tamam hocam.
Geldi mi screen?
Geldi hocam.
Full screen yapalım.
Evet, yeşile basalım.
Tamam.
Tamamdır hocam.
Sesim de geliyor, görüntü
Evet,
de
hiçbir
iyi.
sorun yok. 10:45'te başlayabiliriz.
Peki. Sen hangi üniversitedesin?
Yıldız Teknik Üniversitesi'ndeyim hocam ben.
Hangi matematik bölümünde?
Matematik bölümündeyim.
Peki.
Görüşmek üzere hocam. Hemen break'te
Tamam.
bekliyoruz.
Tamam, her şey tamam.
Hello everyone again. Welcome to the invited speaker session. I'm Hande Uslu. Now we will continue with the invited speaker speech. I would like to invite Professor Tekin Dereli. He is from the Koç University, Turkey. Hello, Professor.
Well, I cannot start the video. I think you have to allow me. Start video.
Try one more time.
The co-host
Yes,
has asked to start your video now. Okay.
Now we can see you, right?
And then share screen.
Yes. We were looking forward to listen you.
Okay. Okay. Right.
Okay, let me introduce you one more time. Professor Tekin Dereli is going to give a speech titled by Connection and Curvature on the Principal Fibre Bundles over Spacetime and Gauge Field Theories of Fundamental Forces of Nature. If you are ready, Professor, we are ready to listen you.
Yeah, thank you very much for this invitation. As you see, I have two addresses now. I used to be teaching at Koç University. Now I'm working at Maltepe University. But before moving to Istanbul, I was working at the Middle East Technical University. I worked for several years at the math department, and I was in the applied mathematics group there. So that's where I come in the applied mathematics. Then I worked in the physics department with the mathematical physics group. Well, I don't know what's the difference, but on the other hand, the terminology that I like best is physical mathematics or theoretical mathematics. This terminology was introduced some years ago by Jaffe and Quinn, and which was commented on by the famous mathematicians. I don't know why it didn't catch up, but nevertheless, physical mathematics is the best term that will explain what I'm going to talk about today. Now I'm going to talk about the mathematical structure that's common to all the field theoretic models of fundamental interactions of nature acting among the elementary particles of matter. Such theories are today well established. Now the prototype gauge field theory is Maxwell electrodynamics. In this picture, the long-range electromagnetic forces are due to the exchange of massless electrically neutral photons between electric charges. It's an old relativistic classic field theory with a relatively recent U1 gauge field theoretic interpretation. I said relatively recent, it's due to Hermann Weyl almost 100 years ago. Now, a similar picture occurs for we are now confident about the standard electroweak gauge theory, which is based on the gauge group SU2 cross U1 among the three generations of leptons. Leptons are electrons and electron neutrinos, but there are three families, such similar families, muon and muon neutrino, tau and tau neutrino. So all of these are copies, these pairs are copies of each other, electron generation, muon generation, tau generation, and they all interact with the exchange of electroweak gauge bosons. And essentially in a similar way, the asymptotically free forces among the color quarks that make up the hadrons, such as protons and neutrons that held them together due to the exchange forces due to color SU3 gluons. This theory that we call quantum chromodynamics, it has interesting properties. Now, asymptotically free forces, I'm not going to talk about this much, but this implies a conjecture called color confinement or quark confinement. Among the mathematicians, it has a different name. It's called the mass gap problem. It is one of the $1 million problems announced by the Clay Foundation. It's not yet solved. So quantum chromodynamics is also interesting, but I'm going to concentrate on the electroweak theory. Now, what's the common gauge theoretic structure among these three models? Now, in order to explain that, let me consider a principal fiber bundle where the base manifold is a differentiable manifold, and a typical fiber is a local Lie symmetry group. Let me take it to be of dimension n. M is usually taken to be the four-dimensional space-time. However, space-time has additional geometrical structure, which is not shown here. It has a metric, it has a connection for parallel transport, it has, in general, curvature. I'm not going to worry about these things. I will come to that later on. At this point, I'm going to take M as a Minkowski space-time, which is flat. And also, I'm going to take it to be topologically trivial. It is essentially R4. And I'm going to take it to be without boundary. So all the complications about the geometrical structure of space-time, I throw it out at this point. I'm going to take just a four-dimensional Minkowski space-time with no topological obstructions. Okay, and what we call gauge theory is the theory of a linear connection on the bundle. The pullback of this linear connection on the bundle onto M is identified with the Young's potential one form that I show with A. And the corresponding pullback of the curvature, F, is the Young's field 2 form. Now, in the geometric formulation of Maxwell equations, the connection and curvature are just abelian. It's the principal U1 bundle over space-time. And this allows a direct generalization to Young-Mills gauge theories, which was achieved in 1954. C. N. Young and R. L. Mills. C. N. Young is celebrating his 100th birthday this year, 2022. He's still alive. I don't know, he's not writing papers, but he's still active. We start by giving the basic field variables as the G Lie algebra valued Young-Mills potential one form. This is the Lie algebra. And then these are the generators of the Lie algebra, basis for the Lie algebra, given in the adjoint representation of the Lie algebra. And then I introduce a coordinate chart that I call x mu. This can be Cartesian coordinates of a point in M. And then what the physicists call Young-Mills potentials is these components, A, J, mu. In internal symmetry index J goes from 1 to N. And then a space-time index mu, coordinate index mu, which takes values from 0, 1, 2, 3. And then the Lie algebra generators satisfy the basic structure equations. Their Lie brackets is just proportional to the generators again. And these coefficients here are identified as the structure constants of the Lie algebra. They are constants. And the corresponding Young-Mills form can also be expanded in a similar way in a coordinate basis relative to that Lie algebra basis. And again, what physicists call Young-Mills fields is this Fj mu nu with a pair of skew symmetric coordinate indices. And what is typical of the Young-Mills field is this nonlinear term. In the case of the Maxwell field, there is no nonlinear term. It's just the first two terms given the electromagnetic fields in terms of the potentials. But in the Young-Mills case, there is the self-interaction term here. Now, what is important for our purposes is how does this potential and the field change under a local change of section of in the bundle. It is called the local gauge symmetry transformation with a Lie group element U, an arbitrary local Lie group element U. The Young-Mills potential one form transforms inhomogeneously. So this is not a tensor anymore. A is a connection. A is not a tensor because of this nonlinear inhomogeneous term under a change of local section in the bundle. It's a local gauge symmetry transformation of a potential. This is typical. But on the other hand, if you put this in the definition of the Young-Mills field, you will see that F transforms as a tensor. And we get something more from this definition as well. Take the definition of F. Just take the exterior derivative df. D square is 0. That goes out. And then I have dA wedge A minus A wedge dA because D is a graded derivation. And then you cancel some terms and reorganize them, and then you get a Bianchi identity. This is the gauge Bianchi identity. That comes from the geometry of the principal fiber bundle. Now we have to postulate the field equations, the actual field equations. In the case of Maxwell equations, there is no nonlinear terms that are not present for a U1 gauge field theory. df equals 0 are the homogeneous bit of the Maxwell equations. It involves the Faraday law charge density and electric current density. And here we postulate Young's field equations by introducing the Hodge dual of F, star F. It is in the Maxwell case, E goes to B, B goes to minus C. Electric and magnetic fields are switched. So the dual field 2 form, star F, satisfies the Young's field equations with a source term here. And it has a covariant conservation relation satisfied. You can take the Young's field equations and apply the exterior, take the exterior derivative, first term vanishes, and you can organize the second terms, and then you can get an expression for D star J, the divergence of a current density vector. And then you will see that the conservation law is not a true conservation law for the gauge current. It will have these inhomogeneous terms. That's important for physical interpretations. Now, this is the common structure for all the gauge models. However, the things are much more involved than that. And I think in order to show that, I will go through a very quick, a very brief account of the standard electroweak theory, which was introduced in 1967 by Abdus Salam and Steven Weinberg. It was introduced as the SU2 cross U1 model. So we are now so confident that we elevate it to a theory. So standard electroweak theory. In this case, the local gauge group is SU2 cross U1, but SU2 is corresponds to the isospin invariance, and this U1 is not electric U1; it is a hypercharge. So I refers to isospin, Y refers to hypercharge, that are both conserved charges, and then the gauge symmetry should be spontaneously broken down to the electromagnetic U1, which is identified as the electromagnetic gauge group. Now, the important thing is that this electromagnetic U1 gauge symmetry group is not the hypercharge symmetry group. It's a diagonal embedding of U1 into SU2 cross U1. So U1 is going to get contributions from both factors in this direct product. And now we introduce Young's gauge potentials associated with the SU2 and with U1 separately. The terms of 3 by 3 matrices, and the structure constants are simple. That's why I'm going through this example here. They are just Levi-Civita symbols with JKL, epsilon 1, 2, 3 equals 1, and then it will be +1, -1, depending on whether you have an even permutation of 1 to 3 or odd permutation of 1 to 3. And the corresponding Young's field 2 term has also a similar expansion. It's an SU2 valued field 2 form, and it satisfies the SU2 Bianchi identity. We also introduce an abelian gauge potential associated with U1, and then the corresponding field 2 form. Now, what's important, we introduce a isoscalar, a scalar field for spontaneous symmetry breakdown. I think I have to be here, right? And we introduce the 6 potential, X scalar, as an isospin doublet with the upper component, complex scalar, with a positive electric charge, lower complex scalar with a electrically neutral, just like the proton-neutron pair. Remember, proton was positively charged, neutron was electrically neutral. So we have a Higgs scalar iso doublet with the upper component carrying a positive electric charge, lower complex component carrying no electric charge, and under a gauge transformation, it transforms under SU2 cross U1 as a local gauge transformation in this way, U times Y. And then we introduce an SU2 cross U1 gauge covariant exterior derivative of the Higgs scalar. Now you have to be careful about these are coupling constants that mathematicians usually don't like. They just put it together into the potential and don't show it. But for physicists, that's important. We rescale a potential by a constant factor, pull out a constant, and then this will be used as a perturbation parameter when you consider a perturbative quantum field theoretic generalization of these models. Gauge coupling constants are important, G and G prime, and they are dimensionless constants. They don't carry units, that's all. And then what about this factor? Accordance with the physical definitions of the hypercharge and isospin, the factor 1/2 appearing in the exponent is introduced to implement the Gell-Nishijima formula that gives the electric charge of the leptons. It's the third component of the isospin plus 1/2 times the hypercharge. That follows from the definition of hypercharge. So we carry that 1/2 into the definition of the coupling constant related with the U1 invariance. And also there is one other thing you have to be careful about. The SU2 gauge potential was given in a representation, in the adjoint representation, in which case the generators are given by 3x3 matrices, well, which don't work out in this exterior gauge covariant exterior derivative because phi is a doublet. So you have to have a 2x2 representation, which is the fundamental representation of SU2. So I show it by, instead of Ti, I show it by Tj divided by 2i. That's also technical skill. In order to induce the Higgs mechanism, we introduce a scalar potential. I write it conveniently in the square form, and we introduce an arbitrary positive self-coupling constant, which we don't know, it's an arbitrary parameter. And we also introduce a constant inside the parentheses. We use the real expectation value, use the Higgs scalar. A vacuum of the Higgs field is the configuration of the Higgs field for which the potential function vanishes. So the magnitude of F equals V plus or minus V is the gauge potential. Well, that defines the gauge vacuum configuration of the Higgs field up to a phase transformation. That's how we induce spontaneous symmetry breakdown. The theory has a gauge symmetry under SU2 cross U1, but the vacuum state is symmetric under a residual symmetry group, gauge group, which is just U1. I give you the field equations, and in order to very quickly go through the Higgs mechanism of generation, mass generation, let me choose a vacuum configuration. The vacuum configuration chooses the metric to be Minkowski. There are no gauge potentials, 0, 0, and the Higgs field configuration is just 0 times V. The upper positively charged Higgs complex scalar field vanishes, and the lower electrically neutral complex Higgs scalar is real. And then in order to read the masses and obtain the physical spectrum of particles, physical degrees of freedom, you perturb the vacuum solution, and then you get the linearization equations, and you read the masses from the linearized field equations. But then you have to be careful about the linearization process because we introduce a bookkeeping parameter, a perturbation parameter. So we perturb the SU2 potentials and hypercharge potentials by at the same order of magnitude. And that's the linearization of the Higgs scalar. We get epsilon phi plus and epsilon h. That's the Higgs field. That's, and then in order to be consistent, you have to perturb the metric as well, but you have to, leading term should be epsilon square. And the rest is turning the handle. You get the derive the linearized field equations for the SU2 potentials, Young-Mills potentials, and the hypercharge potentials. These are just Procca equations. You diagonalize the fields by using the following combinations of the gauge potentials and directly read the mass values. We introduced an electrically charged W plus, a complex vector field, vector intermediate vector boson, and its charge conjugate W minus as A1 plus or minus IA2. And then we have two combinations. We have a massive intermediate, neutral intermediate vector field Z given in terms of A3 and A. And then we have an orthogonal combination to Z0, which I call gamma. That's the electromagnetic photon field, which remains massless. The fact that one of the vector fields remains massless is related to the fact that the vacuum configuration of the Higgs potential has a residual U1 electromagnetic gauge invariance, and this shows up with the fact that the corresponding gauge boson is massless. The other ones are massive, and the masses are proportional directly to the vacuum expectation value and the gauge coupling constants. Now you see that mz square should be slightly greater than mw square, because this is not going to be zero, so it is strictly greater than mw square. So if you take the mass ratio, that gives us a convenient parameterization that we call the Weinberg angle. And the experimental measurements of the Weinberg angle are something like 0.25, some more digits. And you can also read the Higgs boson mass. There is one real Higgs boson, H, that is left behind. It turns out to be 8 lambda v square after linearization. Now, it can be fixed. It cannot be predicted because we don't know anything about this constant lambda. So it has to be measured and determined in the lab. It was a difficult and a very expensive experiment, which took almost 45 years to observe the Higgs boson and measure its mass. And this had been achieved in the LHC in 2012. And now the experiments are quite accurate. The masses of the gauge bosons and the Higgs bosons can be measured. MW is about 95 GeV with three digits after the comma can be determined. MZ is about 97 GeV with 3 digits as well. And what's important, Higgs mass is about 125 GeV. So it's a determined, observed and determined masses are determined. I'm going to skip this, go very fast. Well, I have discussed the gauge vector bosons. I have discussed the Higgs boson. I motivate its presence and I motivate how it induces spontaneous breakdown, but I have to also account for the fermions. I have to do it 3 times. I have to do it for the electron generation, the same for muon generation, the same for tau generation. For the electron, it's quite complicated because electron is a massive spinor. It's a 4-component Dirac spinor. It has upper 2 components given as a Weil spinor. Lower 2 components is given as a conjugate Weil spinor. You can think of this in a very simple-minded way. Is one of them is associated with the electron, while the other one is associated with this antiparticle, the positron. On the other hand, electron neutrino at first was thought to be chiral. Its electron neutrino is chiral, and then it's almost massless. So what we do is we project out chiral projection of the upper components and the lower components. One of them is left-handed, the other one is right-handed. This is for the electron Dirac spinor. And in the Salam-Weinberg model of electroweak interactions of leptons, left-handed components of the electron and the electron neutrino itself, which is left-handed, is put as a isospin doublet. And so this is I3 is equal to 1/2 for the neutrino, I3 is equal to -1/2 for the electron. So the hypercharge should be -1 as well. So this is the charge assignment. And then the right chiral projection of the electron is an isosinglet, which is isospin 0, y is equal to -1, so that the electric charge is as it should be. Now, the hypercharge assignments are more subtle. I have told you about that. Let me go it. Now, after that, we introduce gauge covariant exterior derivatives because psi L and psi R transform as iso doublet and an iso singlet under SU2 cross U1 local gauge transformations. So we introduce the gauge potentials as compensating fields. And then in order to give masses to the electron and leave the neutrino massless, we introduce a coupling of the fermion fields to the Higgs scalar fields with some new additional real coupling constants that we call Yukova couplings. And when you consider the vacuum expectation value of the Higgs field, that will give you the mass term for the electron and no mass term for the neutrino. Well, I think I'm going to be very quick. There are many reasons for not regarding the standard model as the final theory. We have to go beyond the standard model. You can read this. What we wish to consider below is the simpler question as how to incorporate the universal long-range gravitational forces that act as a distance between massive objects can be incorporated in a unified gauge theoretic picture by linking together the fundamental strong and electroweak interactions with the gravitational interactions at very high energy scales, or putting it in a different way, at extremely small distances. Now, in order to do that, I have to go through very quickly about the structure of the space-time. A space-time manifold, space-time is a triplet. It's a four-dimensional differentiable manifold that we usually take to be smooth and topologically trivial with no boundary. These conditions can all be relaxed. G is the Lorentzian signature metric on M. That is a second-rank covariant non-degenerate symmetric tensor field. And nabla is a linear connection used for parallel transporting tensor fields on M. And we are going to assume that the connection is the unique metric compatible zero torsion Levi-Civita connection. In particular, the Minkowski spacetime is topologically trivial and flat. We can introduce a local coordinate chart I'm going to call x mu. And any decent coordinate chart induces a natural basis on the tangent bundle in terms of the coordinate vector fields. And the cotangent bundle is vector space isomorphic to the tangent bundle. So the coordinate vector fields induce a natural cobasis, covectors, set of covectors, coordinate covectors that are also called one-forms coordinate differentials. And there is a natural pairing of vectors and covectors because covectors act as linear functionals on vector fields and give functions numbers here. And the metric tensor in Minkowski spacetime in a Cartesian coordinate chart, I'm going to talk about this a little bit because of this signature business. This minus is very important. It fixes a local light cone structure over spacetime, and that's what we need for relativistic field theories. And in a natural coordinate system, we usually take c equals 1. If you look at this equation here, x and y and z are measured in meters, t is measured in seconds, so c is needed there as a unit conversion factor, but it's much more than that physically. It's a constant of nature. It's one of the fundamental constants of nature that's identified at the speed of light in empty free space-time. And it's a natural speed limit. Nothing in the universe can move faster than the speed of light. So it has a physical meaning, but in this framework, it appears just as a unit conversion factor. And usually in our theories, in our equations, we assume that we are using a natural system of units where it is taken as one. And this signature here is by convention. Some people use plus, minus, minus. I prefer minus, plus, plus, and I'm going to continue like that. Now, vector fields can be expanded, and they have contravariant indices, upper indices. One forms can be similarly expanded in a coordinate basis. They have lower components, they have covariant indices, and the pairing of a vector field and a one form can be achieved by taking this summation. I'm following the Einstein summation convention. Now, the definition of metric is a bilinear map that takes any pair of vector fields and assigns to them a unique real function, a smooth function. In a local coordinate chart, when you evaluate this G in a coordinate basis, vectors del mu, you obtain a set of 10 a symmetric 4x4 matrix. It need not be diagonal in general, but it is symmetric, and it has to be non-degenerate. The metric tensor has at most 10 independent components. If you think about a 4x4 symmetric matrix, it has 10 independent components. Now, what's important is that according to Einstein's interpretation, the gravitational potentials are carried by the components of the metric tensor. In Newtonian theory of gravitation, we have just a single unique gravitational potential. In Einstein's theory, we have at most 10 gravitational potentials, which are identified as the coordinate components of the metric tensor. So all the physical interpretation resides in the metric tensor in Einstein's theory. And the non-degeneracy of the metric means that the inverse metric exists and it's contravariant. And I can, given the metric G, a non-degenerate metric G, I can assign to any vector a unique covector. I denote by X tilde. It's a rule that assigns X to a one form. This is called index lowering. Remember that X has an upper index components. X tilde has lower components. So this procedure operation is called index lowering. In a similar way, since the metric is non-degenerate, the inverse metric exists, and then in this inverse metric sends a one form to a unique vector field. I similarly denote by omega tilde. This operation is called index rating. And the signature business allows us to consider time-like, null, or space-like vectors. And in a coordinate chart, I can look at the zeroth component of the vector field as well. If the zeroth component is positive, it's a future pointing vector. If the zeroth component of the vector is negative, it's a past pointing vector, etc. And note that the similar classifications hold also for covector fields. But I don't have to stick with the coordinate frames. I can always introduce, any local observer can introduce an arbitrary G orthonormal frame of reference that I call a local Lorentz frame, or simply a frame denoted by a set of 4 vector fields. And these are orthonormals relative to the given metric G. I'm going to use a different set of indices here, A, B, etc. These Latin indices are also take values 0, 1, 2, 3. But in order to distinguish them from the coordinate-induced basis frame, I use Latin indices, mu, nu, etc. They are reserved for coordinate indices. They are related to a coordinate chart and the natural basis and natural co-basis induced by that coordinate chart. Whereas XA refers just to an arbitrary local Lorentz frame, G orthonormal local Lorentz frame. And the corresponding coframe I denote by EA, upstairs index, and there's a pairing rule. Well, delta AB is the usual Kronecker symbol. Although not compulsory, we take a right-handed frame of reference. That's a convention. This implicitly means that we are assuming an orientable space-time manifold. That's an extra assumption. In physics, we don't work with non-orientable manifolds, orientable manifolds, and choose the orientation of the frames to be consistent with one of the possible orientations of the space-time. And we use a right-handed orientation. So we fix the signature of the metric and we fix the orientation of the space-time that determines the sign of the volume element. Now the local Lorentz group is what happens if you take a frame and a coframe and change your local Lorentz, make a local Lorentz transformation. You change the reference coframe linearly in terms of this 4x4 Lorentz transformation matrix lambda AB. Now, usually we give the Lorentz boosts in freshman classes, so let me just give it a Lorentz transformation matrix, which corresponds to making a Lorentz transformation along the x-axis at the speed v. So this is the Lorentz transformation relating the coordinate measurements of 2 inertial observers, one at rest, the other one is moving with a velocity v relative to it. And then the Lorentz transformation matrix is this Lorentz boost is given in terms of the rapidity parameter, which is v over c, and then the Lorentz factor is 1 over 1 minus beta square. You will see these in your freshman classes. So what I'm talking about is that I have 3 boosts, one along the x, y, z direction, and I have three rotations about the x-axis, about the y-axis, about the z-axis. So 3 rotations and 3 boosts. the local Lorentz group is a six-dimensional Lie group. You have to be careful about the signature. We have an indefinite signature in the metric. So the local Lorentz group is SO13 rather than SO4. It's not a four-dimensional rotation. It's a space-time rotation. Now we have given this transformation rule, local Lorentz transformation of a coframe. Frame vectors transform contragradiently with lambda inverse. And then we can look at how this metric behaves, metric components behave. And you can show that this definition should hold. All the 4x4 matrices that transform according to this law with the Lorentzian signature metric constitute the matrix group, Lie group, that we call, these are orientation preserving Lorentz transformation. This is called the homogeneous Lorentz group. Now, there are several equivalent ways of prescribing a rule for parallel transport of tensors. We stick with one of these. In order to define a metric compatible linear connection, we specify it in terms of a set of connection one forms omega AB. Metric compatibility is determined by lowering an index and then taking it skew symmetric. I'm not going to explain how, but now what does it do? So I have 6, it's a 4x4 matrix, skew symmetric. So I have 6 independent one forms specifying a connection on the Lorentzian frame bundle, orthonormal frame bundle. So I have explicitly shown these 6 independent one forms. It means that we need 24 independent functions to fix a linear connection. 6 independent one forms have 24 independent functions. Now, a connection with vanishing torsion is determined by the Maurer-Cartan structure equations. So given a metric G, first let us choose a G orthonormal local covariance coframe, then evaluate its exterior derivatives. So we have DEA. So these are 2 forms. 2 forms have 6 independent components. We have 4 of those. So we have 24 independent components. Thus, the Maurer-Cartan structure equations is nothing but a system of algebraic system of 24 equations for 24 variables. So by a fundamental theorem of algebra, the above Maurer-Cartan equations admit a unique solution for the connection one forms. I show that unique connection by omega hat AB. That's the unique torsion-free metric compatible connection, the Levi-Civita connection. It's determined uniquely by the metric up to a local Lorentz transformation, because this is fixing EA, and the coframe is determined up to a local Lorentz rotation. And then I can look at how the connection transforms under a local Lorentz transformation. Well, that's quite easy. You know how the coframe transforms. So you work out how DEA transforms under a local Lorentz transformation. This is non-zero. It has to be inhomogeneous, and you can show that this inhomogeneous part is exactly this term. Now you can see that this is nothing but an SO13 Gage potential, lambda, omega, lambda inverse, lambda, d lambda inverse, just like a Young-Mills potential. This is just like how a Young-Mills potential transforms in a Gage theory. And the corresponding curvature 2 forms are given by the second set of Cartan structure equations. So if omega is interpreted as a connection, then R is the corresponding curvature 2 form. And then it's a tensorial quantity, just like the Gage field 2 form. And then we can obtain Bianchi identities, just take the exterior derivative of the second structure equations, DRAB. The first term vanishes and the second term is simplified. And we get the Gage Bianchi, second Bianchi identity here, but we have something more. We can take the first Maurer-Cartan structure equations, take its exterior derivative to introduce its compatibility condition. And this gives just R wedged into EB equals 0. So that's the first Bianchi identity, that's the second Bianchi identity. Now, I think now it's becoming apparent how the Yang-Mills gauge theoretic structure and the connection theory of connection on an orthonormal frame bundle are looking similar. There are similarities in the second Bianchi identity in how the gauge potential linear connection and the corresponding curvature is transforming under a local Lorentz transformation with the gauge transformation of A and F. But there is something more in this theory because we identify the gravitational potentials, the Newtonian potentials comes from the metric components. That's the essential physical quantity. In this approach to gravitation, gauge theoretic approach to gravitation, connection one form is a derived quantity. Whereas in the Yang-Mills case, the gauge potential is the essential physical quantity. So that's the basic difference. I'm not going to talk about these following conditions on the connection to be flat. Curvature vanishes. There exists a global coordinate chart. There are holonomic coordinates. There exist inertial frames, etc. I can skip those. I think my time is getting short. Now, an alternative formulation of determining a metric compatible connection, I'm going to talk it very, very shortly about that. We use a type-preserving causal type covariant derivative relative to a vector field X. I denote it by nabla sub X. So this is the covariant derivative relative to a vector field X. It's a type-preserving derivation. So I can, in particular, consider the covariant derivative of a vector field Y relative to another vector field X. That will parallel transport Y along the integral curves of X. So it's a vector field again. So the nabla X of Y is again a vector field. Now, in particular, consider the covariant derivative of a frame vector relative to another frame vector. Nabla of XB relative to XA. It's going to be proportional to it's going to be a vector field. In general, I can expand it. I have two indices AB, covariant, and then I have a summation on the C. These expansion coefficients are called the affine connection coefficients. Now, these affine connection coefficients determine the connection one form completely. And very shortly, very briefly, the relation between the affine connection coefficients and the connection one forms that I introduced before is this one. These are one forms, so I can evaluate its value on a frame vector XA. So it has a 3-index object, and I identify the affine connection coefficients. Watch for the index. Watch for the index locations. That's important because when I lower the index C, it's skew symmetric in C and B. So you have to be lower index C, and then you know that affine connection coefficients are skew symmetric in C and B. But C is in the first location, A is the second location, B is the third location. So you have to be very careful about the index location when you are talking about affine connection coefficients. And in terms of this causal derivative and the Levi-Civita connection in terms of the covariant derivative relative to the Levi-Civita connection, the Maurer-Cartan equations are taking this form. X, Y is the Lie bracket of two vector fields, essentially the commutator of these two vector fields. And the second Saltan structure equations now take the form. It's you differentiate, take the covariant derivative of a vector field twice, you still get a vector field. So this R sub Z of XY is a vector field which is skew symmetric under the exchange of X and Y. Well, you can evaluate a vector field on an arbitrary one form. So take a beta, evaluate this vector field on beta, and you get the Riemann tensor. That's the definition of a Riemann mixed type tensor. It has one upper index, three lower indices, covariant of rank 1, contravariant of rank 1, covariant of rank 3, and then it is skew symmetric in the last two indices, one index up, one index down, and then it's skew symmetric in CD. The first Bianchi identity with the Levi-Civita connection amounts to saying that it's totally skew symmetric in the lower three indices. That's the first Bianchi identity. Now, once I have obtained these orthonormal components of the Riemann tensor, I can talk about the Ricci curvature 2 tensor, which is a second-rank covariant tensor. And in the case of a Levi-Civita connection, it's a symmetric second-rank covariant tensor obtained by contraction. I contract by conversion, I contract the first index with the third index. Some people contract the first index with the fourth index. Anyway, it just means a negative, overall negative sign. So Ricci tensor can be obtained from the Riemann tensor without any other structure. But if you can take the Ricci tensor, if you want to contract it again, you have to raise an index which needs a inverse of a, so you need a non-degenerate metric to do that. So the curvature scalar definition needs the introduction of a non-degenerate metric tensor. You need one more contraction. And there is an important lemma that was observed by Einstein in 1915 first. The Einstein tensor, which is given by this combination of the Ricci tensor and the curvature scalar RAD minus a half R eta AB, is covariantly constant by construction. Its covariant derivative identically vanishes. Now we are making essential use of this fact because Einstein postulates his gravitational field equations in terms of the Einstein tensor, and it's set equal to the energy momentum tensor of a matter distribution in the space-time. It's a second-rank symmetric covariant tensor. Now I'm not going to talk about what these are. I have a minus sign, I have a gravitational coupling constant, Newton's constant, I have C cube appearing downstairs. Why is that so? Why I need a minus sign? Well, these are all physical reasons for it. It's important for interpretation. But the important thing is that this Einstein field equations, the Einstein tensor, comes out by a second-order variational principle from the Einstein-Hilbert action function, which is written as the integral of the Ricci curvature scalar over this invariant volume 4 form. And these constants are not important. If you apply the variational formulation of Noether's theorem, the variation of this action with respect to the metric components give us the source-free Einstein field equations. Now I think I'm running out of time, so I'm not going to talk about the principle of least action. Let me just indicate you this one. Now, the Young-Mills field equations that I have shown you in general, let me go back to that. I have postulated the Young-Mills field equations and used it for electroweak theory, right? Right. I have postulated the Young-Mills field equations, D star F plus A star F minus star F A equals star J. I postulated at this level just by looking at the Bianchi identity and generalizing. That's correct. But I can give you a variational formulation in terms of a Young-Mills functional, action functional. I'm not going to show you how to derive it. I'm just going to state the result that the Young-Mills field equations that I postulated can be obtained by Noether's theorem by a variational principle from an action which is quadratic in the Young-Mills field form. In order to get the source term, I need this minimal coupling of the potential to an isotopic spin current density 1 form. The Young-Mills equations I obtained by infinitesimal variations of this quadratic action. So this also shows the basic difference between the Einstein's Gage theory, Einstein's general relativity theory as formulated as a Gage theory of a connection on a orthonormal frame bundle over space-time with the Young-Mills field equations formulated as on a principle as a linear theory of linear connection on a principal fiber bundle. The actions are Young-Mills action is quadratic in the curvature tensor, whereas the Einstein action is. I think I have to go in the right direction. So Einstein action is linear in the curvature tensor. I cannot write anything like this in the case of Young-Mills theory because I don't have this metric as appearing as a dynamical variable. In the case of Einstein's theory, the true physical degrees of freedom are carried by the components of the metric tensor. So it is possible to write an action and the relativistically invariant action in terms of the curvature scalar, which is linear in the curvatures. And the best we can do in the Young-Mills case is to write an action in terms of which is quadratic in the curvatures. Can I write a quadratic curvature invariant for gravitational fields? Yes, I can do that. But since the metric is the basic physical variable, the corresponding field equation satisfy the components of such a gravitational theory with an action which is quadratic in the Riemann curvature tensor turns out to be fourth order differential equations. The Einstein-Hilbert action gives us second order field equations for the metric components. The Young-Mills action gives second order field equations for the Young-Mills potentials, which is a linear connection. And so the similarities end at this stage. I'm not going to talk about how to construct an energy momentum tensor. So let me just very quickly summarize my point. The main question in this talk was whether the gravitational interactions that act at a distance among all massive objects admit a similar gauge theoretic structure as the Young-Mills gauge field theories. Now, I have explained that the answer is yes in a general sense, but no in some other important physical respects. Now, we have seen how Einstein's dynamical theory of gravitation over the fourth-dimensional space-time manifold, this triplet Mg and the Levi-Civita connection, can be given as a gauge theory of local Lorentz group, SO13. And if you want to couple fermions, spinors, you have to consider the double cover of SO13, spin 13. This is associated with the action on the Clifford algebra over the cotangent bundle of space-time. I'm not going to go into any detail here, but spin 13, the spin group, this particular one is essentially SL2C, and in order to couple fermion fields, spinor fields like electrons, leptons, etc., quarks to gravitational fields, you have to go to the spin cover of the local Lorentz group. So you have to work with SL2C rather than SO13. And essential differences show up in the postulated basic field equations. Gravitational potentials reside in the metric tensor over spacetime, while the Young-Mills gauge potentials are identified as the pullback of linear connections on the principal G bundle over spacetime. Now, will it be possible to incorporate gravity in a unified theory of all fundamental interactions with physics? That's the big questions. Very possibly, this cannot be achieved in a straightforward way. Superstring models, M theory, loop quantum gravity, and all such models are, maybe you have heard about these, are all attempts in this direction. It seems that we have a long and difficult scientific journey ahead of us, and the demonstration of the fact that the local Lorentz gauge structure of gravitation is an early step in this journey. And I think I have just 1 minute. I want to do one final comment here. Now, Einstein's general relativity theory dates from 1915, and it has brought us a total new way of understanding the universe at large by introducing a picture of a dynamical four-dimensional space-time structure. However, general relativity doesn't show up neither in our university curricula nor among lists of subjects with priority. On the other hand, I want you to remember that 3 Nobel Prizes in physics during the last 5 years went to this subject. 2017 Nobel Prize in Physics went to Rainer Weiss, Barry Garish, Kip Thorne for their decisive contributions to the LIGO detector and the observation of gravitational waves. Gravitational waves were predicted by Albert Einstein himself in 1917. It's a very difficult, they are very weak. Their detection is very difficult, extremely expensive, but it was achieved in 2015 at last. So we know today that gravitational waves exist. Kip Thorne is the theoretical physicist in this group. Weiss and Barish are experimental groups, are leaders of the experimental groups. 2 years later, 2019 Nobel Prize in Physics was awarded to James Peebles for his theoretical discoveries in physical cosmology. Well, probably you heard about this Big Bang cosmologies, where the universe starts from an essential space-time curvature singularity at time t equals 0. With a Big Bang, it goes through an inflationary phase, then it makes a phase transition to a Friedmann phase of expansion, and then we have structure formation, and then heavy nuclei formation, etc. So we have a scenario, and James Peebles has contributed to this physical cosmological scenario. And again, Einstein's theory of general relativity is essential for our understanding of a dynamical cosmological view of our space-time. And as 2 years ago, 2020, finally, the Nobel Prize in Physics went to Roger Penrose for the discovery that black hole formation is a robust prediction of the general relativity theory. Kip Thorne and James Peebles are theoretical physicists, but I think most of you will know as Roger Penrose as a mathematician. He's a true mathematical physicist. And I think I want to finish with the last statement that I think we must put an effort to learn this subject of gravitation, general relativity very well, and get ready to make contributions to science of gravity in the long run as mathematicians and as theoretical physicists. Thank you very much.
Thank you very much also, Professor Tekin Dereli. We would like to thank our all sincere gratitude for this exceptionally good talk. Let me ask any comment from the attendees. If you have any comment, you can use the question and answer window.
You can get in touch with me if you are really.
Yes, also, we can kindly recommend for all participants, you can use the email addresses to reach Professor Tekin Dereli for your...
I skipped a lot, so if people are interested to see the details, I can send them the presentation.
Thank you very much, Professor. Again, we would like to express our thanks because we are glad to see you here. You can arrange your busy schedule. So now we can continue.
I stop sharing.
Yes, thank you very much. Now we can continue as we scheduled with the regular session. Now I give my turn to my colleague Uğurcan Eser to moderate new session. Thank you very much.
Good afternoon, everyone. I am Uğurcan Eser. Ladies and gentlemen, I will moderate this session. Now, I kindly invite Professor Haliscan Koyuncuoğlu from İzmir Katip Çelebi University of Turkey to do his presentation. Welcome.
Hello.
Hello.
I think you hear me.
Yes.
Today, I will briefly focus on T lambda periodicity on time scales, and I'm going to provide a generalized Massera theorem according to the provided T lambda periodicity. I will start with the outline of my talk. First, I will briefly introduce you my motivation behind that study. And after that, I will provide you a summary which provides a setup for construction of the Massera type theorems. I'm not going to spend so much time on the time scale essentials. Actually, I will evaluate the given time by introducing the shift operators and T lambda periodic functions based on shift operators. Then I will give the basic theorems, which is originated by Massera. And then there will be 2 or 3 examples just for indicating the conditions which can be checkable. All right. Motivation, I write some sentences for our guests. Periodic solutions of differential and difference equations are extensively studied so far, and by just Googling periodic solutions of differential equations, it's possible to get more than thousands of results. By using conventional periodicity for a function, we just use very elementary definition f of t plus capital T equals to f of t, which holds for a fixed period t as positive number, and of course it holds for all t belonging to domain of the function f. Indeed, I'm using this as conventional periodicity, and of course this definition is valid for translation invariant domains. And of course, in order to define a periodic function, we have to guarantee that the domain of the function is periodic. And by periodicity of the domain, or later we will be considering timescales, we will assume that a domain, a timescale is translation invariant or additively periodic if for the domain we have a positive constant p, so that for any t, t plus minus p should be in the domain. So it's closed under addition it's closed under addition, we can say, for additive periodicity. But we will be considering actually much more general domains. Therefore, of course, there will be so many domains which are not closed under addition, and we have to emphasize that addition is not the only way to step forward or backward on a domain, on a time scale. For example, in literature, we have very famous equations. They are called Q-difference equations or quantum difference equations, and they are not closed under addition. They are not translation invariant. And therefore, shift operators are introduced by Murat Adıvar and Professor Yusuf Raful. And shift operators characterizes how to move on a domain, how to move on a time scale. And therefore, in our definitions, we will take the advantage of shift operators, and we will define T lambda periodic functions with respect to shift operators, and then we will try to provide a relaxed and generalized periodicity definition, and we will call it's going to be T lambda periodicity. And just there is some literature given. Of course, periodicity is generalized and relaxed so far by thousands of researchers, and as the relaxed periodicity, we can refer to almost periodicity and almost automorphic concepts which have been introduced at the beginning of 20th century. And also, I motivated from the given references because this relaxed periodicity is defined on the set of real numbers and on the set of integers as omega c periodicity. Therefore, I will be also trying to unify the existing papers on general domains, so-called timescales. Here is the given definition of omega c periodicity. F of t plus omega is equal to c times f of t, and c is of course non-zero complex, or mostly I will be considering real c, and w is fixed positive constant. And of course, according to particular choices of c, this definition coincides with conventional periodicity, anti-periodicity, or block periodicity. But here addition is used, and of course we can't use this addition on much more general domains because the time scales we are going to consider does not need to be additively periodic or translation invariant. The objective is as follows. I'm not going to read all of them. First of all, I will be considering T lambda periodicity, T lambda delta periodicity, T lambda symmetry, T lambda delta symmetry for time scales by employing shift operators. And then we will establish Massey type theorems according to those definitions. And secondly, we will try to obtain Massera type theorems regarding T lambda periodic solutions of both linear and nonlinear dynamic equations on time scales. And to achieve this objective, Massera type theorems establish a bridge between periodic solutions and bounded solutions. And here we are using a generalized, a relaxed periodicity concept. Therefore, according to this periodicity concept, we define a new boundedness definition, and we will call it lambda boundedness, and we will see the relationship between lambda bounded solutions and T lambda periodic solutions as the second and the main task of this talk. So there are some time scale essentials, but I am not going to spend so much time with those definitions because of time restriction. I have to assume time scale familiarity. By time scale, I mean an arbitrary, non-empty closed subset of real numbers. And in one, we indicate a time scale is additive if there exists a positive p, so that t plus p or t minus p is in the same time scale. Some additive sets are given, R, Z, or the union of closed intervals, they are additive, but the given sets below, they are not translation invariant, they are not additive. So these are tools for time scale calculus: forward jump, backward jump, step size, and the Hilger derivative. Hilger derivative, we can understand it as the generalized derivative. So if sigma is 0, it turns to, if sigma t is t, it turns to usual derivative. If sigma t is t plus 1, then it turns to forward difference, and so on. There are some well-known derivatives given in that table. F prime, if t is chosen as z, we have forward difference. If t is chosen as q to z closure, we have q difference, and so on. Actually, we will require the time scale exponential function. First of all, in order to define time scale exponential function, we have to ensure that our function is regressive. And then we define cylinder transform. And this is what I need, actually, because I'm going to consider a linear initial value problem. And in the sense of time scale exponential function, we invert that solution, and this is the unique solution to the initial value problem. All right. Now I have to start talking about shift operators, and this definition is taken from the original work of Adevar. I'm not going to read all of those steps. It can be found in Math Slovakia paper of Murat Adevar. It just describes the shift operators, and it explains how we define, how we characterize the forward motion and backward motion on a time scale. And delta plus will stand for the forward shift, delta minus will stand for backward shift. And with respect to those shift operators, there are some specific examples are given. If t is r, we have usual addition. For z, we have usual addition. But if you choose a quantum domain or q difference domain, the shift operators changed. For forward shift, we use multiplication. Backward shift, we use division. And for another time scale, n to 1/2, we characterize different shift operators. Then, in order to define a periodicity concept on a time scale, first of all, we have to ensure that our time scale is periodic, and this is the periodicity in shifts. I mean, forward shift and backward shift must be in the time scale. Just we replaced plus minus. Instead, we put forward shift, backward shift, and this definition is rewritten. And accordingly, periodic functions are changed. This is usual periodicity according to shift operators. Plus minus replaced with forward delta, backward delta. And also, especially this is commonly used in Q-difference equations, one more periodicity definition is proposed. We call this as delta periodicity. Now, we used these definitions to invert some results in qualitative theory of dynamic equations. For instance, here, if you pick P is delta periodic function in shifts, then you have that period, you have that property which describes periodicity of the exponential term. Now I have to start what I have done. First of all, I'm using that notation for K times composition of shift operators. And the setup I mean is here. I have to define the set PT0. And also we use MT as the maximum of this set. We have the fixed initial point T0 by using forward shifts K times. We are trying to reach T, and this number is called MT. And any member of time scale can be decomposed in this form. If T belongs to PT0, TR means 0. You reach your original point by using the period of time scale. Otherwise, TR is formulated in this form. Now, T lambda periodic function is given as follows. We have forward and backward shift operator by the period T, and we have lambda 2 plus minus 1 f of T. This is actually very parallel to the definition constructed on additively periodic timescales, just we are using the advantage of shift operator. There is another result. If you have a T lambda periodic function in shifts, then we can represent f in this piecewise defined way. If your point T is belonging to set PT0, you have this representation. Otherwise, it is represented by lambda to MT and f of TR. TR can be understood as remainder. An example here, minus 2 to logarithm of QT. This is Q square for periodic shifts. And here is the very simple algebra, which indicates our function is belonging to that class. All right. Also, another function is given on the set of real line, but specific shift operators are used. And
sorry, Professor Koyuncuoğlu,
yeah.
Can you summarize your presentation, please?
All right.
You have about a couple of minutes.
All right. Thank you. Now we used that periodic definitions, and then first we consider this linear dynamic equation, and then we got the following definition. First of all, we have lambda boundedness definition, and we say a function x is lambda bounded if this relation holds for a fixed lambda. And then by Brouwer's fixed point theorem, we propose the following result. The linear dynamic equation has T lambda periodic solution in shifts if and only if it has lambda bounded solution. Just one remark I have to say, here we had to use P's usual periodic function. We can't choose the function A here or P whatever. It must be delta periodic function in shifts. We can't use relaxed periodic definition on A because I have to use this periodicity of the exponential function. This is one weak part of this study. Also, we focused on the nonlinear dynamic equation, the functional nonlinear dynamic equation, and we got a similar result. The T lambda symmetric equation has lambda bounded solution if and only if it has T lambda periodic solution. Okay, just I'm going to recall what do I mean by T lambda symmetry. This is what I mean by T lambda symmetry for functions of two variables. Just I need 1 or 2 more minutes for concluding my presentation. For checkability of conditions, I consider some examples. First, I picked T equals to R, and I expressed my solution in this form. And in the specific form of A and F, A is delta periodic, F is T lambda delta periodic in shifts. I have lambda bounded solution. Therefore, our solution must be T lambda periodic according to generalized Massey theorem. And also here I considered a nonlinear dynamic equation. And I checked the conditions, all of them are satisfied. We have T lambda symmetry there. And after that, we obtain T lambda periodic solution of the nonlinear dynamic equation. And according to the Massey theorem, we deduced that this is 4-bounded. I'm so sorry, maybe I exceeded my time. These are my references. Actually, I really inspired by the Bonner and Mesquita's paper. This is a very nice paper. And these are my other references. I would like to thank you for your time and interest on my study. Thank you.
Thank you, Professor. Dear attendees, do you have any question or comments? You can close your screen sharing, dear Professor.
Thank you so much.
Thank you. I think there is no more question or comments. Okay, thank you again, Professor. Yes, dear attendees, our next presentation will be presented by Professor Mancho Mane from Plovdiv, Bulgaria. I would like to invite Professor Mancho Mane.
Thank you. Do you hear me?
Yes, yes.
And can you see my presentation?
Yes.
Thank you again. First of all, I want to apologize for the confusion over time. I did not know that Turkey was no longer switching to a winter time shift.
Okay.
And now I want to thank the organizers for giving me this opportunity. The title of my talk is Ricci like solitons with arbitrary potential and gradient almost Ricci-like solitons on Sasaki-like almost contact bimetric manifold. I'm from University of Plovdiv, Bulgaria. Ricci soliton is a special self-similar soliton on the Hamilton's Ricci flow, and it is a natural generalization of the notion of the Einstein metric. According to Hamilton, a pseudo Riemannian manifold admits a Ricci soliton if the metric its Ricci tensor and the lead derivative of the metric along the vector field, which is called the potential, are linear dependent. If the coefficient of this dependence a function, then the soliton is called an almost Ricci soliton. If the function exists, so they are, sorry. So that the potential is its gradient, then the almost Ricci soliton is called the gradient almost Ricci soliton. The topic became more popular after Perelman's proof of the Poincare conjecture, following Hamilton's program to use the Ricci floor. Ricci soliton have been explored by a number of authors. So you can see under the line some references in the relation. The presence of the structure 1,4 meter on manifolds with almost contact or almost para-contact structures motivates the need to introduce the so-called ether Ricci solitons. They are introduced in paper number 13 on Cho and Kimura in my presentation. Later, it has been studied on almost contact and almost para-contact manifolds by many authors. For example, Blaga, Prakasha, Dimani, and many others. For eta Ricci solitons, you can see also in references. Our global goal is to study the differential geometry of almost contact bimetric manifolds is investigated since 1993 with Ganchev, Mikula Gribachev, and myself. In paper number 27 of my recent papers, it is made a further generalization of the notion of a Ricci soliton and an eta Ricci soliton, the so-called Ricci-like soliton, using both bimetrics and eta times eta. There we have explored this object with potential Derive vector field on some important kinds of manifolds under consideration, which are Einstein-like, Sasaki-like, and having a torse-forming Riemann vector field. In next my paper, we continue to study Ricci-like solitons whose potential is the Riemann vector field on pointwise collinear tweets. In the present paper, our goal is to investigate Ricci-like solitons with arbitrary potential and gradient almost Ricci solitons on almost contact bimetric of Sasaki-like type. Some preliminaries in this relation. A differential manifold M of dimension 2n plus 1 with an almost contact structure phi psi eta and bimetric G is called almost contact bimetric manifold if identity number 1 are satisfied. The associated metric tilde G of G is defined as you see here. The manifold with G tilde, it's also an almost contact bimetric manifold. A classification of these manifolds, which contains 11 basic classes, calligraphic 1 to 11, is given in the work of Ganchev, Mikula Gribachev, 1993. It is made with respect to the tensor F in equality number 2. In our paper, joint paper with Stefan Ivanov and Christo Manev in 2016, it is defined the class of Sasaki-like spaces in these manifolds by the condition its complex cone to be a Keller-Norden manifold. Then we obtain such expression of the covariant derivative of phi. Obviously, Sasaki-like manifolds form a subclass of the fourth class according to the used classification. A manifold of this type is said to be Einstein-like if its Ricci tensor satisfies the equality number 4 for some triple of constant ABC. In particular, you obtain eta Einstein manifold and Einstein manifold respectively. If ABC are functions, then the manifold is called almost and Einstein-like and so on. Then the scalar curvature tau and tilde tau on the Einstein-like manifold have the form in 5. For a Sasaki-like manifold with dimension 2n plus 1 and a scalar curvature tau regarding G, which is Einstein-like with a triple of constant ABC, the following equalities are given in my paper 27, number 6 equalities. And then for tilde tau, according to G tau, according to tilde G, on an Einstein-like Sasaki-like manifold, we obtain this equality. Therefore, we have expression for each tensor as in 8. Proposition 1.1. Let the manifold is Sasaki-like if it is almost Einstein-like with functions a, b, c. Then the scalar curvature tau and tilde tau are constants as in 9, and manifold is eta Einstein with constants a, b, c respectively, as you see here, according to tau. In the second section, I talk about Ricci-like solitons with potential vector field on Sasaki-like manifolds. We say that the manifold admits a Ricci-like soliton with potential vector field V if the following condition for derivative L is satisfied for a triple of constants lambda mu nu. This equality number 10. And in particular cases, we define an eta Ricci soliton or Ricci soliton. If lambda mu nu are functions, then the soliton is called almost its own, respectively. If manifold is Sasaki-like, we have expression of the Lie derivative of G according to Xi in this form. That means we have, with respect to the tilde G and theta, this form, equality. Then we have the following form for the Ricci tensor with respect to G, G tilde, and theta times theta. And I recall Theorem 2.2. Let the manifold be Sasaki-like, and we have 6 constants a, b, c, lambda, mu, nu, such that it's satisfied the equalities in 12. Then the manifold admits a Ricci-like soliton with potential Xi, and constants lambda, mu, nu are such their sums are minus 2n. If and only if this manifold is Einstein-like with constant ABC, where the sum of ABC is 2n. In particular, we obtain necessary and sufficient condition for eta Ricci solitons, shrinking Ricci soliton, and Einstein's manifold, as you see here. Example first here. Actually, this is example 2 of the paper number 20. In my list, it is given a Lie group G of dimension 5 with a base of left invariant vector fields from E0 to E4, and the corresponding algebra is satisfied as follows here by these commutators. P and Q are reals. After that, G is equipped with an almost contact B-metric structure, as you see here in this equalities. And it is verified that the constructed manifold is Sasaki-like. In the paper number 27 in my list, it is proved that this manifold, this constructed manifold, is eta Einstein with constants ABC 004. Therefore, it is clear that the scalar curvatures with respect to both B-metrics are 4, equals to 4. It is also found there that this manifold admits a Ricci-like soliton with potential Xi and constants lambda mu nu of this form. Therefore, this example is in unison with Theorem 2.2, the third case for 0a. The third section is about Ricci-like soliton with arbitrary potential on Sasaki-like manifold. Let M be Sasaki-like and admit Ricci-like soliton with arbitrary potential V. Then theorem 3.3, we have the following identities here. And proposition 4 is about here. We obtain the constant for the scalar curvature. Now let M be Einstein-like and Sasaki-like. And in theorem 5, if it admits a Ricci-like soliton with the potential V, arbitrary potential V, then the Ricci-like tensor is rho is 2n eta times theta, and the scalar curvatures are exactly 2n. And one corollary about eta Einstein in this case. Let us recall this definition for phi holomorphic plane. It is invariant with respect to phi, and psi section goes through psi. Theorem 7 says that for 3 dimensions Sasaki-like manifold, if it admits a Ricci-like soliton with potential V, then the sectional curvatures of its phi holomorphic sections are -1. And the section curvatures for its psi sections are equal to 1. And the second example, it's about R3, where the metric is defined as in 18, and the structured as phi psi eta. And then we determined the base E1, E2, E3, and it is orthonormal 5 bases in the tangent space. And immediately we obtain the commutators as in 19. Then according to example 1, the solvable Lie group of dimension 3 with basis such was obtained, defined.
Sorry, dear professor. Can you summarize your last words, please?
Okay. And here we construct potential, as you see here, explicitly with such functions. And we here obtain results in accordance with theorems 3, proposition 4, and theorem 5. And in the final section, I talk about gradient soliton of this type. And in the last example, I add it with the definition of the function, which gradient is the potential of the soliton, and obtain here the constants are explained, are expressed as you see here in accordance with theorem 4.8. Thank you for your attention.
Thank you so much, dear professor. Dear attendees, is there any question or comments? Please, can you, if you can. You can close your screen sharing, professor.
Okay.
Thank you. I think there is no question or comments. Thank you again, professor. And dear attendees, our next presentation will be presented by Debashish Haldar from Odisha, India. The title of presentation is Multiframelet and Multiframelet Set on QP. Welcome, professor. Can you hear me?
Yeah.
Can you hear me?
Yes, sir. Am I audible?
Your voice is too much low. Can you increase your voice, please?
Now, am I audible?
Okay, okay. Screen, can you full screen? Okay, thank you. You're welcome.
Okay.
You have 15 minutes and 5 minutes question section.
Okay. Okay. This is Devashish Haldar, PhD scholar of NIT Rourkela, India, and I am going to present my talk, multi-framelet and multi-framelet set on QP. So these are the outlines. And the first, I will going to discuss about the what is periodic number and the properties of the set of this periodic number QP and multi-framelet defined on this QP, multi-framelet set and the references. First is for a prime number P, a field QP of periodic number is defined as the completion of the field of the resonance number Q with respect to the non-Archimedean periodic norm. This periodic norm is defined as it is a 0 when x is equals to 0, and it is p to the power minus gamma when x is equals to p to the power gamma times m by n, where this p doesn't divide m and n, and this gamma m n are the integers. So this norm satisfies the strong triangle inequality is this, and that is why this norm is said to be a non-Archimedean norm. So the canonical form of any the canonical form of any this periodic number x is the summation of xj p to the power j, where this j is from the gamma to infinity, and where this gamma is can be any integer, and these xj's are from the 0 to p minus 1, and the leading coefficient x gamma is not equals to 0. The fractional part of this x is defined as the summation of this xj p to the power j, where this j is from the gamma to minus 1. So the fractional part of this x is equals to 0 if and only the gamma is a non-negative, and the fractional part of 0 is 0. The set of periodic integers zp is defined as the set of all periodic number such that whose fractional part is the 0, and set of all the fractionals number ip is defined as the set of all periodic number x such that whose fractional part is the x, the number itself. A ball, a center at C with radius p to the power gamma is defined as this b gamma c, and is denoted as b gamma c and defined as the set of all periodic number x such that whose norm of x minus c is less equals to p to the power gamma. The set JPM is defined as the set of all the numbers. This s minus m p to the power minus m to the sum s minus 1 p to the power minus 1, and where these sj's are the this 0 to p minus 1, and the leading coefficient is minus j is not equals to 0. So the order of this set can be is the p minus 1 into p to the power m minus 1. The inner product defined on this L2QP is as the integration of fx complex conjugate of gx dx, and the measure is given here with respect to the Haar measure. The additive character, the chi p on the field this QP is defined as the x goes to e to the power 2 pi I, the fractional part of x. The Fourier transform of f is defined as the integration of this chi p x fx dx, and the inverse Fourier transform of f is defined as the integration of chi p minus x fj dj. And there is a wonderful relation between the Fourier transform, between the function and its Fourier transform. It says that Parseval theorem. It says that inner product of f and g is same as the inner product of Fourier transform of f and g. So now the properties of the QP, the field of periodic number. So we are now going to present some of the properties of this on this set. The set of natural number n is dense in the set of all periodic number, is periodic integer, and set of all rational number is dense in set of all periodic number. This QP is a fraction field of ZP. This QP is locally compact, totally disconnected, and has no isolated points. Every ball BJC is both open and compact. Every point of the ball is the center of the ball. Any two balls in QP are either nested, means one is completely inside the other, or the disjoint. This QP with respect to addition and multiplication is a field with characteristic 0, and the IP shifts of the ZP for the IP shifts of a ZP will form a partition of this QP. Any set K is compact if and only if it is closed and bounded. Any number, any periodic integer x is invertible if it's, the periodic norm is equals to 1. Any series UN is convergent if its sequence goes to 0. And if the norm of x is less equals to norm of y, then this norm of x plus y is equals to norm of y. So any triangle is isosceles. Now the multiframelet of this QP. So for this these L many functions, f1 up to FFL of this L2 QP, and this factor L is defined as this finite set 1 2 up to L. This affine system FLJA, where this FLJ is defined as the p to the power j by 2 FL p to the power minus j times x minus a, and this j is in integer, a is in the periodic fractional number, and the L is the factor L. This affine system is said to be a multiframelet of order L if there exist two positive constant a, b such that this condition, this equation 1 will satisfy. So this system, this affine system is said to be a Baselet if only this second inequality of this equation 1 will satisfy. And this multiframelet is said to be a tight multiframelet if we can choose a equals to b, and it is said to be a normalized tight multiframelet if we can choose a equals to b equals to 1. Here this a is said to be the lower multiframelet bound, and b is said to be the upper multiframelet bound. So here are two examples of this multiframelet. The first one is the equation 2 is of multiframelet. This will produce a multiframelet of order p minus 1, and the second one will produce a multiframelet of order p minus 1 times p to the power m minus 1. So now we are going to present some of the properties of this multiframelet. So every multiframelet is complete in L2 QP. Means it's the closure of the span of these multiframelets will the L2 QP. Each of the element of this multiframelet with upper bound b are the bounded above by the root of the b, the square root of b. If this affine system, this FJ L is a baselect for a dense subset, then it is a baselect for the whole space L to QP. And this this multiframelet, if it is a multiframelet for a dense subset of this L to QP, then it is a multiframelet for a L to QP. Means the to checking a baselect or a multiframelet is enough to check on the dense subset. The multiframelet sequence, a sequence this FJL is said to be a multiframelet sequence if it is a multiframelet for the closure of the span of this affine system. So every multiframelet is a multiframelet sequence, and every multiframelet sequence is a baselect. The FJL is a multiframelet sequence with bound, let's say AB, and if U is the unitary operator on this L to QP, then the unitary operator U applied on this the affine system will give you a multiframelet sequence with the same bound. And here this bound AB means the A is the it is understood that A is the lower bound and B is the upper bound. The multiframelet operator S is defined as by this the sum. So this multiframelet operator S is bounded, a linear, self-adjoint, and the bijective operator. So if this affine system is a multiframelet with a bound AB, then the inverse of this multiframelet operator applied on this affine system is a multiframelet with bound the B inverse A inverse. The next one is the important result of this multiframelet. It is a multiframelet decomposition theorem. Let this affine system is a multiframelet for this L to QP with the multiframelet operator S. Then any element G can be written as this like this or by this, where the sum converges unconditionally. Next, we are going to present a multiframelet set. A measurable set, this factor F, is said to be a multiframelet set of order L if this factorial can be written as the union of this FL, where the Fourier transform of each of these FL is the characteristic function of capital FL, and this affine system will form a multiframelet for L to QP. And this one is an example of the multiframelet set, and this is a multiframelet set of order P-1. And
dear Professor Halder, you have about 5 minutes.
Okay. And here is the example of this the normalized type multiframelet set. The next is let this affine system is a multiframelet for L to QP with the upper bound B, and the Fourier transform of this FL is characteristic function of this capital FL. Then the measure of this if of this FL is less equals to B. And here is it is if this JL is a normalized type multiframelet, then these two conditions will be held. And let this be a system such that the fractional transform of this and the Fourier transform of this, then this the union of this in FL is a multiframelet set of bound AB if and only that this condition will hold. And the one is the similar kind of result. The semi-orthogonal multiframelet, if a multiframelet is said to be a semi-orthogonal multiframelet, if the closure of the span is the perpendicular with the this span, where this J and K are not equals to, and they are not equal. So here is a theorem on this semi-orthogonal multifamily. If this is a system such that the union is a disjoint the measurable set, and if this is a semi-orthogonal multifamily, this affine system, then means this form a measurable partition, and then and it will satisfy this one means this relation. So these are the some important references. Thank you.
Professor Haldar, we thank you for your presentation. Dear attendees, do you have any question or comments for Professor Haldar? I think no more question or comments. Thank you again, Professor Haldar.
Okay, thank you.
You can close your screen sharing. Thank you. Dear attendees, our next presentation will be presented by Ali Başan from Zonguldak Bülent Ecevit University from Turkey. The title of presentation is Numerical Computation of the Nonlinear Equal with Wave Equation arising is a nonlinear media. Welcome.
Thank you very much, Mr. Eser.
Thank you. Can you share your screen, dear Professor?
Okay. Is it okay?
Yes, yes.
Thank you very much. In this presentation, we will look at numerical computation of nonlinear equal with wave equation, in short, EV equation. In this study, we use two effective methods. One of them is a differential quadrature method, and the second one is finite difference method. With these numerical approach methods, we used one of the effective linearization technique, namely Riemann and Graves implemented. Three examples are investigated for the checking the accuracy of the new method and their error norms, invariance, relative chains of invariance, and rates of the convergence are also investigated. You will see the EV equation given at equation 1. This equation displays equilibrium between the dispersive and nonlinear effects. In recent years, many studies have been published for exact solutions of EV equation. For example, expanded function method, His expansion function method, extend simple equation method, modified extended tangent hyperbolic expansion method. Beside the exact solutions, many researchers investigated numerical solutions of EV equation by using various methods and techniques such as Galerkin method, collocation method, R-wavelet method, least squares method, federal Galerkin method, radial base function method, finite difference method, linearized increased finite difference method, lumped Galerkin method, fully implicit finite difference method, and multi-quadratic quasi-interpolation method. In this study, we use two different numerical methods together to obtain the high accuracy solutions. One of them is BQM, firstly suggested by the Bellman et al. For the effective solutions of the differential equations by using fewer number of the mesh points. Let us look at the space discretization. Bellman et al. Inspired from the integral quadrature to approach the derivative value of any smooth function at the mesh points in the solution domain by using all of the functional values at the mesh points. In this study, we used quartic B-splines as the base functions. By using the quartic B-splines, 3 n plus 6 unknowns and n plus 3 equations is obtained. To create a unique solution, we use derivative of equation 3 for 3 B-splines for solvable equation system. After that, 3 unknowns are vanished and the equation system is solvable. Here you see for the first grid point coefficient, Whiting coefficients and unknowns and other vector. For all of the mesh points, this system is obtained and it is used at the solution process. Now you will see the time discretization part. Equation 1 is implemented by using the Craig-Nicholson technique given at the 7th equation, and it arranged to vanish the nonlinear terms. We used the Rubin and Graves technique given at the 42 references. After that, we defined some terms for simplified the equation system given at the 10. And the matrix system is given at 12, obtained. By using the boundary conditions to the equation 12 and elimination of first and last equations, we obtained 13. These systems is solved by Gauss elimination method. Numerical experiments are checked by error norms, invariants, chains of invariants during simulations, and rate of the convergence. First of the our example is single solitary wave, given the analytical solution at the 17. Here you see the velocity is given by the c, and 3c is the amplitude of the wave. By increasing of the amplitude, the velocity of the wave is increased also. We use 4 different value of the c given by 1, 0.1, 0.01, and 0.03. Let us look at the numerical results. Here you see very fewer mesh points used in present approach, 151, and the earlier studies are used many mesh points than us. Our error norms is very small than early ones, and invariants also almost constant C. For the rate of the convergence, by increasing of the mesh points from the 51 to 151, error norms is decreased respectively, as you see, and the rate of the convergence are given in this table also for both of the error norms. By decreasing of the velocity to the 0.1, as you see again, the mesh point is very small number, 170. In the earlier ones, 1000 is given. Sorry. The error norms very small than earlier ones. At the time 80 is given, and the invariance values are almost constant in this study. Here you see the increasing of the mesh points, and by increasing of the mesh points, the error norms at the time 80 is decreased respectively for both of the error norms that you see. In table 5, you see the numerical results by using the smaller velocity 0.003 or error norms is very small than earlier ones. This approach seen very successful in the literature, and invariants are almost constant. These comparisons are give us that our approach has combined two advantages of the methods. One of them, differential quadratic method, and the second one, finite difference method. Also, the linearization technique, Rubin and Graves technique, is maybe given. In table 6, by the increasing of the mesh points from 51 to 161, the error norms decreased respectively, and the last implementation of the single solitary wave for very small velocity 0.01. As you see in table 7, error norms is very small than earlier ones. Let us look at the second example, two solitary waves. As you see the different velocity values of the two waves, and by using different velocities, their position will be used at a different location. First of them is 10, and second one is 25. The first one is have greater amplitude, and second one is smaller amplitude. The greater amplitude have high velocity, so the faster one will catch the smaller one and collapse after that and separate it and as the smaller one. You will see the simulations graphs also. Let us look at the numerical results. As you see here, we must say that the exact solutions of the two solitary waves and three solitary waves is not existing in the literature, so we cannot obtain the error norms for this example. Only we calculated the invariance of the two solitary waves. As you see, the analytical values of the invariance given here, and our numerical results are almost near to the analytical one. If compared with earlier studies given by 28 and 29, here you will see the smaller, very fewer measure points than earlier ones, and better results than earlier studies. Let us look at the three solitary waves. Here you see for this example, three different velocities we used. and three waves are located at the different positions given at the 10, 25, and 35. Numerical results are given in the table 10 here, or invariant values are almost constant, which is better than earlier ones given at the reference 15 and 14, as you see. Let us look at the simulation of the waves. Here you see the velocity is 1 and decreased respectively given here. By the decreasing of the velocity, the position of the waves will be smaller. The error norms are at the right side of the page. You see, all error norms is very small, and 0 at the left and right boundaries. For the simulations of the two solitary waves, here you see the greater amplitude and smaller one. By the simulations run, the faster one catch the smaller one, and after that it's separated, and at the time 30 you will see the change of the positions. Here you see the three-dimensional graphs of the simulation. For the simulation of three solitary waves, you will see the three waves at the beginning of the initial times at time 0. By the time increased, faster one catch the other ones and separated by the time at time 15. You will see the three-dimensional graph of these solitary waves. As a result, we may say the conclusion of this study. We use two efficient methods together for better results, and three well-known test problems are solved, and all of the results given with details. As you see by the comparison of the earlier ones, or numerical results are better than earlier ones, obviously. At the end of the presentation, you will see the references of the study. Yes, thank you very much for your attention.
Thank you, Professor Besham. Dear attendees, is there any question or comments? I think there is no more question or comment. Thank you again, sir. Thank you, Professor Besham.
Thank you very much, Mr. Esser.
Dear attendees, our next presentation will be presented by Professor Anabela Silva from Aveiro, Portugal. I would like to invite Professor Silva. Welcome.
Welcome. So thank you for the opportunity to present in this webinar. My work is about fractional boundary value problem, a particular class of fractional boundary value problem. And this is a joint work with Professor Luís Castro, also from Portugal. Our motivation is on fractional calculus and Euler-Rassier stability. So we studied stability, in particular Euler-Mears and Euler-Rassiers. We know that the fractional calculus was used in many areas of science and engineering, since many systems can be described by using fractional differential equations, and in particular with boundary conditions. And on the other side, these problems have a particular problem, which is find the Z solution. And because of that, the Euler-Mears and Euler-Mears are so important. This stability permits us to obtain a very close solution, a very close approximation to the solution. And it is important because the Z solution in most of the times are difficult to reach. So I will present some basic definitions to this work. I will present the fractional boundary value problem that we studied. I will present the solution, the existence of the solution. The principal technique that we use in this work is the Van Eyck contraction principle, which is used in operator theory, very used in operator theory. And I will finish with the study of uniqueness and Euler-Mears and Euler-Mears stability. So the operators that we are using are the Riemann-Liouville fractional integral operator, which is defined by this way. Here we have the gamma function. The interval is defined between 0 and infinity. Alpha is the order of the integration. And we use the Caputo fractional derivative of order alpha greater than 0, which is defined by this integral. Gamma is again the gamma function. N is the integer immediately greater than alpha. So alpha is between n minus 1 and n. And here we have the derivative, the usual derivative of n over t minus s elevated to alpha minus n plus 1. With these derivatives, of course, this derivative when n is equal to alpha, we have the usual derivative. So the problem that we study is a problem that we can find in this paper of 2011 of Zhao, Shai, and G, where they studied a problem like that. Here we have the Caputo derivative of order alpha. In particular, the alpha that we consider in this work is between 1 and 2. Lambda is a positive parameter. Xi and eta that appears in there are numbers, are constants between 0 and 1. Beta that appears here, in here, and gamma that appears in here are constants between also 0 and 1. We have this particular thing that is the Xi is less or equal than eta. The function f is a continuous and non-decreasing function for each t between 0 and 1. T is between 0 and 1 is the interval that we consider. X that appears in here is a positive function. Moreover, to obtain the solution, the authors Zhao, Shai, and G consider this particular condition, which is important along all the work, which is the relation between these constants beta, gamma, and eta and Xi, which should be less than alpha minus 1, which is the order of the integration, times 1 minus beta Xi. This in particular, it appears when we are obtaining the solution. So in the rest of the work, we will consider always this condition. Zhao et al. Proved in 2011 that the solution of this problem in here don't have the lambda that we use in our work. They proved that for that problem without that lambda, the solution is given by that expression where we have the Riemann-Liouville integral in here of this function f in t, xi, 1 and eta. And we have this constant delta, and of course this is not a constant, there is a t in these expressions. We usually in the fractional boundary value problems, we rewrite the solution in terms of the green function. So we can rewrite the solution in terms of the green function, which is a function like that. Of course, we will not explore that because it is too big to explore in here. So the integral between 0 and 1 of the green function here defined times the function f, this continuous and non-decreasing function. When we consider the problem with that lambda, the solution will be given by that expression where the green function is given as in the previous lemma. The authors Zhao et al. also studied that the green function satisfies some properties. So we consider again this property, this condition along all the work. The green function satisfies in particular this first one property, which is the most important for our work. The green function is positive and less or equal than a constant m, and m defined like as this expression in here, times 1 minus s elevated to alpha minus 2, when t and s belongs to 0, 1. So in what follows, we will use this condition 1, not the second one. As about the Banach contraction principle, the Banach contraction principle said that if we have a generalized complete metric space, if we consider a mapping that is strictly contractive, this means that when we compute the metric, I will call that the distance, but this is a metric. So when we compute the distance between tx and ty, this is less or equal than a constant, which is a constant between 0 and 1, less than 1, not equal than 1, times the distance between x and y. When this happens, we say that the operator t is strictly contractive. And if the operator is strictly contractive, we have these properties, the mapping t as a unit fixed point, and we have the following inequalities. In particular, since we are dealing with continuous functions, we will not use the derivatives, we will use the last one property in a theorem that we proved. We use the Banach space of continuous functions from I in our case is 0, 1, with finite norm defined by the supremum of the absolute value of x. So this is a Banach metric space, and we will use the usual metric in Banach metric space. When you talk about Euler-Meyer stability, we talk about the following definition. The problem that we are studying is Euler-Meyer stable if there exists a constant k greater than 0, such that for each epsilon and for each solution, each solution epsilon that satisfies this inequality. I remember that the problem said is very similar than that, but we have in here equal, not the absolute value, and have in here equal to 0. So when we are talking about Euler-Meyer stability, we consider a solution of the inequality, not equality. In here we have the inequality and absolute values. So if this epsilon satisfies this inequality with the initial conditions, there exists a solution, an exact solution of the problem, such that the distance between x and y is less or equal than k epsilon. So if we are considering the solution epsilon satisfying that, we can say that there exists a function g in this space, which depends on epsilon, such that the modulus of this g is less or equal than epsilon, and g is defined precisely by this way. So g is the expression that appears in the modulus. The initial conditions are again satisfied. And we use this in particular to study the stability. So this is the problem that we are studying. This is the m that we have defined before. We will suppose always this condition, as I said, and we obtain this theorem. F is a continuous and non-decreasing function such that f satisfies the Lipschitz condition, where this L is greater than 0, and this function f as a supremum that we call n. This is a finite supremum. Then the fractional boundary value problem is Euler-Meyer stable if we assume that the L that appears in here is less than alpha minus 1 over lambda m, the m defined in this way and lambda that appears in the problem. To prove that, so we consider the solution that I show you at the beginning of this presentation. This is the solution of the problem, the general formula of the solution of the problem. And we consider an operator T defined as a continuous operator from 0, 1 to R plus, and defined by this way. And we transform our problem into a fixed point problem. So the eventual fixed points of this operator T will be the solutions of the problem. And if we prove that the fixed point is unique, then we have a unique solution. It's because of that we applied Banach contraction principle. With this Banach contraction principle, we will show that T as a unique fixed point. This is the idea of the proof. To do that, we first prove that T maps C01 R plus into itself. To prove this, we consider this supremum of the function f. We choose an R which is greater than that. Since alpha is not equal to 1, this is defined. And we consider the balls such that the norm of x is less or equal than at R. And now we compute the modulus of this Tx. We use the measuration that the measuration that we know for the function, for the green function. We use that in here. We use the fact that f has a supremum n, and we obtain that this is less or equal than R. So we prove that TBR is contained in BRs, since we have the continuity of function f and green function, we also have that Tx is continuous. On the other hand, we have to prove that T is strictly contractive. To prove that, we compute the distance between Ty and Tx, and we obtain, and we can compute that. We use again these inequalities, and now we use the maximum of this green function that we know it is in here, and we use the Lipschitz condition to the function f that is in here. We know conditions. We are imposing a condition to this L, and imposing this condition, we obtain that the constant in here is less than 1. If it is less than 1, T is a contraction. And so we conclude that the T as a unique fixed point, which is the unique solution of the problem. Now, we have a unique solution, and we will prove the stability. To prove the stability, we consider the function g as I defined it before, which comes from this inequality. This function g is, the modulus of this function g is less than epsilon. We compute, so epsilon can be written in this way. If we assume this g, we can obtain this solution. And now computing the distance between x and y, we obtain these inequalities. We will use again the supremum of the green function, and also we use the Lipschitz condition on f, which appears in here. When we obtain this expression, we have in here the modulus of x minus y, and we have again the modulus of x minus y in the integral. So to go over this problem, we use a technique, a known technique, which is the Grunwald's lemma. The Grunwald's lemma says precisely that we have epsilon less or equal than a k, the integral of h times epsilon, where the epsilon and h are non-negative functions. Then we can measure this epsilon by this way using this exponential. So we use the same technique, and we prove that x minus y is less or equal than this exponential, and we have precisely epsilon times another constant. So we conclude that the fractional boundary value problem is Euler-Meyer stable. We also proved Euler-Meyer's Rassier stability. Euler-Meyer Rassier stability is very similar, but in here we use a function from 0, 1 to R plus. We use another constant k, And the difference in here, the difference between Euler-Mir-Racias and Euler-Mir's stability is that this expression in here is less or equal than epsilon times this function f, this positive function. And also, assuming that those conditions, we obtain at the end that the distance between y and x is less or equal than a constant times epsilon times the function. So the proof is a little different because when we consider the function in here, we have some other difficulties. We consider again the same as in the previous one. We consider again a new function h, a continuous function, which modulus is less or equal than epsilon phi, since h is defined precisely by the expression that are in years inside the modulus. The initial conditions are again the same. For this case, we obtain that assuming that initial condition, considering the function f, which should have a finite supremum, we assume again the Lipschitz condition, and the fractional boundary value problem will be Euler-Mir-Racias stable with respect to this function phi. So to prove that, we consider again the operator t as a unique fixed point. The formula to prove that is similar, is equal to the last one, so I will not show it again. And now we consider an epsilon, which be the solution of this inequality. We consider again this expression, we consider this h, where this h is less or equal than less than epsilon phi t. It means that we can rewrite epsilon in this way. We fix the notation M1 and M2, M3, which is the constant that appears in the solution when we write the solution in terms of the Riemann-Liouville integral. And we calculate the distance between y and ty. We obtain that expression using, we impose the conditions that M1, M2, and M3 are positive. Of course, they are positive. The K1, K2, and K3 are positive, and we impose that these M1, M2, and 3 have a finite modulus. And in this case, calculating this y and t minus y, we obtain precisely this inequality, and thus we obtain that y minus ty is less or equal than k epsilon phi. We use the Banach contraction principle, which says that the distance between y and x, y and the exact solution, is less or equal than 1 over 1 minus L. L is Lipschitz condition, times k times epsilon times phi. And so we obtain, since this L is defined using the L that we have obtained before, we obtain that this is less than this constant, and we conclude that the fractional boundary value problem is Euler-Mir-Racias stable. So this is four of the references that we used. In particular, the papers where the paper and where the problem is presented, and some of the recent proofs in the uniqueness of fractional boundary value problems. So this is all. Thank you very much for your attention.
Thank you, Professor Silva. Is there any question or comment, dear attendees? Okay, I think there's no question. Thank you again, Professor Silva. Dear attendees, next session will be started by my colleague Figen Tekilmutlu at 1325. Thank you for all.
Good afternoon, everyone. Welcome to this session. I am Figen Takılmutlu. Now, I kindly invite Professor Mehsin Jebel Ataya from Iraq to do his presentation. Professor Ataya, can you hear me?
Yes, hi. I am ready. I
Okay.
hear you and see you.
Thank you. You are welcome to your presentation, please.
Thank you so much for giving me this opportunity to attend this conference and allowed me to post my presentation, my slide, sorry. Yeah. Share. I think it's feasible for all.
Yes, please, you make it full screen, please. You can use
Okay.
Control L.
Yes, for that. Yes, sorry. This full screen. Nice now?
Yes, it's perfect. Thank you.
Hi, everyone. Today, I'm so happy to present my presentation, which is under the title Homogeneized Sigma Tau Derivations of Associative Ring. Once I am Mehsin Jebel Ataya. I am from Department of Mathematics, College of Education, Mustasir University, Iraq. Let us start with the main idea of my subject, which mean the abstract. The main purpose of this paper is to introduce the definitions of sigma tau homo derivations, respect sigma tau anti-homo derivations, and homogeneized sigma tau derivations, respect anti-homogeneized sigma tau derivations of rings. Furthermore, we posted some result about this concept. In the background of this subject, let us introduce the background about this algebraic area. The modern definition of abstract ring appeared in 1914 in Franklin's paper, which under the title on zero divisors and decomposition of rings. One of the natural equations of the ring theory is to determine condition imply commutativity of the ring. In fact, the study of derivation was initiated during the 1950s, 1960s. Derivations of ring hit tremendous development in the 1957 when Postner established two very striking result in this case of prime ring. He obtained the following result. First one, Postner's the first theorem, let R be a prime ring of characteristic not equal to and D1, D2 derivations of R such that composition of D1, D2 is also derivation, and at least one of D1 and D2 is zero. His second theorem says that there exists a non-zero centralized derivation on a prime ring R implies that R is a commutative ring. Namely, this is another way for Postner's second theorem. Let R be a prime ring and the derivation of R such that for all x in R, x d of x minus d of x x. Another word, we have the bracket d of x with x belong to z of R. Z of R here is center of a prime ring, is the center of prime ring R. Then if D is not the zero derivation, R is commutative. A considerable amount of work has been done in derivation and related mappings during the last decades. For example, this references which I posted it in the last slide. Indeed, Asma and Najat and Ahmed provide, sorry. Provide some result on homo derivation of R. They say if H is strong commutativity preserving on the ideal U, then the ideal subset of Z of R, where a mapping H from R to R is strongly commutativity preserving, write by short as CP on S if the bracket XY equal bracket H of X, H of Y for all XY in the S. This is general formula, or let me definition of strong commutativity preserving. In fact, the study of commutativity preserving started in 1976 when the Watkins published his paper dealing with bijective linear commutativity preserving a map on matrix algebra. On the other hand, Nadim al-Rahman and other provide, and references 11 provide that R is a 2000 free prime ring, U is a non-zero ideal of R, and H is and HP homo derivation of R if condition, this is condition H of bracket XY minus plus bracket XY and Z of R, then the ideal I subset of center. Abdul Karim studied the commutativity of 3' near rings admitting homo derivations which satisfy certain differential identity on near ring. Homo derivation has diversity notation in agreement with the results of Glassman and Case investigated the different notation of homo derivation. The effect of homo derivation on ideal studied by Al-Hurayfi and Muthanna. They provide that as a non-zero left ideal in a prime ring that it missed homo derivation H, which is 0 power valued on U, and satisfying this relation for all XY in U. And also other authors like Ahmed Al-Kinani work on CE homo derivation, centrally extended homo derivation, and get their the additive map H from R to R is their map is additive. Here we pose the natural question here is whether we can find other types of homo derivation. Hence, the answer to this question is affirmative, where this article aims to introduce the definitions of sigma tau homo derivation and homo generalized sigma tau derivation, offering and make some basic observation. The basic concept during this work R will associative ring and Z is center for all X, Y, and R. We can write the notation this bracket for this commutator and X circle Y for anti-commutator. Here plus also make some identities. Recall that A is sim prime if AR A equals 0 plus A equals 0, and R is a prime if A RBA equals 0 plus A equals 0 or B equals 0. Relation between prime and syprime. If the prime ring is syprime, but the converse is not true always. Furthermore, R is said to be commutative if xy equal yx for all xy in R. Annotation of anti-commutative of ring. A ring is said to be anti-commutative if x y equal minus y x for all xy in R, and R is said to be antaution free if for x in R and x equals 0 plus x equals 0. Let R be a commutative ring with identity not equal 0. Recall that a proper ideal, ideal different from R of R is said to be semi-prime if A belong to R and A square in the ideal implies A in ideal. Then a proper ideal U of R to be weakly semi-prime if A in R and A square not equal 0 such that A square belong to the ideal implies A in ideal U. An ideal A is said to be weak zero divisor if there are R and S belong to R elements of ring with RAS equal 0 and RS multiply RS not equal 0. A map D from R to R is said to be commuting on R if the bracket equals 0 and centralizing if the same bracket, but in this case belong to center of R. In 2000, Sophie introduced the definition of homo derivation as a mapping from R to R is satisfy this relation for all x, y in R. It's clear that homo derivation also is also a derivation if homo derivation become derivation if h x hy equals 0 xy in R. In this case, we can write by this way. So if R prime ring, then the only additive mapping which is both derivation and homo derivation is 0 map. If S subset R, a map D from R to R preserves S if D of S subset S, a map D from R to R is 0 power valued on S if D preserve S and if for each x in S there exists a positive integer n of x greater than 1 such that satisfy this relation. An additive mapping D from R to R is called a derivation of Leibniz rule holds. This is Leibniz rule holds for all xy in R. Also an additive mapping D capital R from R to R is called generalized derivation if there exists an additive mapping D on R such that D satisfy this relation for all x in R. Besides derivations and generalized inner derivation, then also generalize the concept of left multiplars, right multiplars, and respect right multiplars. The additive mapping satisfy this relation. Further, this as motivation, we define the additive mapping D from R to R is called sigma tau derivation if there exist automorphisms sigma tau from R to R such that D satisfy this relation. This look like the Leibniz rule, but just here sigma tau.
Professor, you have 5 minutes.
Yes, also this definition of sigma tau, generalized sigma tau derivation. And the main definition in this section, we introduce the main definitions which will be used during our work. These are sigma tau, RB ring, sigma tau automorphism, and additive mapping H is called sigma tau homoderivation on R if satisfy this relation, anti-homoderivation of R if satisfy this relation. If this hx hy equals 0, then H is sigma derivation, not homo, respect here. If sigma tau derivation, this term equals 0, then H become homomorphism mapping or anti-homomorphism mapping. If sigma tau equal identity, we will get this result. Just for more motivation, we call about this example, about this previous definition, we put this example H here by this way, H mu x, x is multiplier endomorphism on an R, and by step, I find this example satisfy previous definition. Second definition, RB, let R be a ring, sigma tau automorphism, and additive mapping H capital is called homogeneized sigma tau derivation of R if H satisfies this relation, where H small here is sigma tau homo derivation of R, anti-homo generalized derivation by the same manner. We will find, we will have this definition. Actually, we can apply some steps about the previous example to explain on illustration this definition. This remark about the second definition. To prove the main theorem, we need some lemma 1 and lemma 2 and lemma 3. For the time, it is limited, so I speak quickly, sorry about that. RB ring, then every intersection of prime ideals is sim prime. Conversely, every sim prime ideal is an intersection of prime ideals. Now it's time for the results concerning sigma tau homo derivation on associative ring. Theorem 3.1, let R be integral domain with characteristic not equal to sigma tau automorphism mapping of RU an ideal. H is sigma tau derivation such that H square of R equals 0, then the ideal will be sim prime ideal. Corollary to R be integral domain with characteristic not equal to, and H sigma tau homo derivation under the same condition. H is sigma tau derivation on R. Proposition 3, let R 2003 sim prime prime commutativity until ring and sigma tau. Always automorphism be an ideal. H satisfy this relation, then R is weak simple weakly semi-prime ideal. When we can prove the following theorem via the same technique, this is R 2003 sim prime ring with 0 divisor of 0, and H sigma homo derivation satisfy this relation, then U weakly sim prime ideal. R has weak 0 divisor. H is sigma tau derivation of R. Proposition 5, RB RB a ring with without 0 divisor, and H is sigma tau homo derivation such that satisfy H of R, H square R, then H of R equals 0. Theorem 3.6, R 2003 sim prime ring, U ideal. H sigma tau homo derivation satisfy the bracket HR1, HR2 for all R1, R2, and R, then H of R equals 0. This is corollary of the section, final result of this section, R 2003, and ideal H sigma tau of R satisfy this identity. H of x circle H of y equals 0 for all x, y, and R, then H of R equals 0. And the section which study homogeneized sigma tau derivation, we find this theorem RB2000 free prime ring sigma tau and sigma tau here also automorphism and H homogeneized sigma tau derivation, which is also 0 or valued on an R, satisfy this relation. Then H of R, H capital equal H small, this homogeneized and this just homo derivation. Corollary to
Professor, please,
yes,
last verse.
Yes, just 2 minutes if possible.
No.
Okay,
Unfortunately.
Okay, no problem. Now this theorem, other result. And I closed my paper by the list of references which I used during my work. I hope when my paper has accepted in the publish, you can see more details. Thank you for your attention.
Thank you for your Professor Atea, for your valuable talk. Unfortunately, we don't have enough time for the question and comment, dear attendants. If you have any questions, please privately connect with Professor Atea. Thank you again, Professor
Thank
Atea.
You, sir. Thank you. Stop share now.
Please stop your screen share. Yes.
Thank you.
Now I kindly invite Professor İsmail Demir from Turkey to the presentation. The title of his talk is Classification of Odd Nilpotent Leibniz Algebras. Professor Demir, you are welcome to do your presentation, please.
Thank you, Professor. I'm İsmail Demir from Uşak University, and I will talk about the classification of odd nilpotent Leibniz algebras. So Leibniz algebras are non-antisymmetric generalization of Lie algebras. They were first introduced by Bloch in 1965. And in order to emphasize their connections with derivations, Bloch called them D algebras. But Leibniz algebras were not much studied till 1990s. And then Lode independently rediscovered them. And Leibniz algebras have been studied by several researchers since then. So let's take an algebra or a field F. We can define the left multiplication L sub A by L sub A of x is equal to A bracket x. And the right multiplication can be denoted by R sub A, and here R sub A of x is equal to x bracket A. And we know that a linear map which satisfies Leibniz rule is called a derivation. So now let's define Leibniz algebra. So a left Leibniz algebra is an algebra satisfying the Leibniz identity. So you can see the Leibniz identity, and from that Leibniz identity, we can see that the left multiplication is derivation here. So we can easily say that a Leibniz algebra is called left Leibniz algebra if the left multiplication is a derivation. And similarly, if the right multiplication is a derivation, we can call it right Leibniz algebra. This distinction does really matter because the definition of Leibniz algebra is not left-right symmetric. In this talk, when I say Leibniz algebra, it will refer to left Leibniz algebra. So we can give other basic definitions which are parallel to definitions in Lie algebras. So let's take a subspace I of A. If I bracket I is contained in I, then we call I a subalgebra of A. And if A bracket I and I bracket A is contained in I, then I is called an ideal. And A bracket A is called the derived algebra. And one of the differences between Lie and Leibniz algebras is the existence of this ideal Liebe. It's the ideal generated by the squares of the elements, and it's in fact an abelian ideal. And as you can see in Lie algebras, Liebe is 0 because we know that squares of any elements in Lie algebra is 0. So we can define the center of A similarly. And let's say we have a Leibniz algebra. The series of ideals A contains A to the 1, contains A to the 2. This is called the lower central series of A. And if a Leibniz algebra has a lower central series reached 0 at some finite step, then we call it a nilpotent Leibniz algebra. A Leibniz algebra is called an odd nilpotent if its even dimensional ideals in its lower central series all have dimension 0. And a Leibniz algebra is called split if it can be written as a direct sum of two non-trivial ideals. Otherwise, we call it non-split. So let me talk about the classification of Lie and Leibniz algebras, the history of the classification. We have a famous Levy-Maltsev theorem, which says that any complex Lie algebra, infinite dimensional complex Lie algebra, or a field of characteristic 0, can be written as a semi-direct sum of semi-simple Lie algebra and solvable Lie algebra. So this reduces the problem of classification of Lie algebras to other separate problems, classification of semi-simple Lie algebras and classification of solvable Lie algebras. And classification of complex semi-simple Lie algebras were completely done first by Killing, then Cartan corrected Killing's proof, and Dynkin gave another proof using Dynkin diagrams. But classification of solvable Lie algebras is still unsolved. Maltsev reduced the problem to classifying nilpotent Lie algebras, and so far we know only the complete classification of complex nilpotent Lie algebras up to dimension 7. It turns out that the classifying complex Leibniz algebras is more complicated due to lack of anti-symmetry property. And the first work on this was done by Lode himself, and he classified complex nilpotent Leibniz algebras up to dimension 2. Then Ayupov and Omirov in 1999 classified three-dimensional complex nilpotent Leibniz algebras using some isomorphic invariants. Then Casas, Insua, and Ladra gave the complete classification of three-dimensional complex nilpotent Leibniz algebras, but they used a different technique, the technique involving Grosvenor bases. In fact, they give two algorithms, one of them deciding whether a given algebra is a Leibniz algebra, and the other deciding that any given two Leibniz algebras are isomorphic or not. So this is very useful, and in fact, I use that algorithm in my classification as well. And classification of four-dimensional complex nilpotent Leibniz algebras is first studied by Albeveri, Omirov, and Rahimov in 2006. And they use the classification of filiform Leibniz algebras and the classification of five-dimensional associative algebras to get their classification. And me and my advisors gave the complete classification of nilpotent Leibniz algebras up to dimension 5. And we used canonical form for the congruous classes of matrices. So before starting the classification, let's check these lemmas. These lemmas are going to be useful. So let's take a non-split nilpotent Leibniz algebra of class C, then A to the C is contained in the center, and that's contained in A squared. The second lemma says that if we have a nilpotent Leibniz algebra with dimension of Levy is equal to 1, then Levy must be contained in the center. And we have another lemma which is giving a relation between the dimension of A cubed Levy and A squared. Now let's start to classify odd nilpotent Leibniz algebras. Before starting, we define the following characteristic, K of A. It's the dimension of A squared, A cubed, and go on, like that. And we'll consider some subcases here. So let's start with K of A 3100. So in this case, our Leibniz algebra is three-dimensional and A squared is one-dimensional. So A squared must be equal to Levy here, and that's equal to span of X3 for some non-zero X3 in A. Then we can take a complementary subspace to A squared in A. So this V here is two-dimensional. Then for any two elements in V, we know that the bracket of U and V must be a scalar multiple of X3. And then we can define the bilinear form F that goes from V cross V to complex numbers, and we define it by F of U V equals C. And we know that the canonical forms for the congruence class of matrices associated with this bilinear form given by Terran in 2010. And before giving that theorem, let's explain this notation. A / B is a block matrix where B is in the upper right block and A is in the lower left block. Here, Terran's theorem says that we can write any complex square matrix as a direct sum of the matrices of these types. So we have 6 types of matrices here, and we're going to use this theorem in order to get our classification. But remember, we're only focusing on non-split, non-Lie Leibniz algebras because we cannot always get split Leibniz algebras from non-split ones. So we have this lemma. It says that if our matrix is in this form, n equals k direct sum 0, then the Leibniz algebra corresponding to that is split. So we took A squared is one-dimensional, then there exists an ordered basis x1, x2 of V such that xi bracket xj is aij times x3, and here the coefficients of aij's, this matrix, determines the algebra. And now all we need to do is to consider all possible 2x2 matrices. So we have 3 different matrices, B2, E2, and 1 direct sum 1. So how are we going to get the Leibniz algebra? So let's look at E2, and E2 is 0, 1, negative 1, 1. So we can see here that x1 bracket x1 is 0 times x3, x1 bracket x2 is 1 times x3, and x2 bracket x1 is minus 1 x3, and x2 bracket x2 is x3. So from E2, we get this Leibniz algebra. And we had other 2 matrices, 1 direct sum 1 and B2, and from those we can get these 2 algebras. And these are all non-isomorphic. We checked it by using mathematical program, implementing that algorithm. So in this case, we have 2 single algebras and one parameter infinite family. So let's check K of A is equal to 5, 1, 0, 0. In this case, we have 14 different classes. And let's check the proof here. Similarly, we're going to take A squared is equal to Lieb A, and that's equal to span of x5. And we're going to take a complementary subspace. And using the Terran's theorem, we can say that there exists an ordered basis, x1, x2, x3, x4. So all we need to do is to consider all possible 4x4 matrices from Terran's theorem. And here we group the matrices corresponding to each partition of 4. So we have all these matrices. From these matrices, we can get all isomorphism classes listed here. Now let's look at another example, another subcase. Here we have 5, 3, 1, 0. So here A squared is not one-dimensional, but still we can use this congruence classes of bilinear form technique. So let's take a 5-dimensional non-split, non-Lie, nilpotent Leibniz algebra, and A squared is 3-dimensional, and A cube is 1-dimensional, and Lieb is 1-dimensional. We need to show that we should get these 4 algebras. So we had this lemma. Using that, we can see that A cube not equal to Lieb A, and let's take Lieb A is equal to span of E5, and A cube is equal to span of E4. Then center is span of E4 and E5. And then we can extend this to a basis of A squared, and taking V equals span of E1, E2, and we can see that there exists an ordered basis of V such that EI bracket EJ is alpha IJ E3 plus beta IJ E4 and AIJ E5. And here, AIJs are the entries of the matrix given in Terran's theorem. And we are lucky here because we only need to consider 2x2 matrices. And there are only 4 possible 2x2 matrices. And also we have another lemma, which is very useful because it says that the Leibniz algebras corresponding to E2 and C1 direct sum A1 are isomorphic. Similarly, the Leibniz algebras corresponding to B2 and C1 direct sum C1 are isomorphic. So it's enough to consider only two matrices in this case. So first, I'm going to take our matrix is equal to C1 direct sum A1. Then multiplication of our Leibniz algebra can be given by this multiplication table. And in this case, we're going to consider two cases. When beta 2 equals 0, with this space of change, we can see that this algebra is isomorphic to A1 listed before. And if beta 2 is not equal to 0, again, we're applying this simple change of basis and get A2. And now we're going to do it for the matrix C1 direct sum C1. Then we have this multiplication table. And the first case, when beta 2 equals 0, yields the Leibniz algebra A3. And the other case, from the other case, we can get A4. So we can use this bilinear form technique to get other cases. So I did it, and let me share you the number of isomorphism classes. And here we show that in this case, when 3100, we had only two single algebras and one parameter infinite family. When K of A is equal to 5100, we had 9 single algebras, 4 one-parameter infinite families, and 1 two-parameter infinite families. When K of A is equal to 5300, there exists no single algebra. When it's 5310, there are only 4 single algebras. When K of A is equal to 7100, so A is 7-dimensional here, we have 30 single algebras, 13 one-parameter infinite families, 3 two-parameter infinite families, and 1 three-parameter infinite family. And I also consider another case when K of A is equal to 75310. And in that case, we have 5 single algebras, 2 one-parameter infinite families, and 1 two-parameter infinite family. So actually, let me recall you that the number of different isomorphism classes of 6-dimensional complex nilpotent Lie algebras were only 20. But here in Leibniz algebras, even for these subcases, we got some infinite families. So this may give you an idea how wild the classification of Leibniz algebras is. So as a future work, I would like to apply this congruence classes of bilinear form technique in order to get the complete classification of nilpotent Leibniz algebras with dimension of Lie is equal to 1. And similarly, with the same technique, I intend to get the classification when A squared, when the derived algebra is n minus 2-dimensional. And also I would like to complete the classification of complex odd nilpotent Leibniz algebras up to dimension 7. And here are my references. And thank you for taking your time to listen to me. Any questions?
Thank you, Professor Demir, for your valuable presentation. Dear attendees, is there any question or comment? I think there is no question. Thank you again, Professor, for his contribution. Now, I kindly invite Professor Yusuf Alagöz from Turkey to do the presentation. Professor Alagöz, you are welcome to present your study, please.
Thank you. Can you see my page?
Yes, we can see, but you can make it full screen, please.
Okay.
Thank you.
Thank you very much. Today I will talk about modules with respect to mean purity. The notion of purity plays a significant role in module and ring theory, and there are several generalizations of purity since it was presented in the literature. Now, firstly, I will give the most general definition of purity, and then we will restrict ourselves to the notion of purity, mean purity, and its homological objects. a short exact sequence A, B, C of right arm modules is called C pure. By C pure, we mean that pure with respect to the class of right arm modules C. It's called C pure if for any homomorphism from S to the C, any homomorphism from S to the C can be lifted to a homomorphism from S to the B for any S in the class of C. Equivalently, hom SB, hom SC is an epimorphism. Here, in 1969, Warfield gave a general definition for purity, and he restricted himself to the class of two classes of modules, finitely presented right arm modules and cyclically presented right arm modules. And he considered when C is the class of all finitely presented right arm modules, then he called to this purity as cone purity. And also if C is the class of all cyclically presented right arm modules, then he introduced the notion of RD purity. And later in 2008, Mao considered the notion of mean purity by using the class of C such that class of C and this class contains the modules R over AR such that RA is a minimal left ideal of R. So it's clear by the definitions, purity implies RD purity, and RD purity implies also mean purity, and the converses are not true in general. Later we will give some examples for the converses. And when you studying a notion of purity, it is important to understand this homological objects of such dispurity. For example, it is really important to understand the injective and projective objects of such dispurities. And also Warfield in the same paper gave the general definition of such dispurities. A is called C pure injective in case A has injective property with respect to C pure exact sequences, and A is called C pure projective in case A has projective property with respect to C pure exact sequences. And again, if you restrict yourself to the class of finitely presented right arm modules, then we have the well-known notion of pure injective and pure projective modules. And on that paper, Warfield mainly work on such these two module classes. And after that, in 2006, Couchot considered the classes, the injective and projective analogs of RD purity. And then in 2008 also, Mao studied extensively the injective analogs of mean purity, but so far it is projective analogs of mean purity are not considered. And in this talk, I mainly focus on mean pure projective modules and mean pure injective modules and its relation with other well-known homological objects. Before giving the definition of mean pure projective modules, the notion of mean injectivity is really important when you studying mean purity, especially over a commutative ring, since if a module M is over a commutative ring is mean injective, if and only if every short exact sequence starting with this module is mean pure. So by using this observation, we will give some nice characterization of rings. So mean injectivity and mean purity is really important in this context, and these two notions are studied extensively from the following papers. Now we are ready to give the definition of mean pure projectivity. A is mean pure projective if it is projective relative to mean pure short exact sequences. And it's trivial by the definitions that R over AR is mean pure projective for any simple left ideal RA. And naturally, any projective module is mean pure projective. So, but the converse is not true in general. If we consider the ring R as a z over p square z for some prime integer p, then here R over PR is a mu pure projective module, but this module need not be projective. Otherwise, this epimorphism would be split. But we know that this ring is indecomposable as an R module also. So here, this would be contradiction. So in this case, R over PR is not projective. So the first question is here is to give the converse of the condition B, whether which gives us a ring characterization of or not. So when we are trying to characterize such these rings, we have here R is left universally mean injective if and only if every mean pure projective right R module is projective. And also this is equivalent to saying that every mean pure injective right R module is injective. And this is also equivalent to the fact that every exact sequence of right R modules is mean pure. Here, by a left universally mean injective ring, we mean that the rings whose every module is mean injective as a left R module. And equivalently, R is left mean injective and left PS. Here, PS ring is a ring with projective socle. And then we need to understand the relation of such these purities with the well-known notion of cone purity. So we said that purity implies mean purity, but the converse is not true. For this, we will use this famous example of Brewer and Costa, and they constructed in this example from this paper in 1975. Here the example is the following: let K be a finite field with Q elements, and R is the ring KXY quotient to this ideal, and it's represented by K small x and small y. And S is the ring RT quotient or quotient with the following ideal. So here they prove that R is cyclically pure in S, and since cyclically purity implies mean purity, we can observe that R is mean pure in S, but they prove that R is not pure in S. So we find that we can easily see that the converse of the fact that purity implies mean purity is not true in general. Also, since purity implies mean purity, we can say that every mean pure injective module is pure injective, and every mean pure projective module is pure projective. Also, to show that the converse is not true in general, we will use this example again. It is well known that every Artinian module is pure injective. Hence, also Brewer and Costa on that paper proved that this ring R is an Artinian ring, and it is also as an R module, it is Artinian, so it is pure injective, but it is not mean pure injective. Otherwise, this inclusion map from R to the S must be split, since R is mean pure in S. But splitting of this map will imply that R is pure in S. But we know that it is not pure in S, so R as an R module cannot be mean pure injective. Also, this example will give us the converse of the for projectivity is also not true in general by the following propositions. These three facts are equivalent. Mean purity, if mean purity implies purity, pure injective with if and only if every pure injective module is mean pure injective and every pure projective module is mean pure projective. So it is important to give a characterization of such these rings, but so far we don't have an exact answer to this, but we have some partial results. If we assume that R satisfies this equivalent, one of these equivalent conditions, then R is an RD ring. And if we assume that R is commutative also, then the localization of R at any prime ideal P is evaluation ring. And also in this case, R is an arithmetic ring and every mean injective R module is absolutely pure. Here, by an arithmetic ring, we mean that R has a distributive lattice of ideas. And also, if we add a condition, also Nodarian condition here, if R is commutative Nodarian ring that satisfies one of the equivalent condition of this proposition, then R is a quasi-Frobenius arithmetic ring. I'm optimistic we can give at least a characterization over a commutative Nodarian ring for this proposition. But so far also it is an open question. It is an open question. Is it possible to characterize the rings whose mean pure exact sequences are pure? Also, the same question can be asked for RD purity. At least if we give an answer to this question over a commutative Nodarian ring, it will be nice also. Another question is when you're studying such purities, it is important also understand the relations with well-known notion homological objects, for example, relations with injective and projective modules. So before giving these relations, let's give the following fact and lemma, the crucial fact and lemma. If we let S the class of R over AR such that RA is a minimal left ideal of R, in the beginning of the talk we said that S purity is exactly the mean purity here, and this is the same as the purity with respect to the class S union R. We can add the R on that class. So the class of mean pure projective modules is the modules direct sum of modules of the class of S union R. Okay, the class of add S union R is the class of all mean pure projective modules. So the natural question is here whether can we write the mean pure projective modules as a direct sum of a projective modules and the modules in add S. So over a right Artinian ring, we prove that M is mean pure projective if and only if M is isomorphic to P direct sum of L, where P is projective, and L in add S. This here add S is the direct sum of the class of modules in direct sum of modules in S. So here, so we are ready to give the characterization of the rings whose injective modules mean pure projective and the rings whose projective modules are mean pure injectives. So at least over a right CF ring, every injective right R module is mean pure projective, characterizes the right quasi-Frobenius rings. But if we assume that R is commutative ring, then we can omit this right CF condition. Here, over a commutative ring, R is a quasi-Frobenius ring if and only if every injective module is mean pure projective. And this is also equivalent to say that R is Artinian and the injective hull of R is mean pure projective. And also this characterizes the rings whose projective modules are mean pure projective, mean pure injective over an Artinian ring. And this is also equivalent to saying that R is Artinian and mean pure injective. This is another nice characterization of quasi-Frobenius rings over a commutative ring. So also it is natural to consider the converse of this fact. The rings whose mean pure projective modules are injective. And this also characterizes the semi-simple rings. R is semi-simple, every mean pure injective is projective, and every projective is injective. So the last question here is to characterizing the rings whose all modules are mean pure projective. So for the case of pure projectivity and RD projectivity, the rings, if every module is pure projective or every module is RD projective, then if and only if R is pure semi-simple ring. But pure semi-simple rings are not characterized as the following equivalent conditions. If every right R module is mean projective, if and only if every right R module is mean pure injective, and this is equivalent to saying that every mean pure exact sequence of right R modules splits. And if R satisfies one of the equivalent conditions of this result, then R is a right and left Kotte ring. And also if R is normal, by a right Kotte ring, we mean that each right R module is a direct sum of cyclic right R modules. Moreover, if we assume that R is normal, by a normal ring, we mean that all its idempotents are central, then R is an Artinian principal ideal ring. If we replace normality with commutativity here, then R is a quasi-Frobenius serial ring. So by using this result, if we assume that R is commutative in the composable ring with Jacobson scar 0, then every module is mean pure projective if and only if R is either field or quasi-Frobenius ring of composition length 2. We can give an example for that rings that satisfy these all conditions of these rings. For example, if we assume that R is a Z over P square Z here, R is indecomposable, commutative, G square 0, and quasi-Frobenius ring of composition length 2. We have such examples. So we have here an important question. We said that from previous proposition, commutative rings whose modules are mean pure projective are quasi-Frobenius serial. And also, if R is quasi-Frobenius serial and it's Jacobson scar 0, then R is the direct product of the rings Ri's from 1 to the n, where Ri is either a field or a quasi-Frobenius ring of length 2. This result given by Arabi, Kakard, and his friends in 2017. And inspired by this result and our proposition, now our question is, can we omit this in the composable condition? If we assume that R is commutative ring which is scar 0, is it possible to give an answer to the following question? Every module is mean pure projective if and only if R is the direct product of the rings Ri's, where Ri is either a field or a quasi-Frobenius ring of length 2. I think this result is true, but we have a sum gap from the proof. If we fix it, maybe this question will be true, but for now this is an open question, and the following question also more difficult question than the first one. Is it possible to give a complete characterization of the rings whose modules are mean pure projective? Now I want to finish my talk with these two open questions. Thank you for your time and attention, and these are my references. Thank you so much.
Thank you, Professor Alagöz, for your valuable presentation. Dear attendees, is there any question or comment? I think there is no questions. Thank you again, Professor Alagöz, for your talk. Now, please, you turn off your screen share, please, Professor. Professor Alagöz,
okay.
Thank you. Now, I kindly invite Professor Süleyman Aydın from Turkey to the presentation. The title of his talk is The Moore-Penrose Generalized Inverse of the Fibonacci Matrix and Applications to the Cryptology. Professor Aydın, you are welcome to present your study. Can you please make it full screen?
Yes, okay. I'm starting.
Thank you.
My name is Süleyman Aydın. I am a PhD student at Pamukkale University in Turkey. Today, I'll give a presentation about the Moore-Penrose inverse of the Fibonacci matrix and applications to the cryptology. Before starting my presentation, I give information about the Fibonacci numbers and Moore-Penrose inverse. Let's remember the Fibonacci numbers. Fibonacci numbers are defined by the recurrence relations of these equations with the initial conditions f0 and f1. Lots of generalizations of these numbers are satisfied and studied by some authors. We can see these studies in these references. The Fibonacci Q matrix is defined as follows, and the end power of the Fibonacci Q matrix is shown by as follows. Now I'll give a definition about the Moore-Penrose inverse, also known as a Poiseuille inverse, are used in mathematics and many branches of science, in addition to being used in problems such as analysis in mathematics and calculation of solutions of linear equation systems. It has many application fields in electrical engineering and other disciplines. For more information, we can see in these references. In this study, we denote the M matrix is a n by n matrix. This matrix is a n by n matrix, the set of complex respectively. Given a matrix A, the conjugate of transpose of A is denoted this form. In this section, we give important studies about the Moore-Penrose generalized inverse of the rectangular matrices. The first definition is about the four Moore-Penrose conditions. We can see in here, if our matrix is a non-singular, it is clear that the Moore-Penrose of the R matrix is the ordinary inverse of the R matrix. In here, these theorems and lemma relate to four more conditions, four Moore-Penrose of the inverse of the conditions. In here, as a result of the given theorems and lemma, we can give the following theorem. For any R matrices, R matrix is the n by n matrix with rank R, and R equals F multiply E, where F is n by R matrix and E is R and M matrices. Then we get this equation. In here, the R matrix is the Moore-Penrose of the R matrices. Now, we give two corollary for showing the Poiseuille inverse. The first corollary is about the full row rank decomposition. In our previous theorem, if our matrix has full row rank, for example, R equals n, then by lemma, we get this equation. The second corollary is about the full columns rank decomposition. In here, R has full column rank, R equals n, then by lemma, we get this equation in here. To calculate the Moore-Penrose inverse of a matrix, it is calculated either by the maximal rank factorization of the matrix or by calculating its singular value decomposition. In this paper, we use the singular value decomposition to calculate the Moore-Penrose inverse. At first, I give a definition about the singular value decomposition. For the matrix C, C is a n by n matrix with rank R. The singular value decomposition is defined as this equation. In here, U matrix is the n by n matrix. V matrix is the m by n matrix. These matrices are unitary matrices. And the sigma matrix is the n by n matrices, is a diagonal matrix of the singular values S of C. The singular values are the square roots of the eigenvalues of the square matrices, this equation or this equation, which are the same values. The number of singular values is equal to the rank of C. We can see in here the sigma matrices. S is the R by R matrices. This matrix is a singular matrices. These rows and these columns of sigma matrices are full of zeros. I'll give a corollary. The singular value decomposition can be written as a submission like this. In here, the columns of U are x1, x2, xn, and V are v1, v2, vn, and the orthonormal. From this definition and corollary, we can find the posterior inverse of any matrix C. In this theorem, we give a definition, or we give a theorem. Let's C matrix is the n by m matrices and have rank R, and the C occurs the singular Walier decomposition form as defined above, like this. In here, X matrices is the more penrose of the matrices C. Day by day, in order to ensure information security of data transfer over communication channels, many studies have been and are continuing on this subject. Therefore, encoding and decoding algorithms play an important role in information security. In particular, the Fibonacci sequence is one of the most preferred number sequence in coding theory. We can see the examples of this in many studies in these references. Algebraic methods in cryptography were examined in the studies given here and in many other studies. In other words, these are algebraic encryption methods that transform a plain message into an encrypted message. We can see these studies in these references. In the first part of the study, we defined the more Penrose inverse of a rectangular matrix whose elements are Fibonacci numbers. In the second part of this study, we give the encryption algorithm defined on the rectangular Fibonacci matrix and the more Penrose inverse. The last one is illustrative example will be given for the encryption algorithm in the last part of the study. In this section, we find the general form of the more Penrose inverse of the matrix whose elements are Fibonacci numbers, and we give the examples. The first theorem lets the elements in the F matrix. F matrix is the n by n matrix, be rectangular matrix with the Fibonacci numbers. For positive integers m and n, we have three conditions. The first condition is F matrices is a rectangular matrix, has full column rank. The rank of F matrix equals m greater than n. We have left inverse as follows. The second condition, n greater than m, we have right inverse as follows. The last condition is m equals n. In here, F is a square matrix. In here, the F matrices is the ordinary inverse of the more Penrose inverse. The other theorem, in here, the F matrix is the n by n matrix, be rectangular matrix with the Fibonacci numbers. For positive integers m and n, in here we have three conditions. Let m greater than n, if m minus n is odd, we get s like this. This one is the more Penrose inverse of the Fibonacci matrix. In here, fn is the nth Fibonacci numbers. If m minus n is even, we get s like this. The second condition, n greater than m, if m minus n is odd, we get s like this. If m minus n is even, we get s like this. In here is the fn is the nth Fibonacci number. The third condition, let m equals n. The Fibonacci matrix is the square matrix. In here, we get the ordinary inverse of Fibonacci matrix. For example, m equals 7 and n equals 3. Then we get the rectangular Fibonacci matrix as follows. In here, m greater than n, we compute the more Penrose inverse as like this. In here is the fn is the nth Fibonacci numbers. In this section, we introduce a new decoding theory using rectangular Fibonacci matrix. This rectangular Fibonacci matrix plays a very important role in the construction of coding algorithm. We put our message in a matrix of M matrices and let us show the initial message in the form of the rectangular or square matrix of M. Throughout this paper, M matrices is the R by N matrix, defines the matrix of the numerical values corresponding to the blocks of letters of the plain text. We consider the K matrix as the rectangular Fibonacci matrix. This transformation is called the coding transformation. This matrix is a code matrix. Let's first obtain the more penrose inverse of our K matrix to obtain the coding transformation. So we get the more penrose inverse of our rectangular Fibonacci matrix. This matrix, F matrix, being the more penrose inverse of our rectangular Fibonacci matrix, this transformation is called the decoding transformation. Now we solve the example using the alphabet table. This alphabet table is writing according to mode 26. We can choose and consider the characters in the alphabet table to our wishes. I give example. Let us consider the message matrix for the following message text. This one is a message text Fibonacci number. Now we choose the K matrix as a Fibonacci matrix. This matrix is the rectangular matrix, which is 4 column ranked. So it has a left inverse. The more penrose inverse of the Fibonacci matrix, we can get like this. Let's write the message matrix in M matrices with the mode 26 as follows. The code matrix is, this one is a code transform encryption transformation. We can get these matrices. Then we convert the matrix C according to alphabet table as follows, like this. Therefore, our encrypted message is like this, with the K matrix is a rectangular matrix. Let's create our decoding algorithm based on our received encryption method and the K matrix. We convert the message text according to alphabet table as follows. Then we get the decoding transformation. This transformation is decoding transformation. We can get the M matrix with mode 26. We convert the matrix of M matrices according to alphabet table as follows. Then we get as the Fibonacci number. Conclusion. In the first part of the study, we defined the general form of the more penrose inverse of the matrix, whose elements are Fibonacci numbers. We examined the studies of the F matrices, where F is a rectangular matrix according to M and N values as follows. The first condition, M greater than N, we have left inverse. The second condition, N greater than M, we have right inverse. The third condition, the last condition, N equals M, we get the ordinary inverse of Fibonacci matrix. In the second part of this study, we defined a new coding theory using the more penrose inverse of rectangular matrix and gave illustrative example. This rectangular Fibonacci matrix plays very important role in the construction of coding algorithm. This decoding method is different from other classical algebraic coding methods. Square matrices are used in all of the methods used in cryptology. We have shown that rectangular matrices can also be used in cryptology with this method. The K matrix we use in this method is the rectangular Fibonacci matrix. We can say that using the method is safer than the inverse square matrix. In here, we can see my references. Thank you for listening to me.
Thank you, Professor Aydenius, for your valuable presentation. Dear attendees, is there any question? I think there is no question. We thank to again Professor Aydinius for his contribution.
Thank you very much.
Please, you can stop share screen. Thank you. Now we will continue with the last talk in this session. Now I kindly invite Professor Marian Sheybani Abdul Yusufi from Iran to do the presentation. Professor Abdul Yusufi, can you hear me? Professor, please open your microphone. Can you hear me, Professor?
Yes.
Yes, okay, we can hear you also.
Okay.
Professor, you are welcome to present your study, please.
Okay. First of all, I would like to thank the organizing committee for giving us the...
Sorry, you can make it full screen, please?
Yes, it is full screen.
No, you can press Ctrl L.
Okay.
Ctrl L, like Los Angeles, L.
Yes, this one.
No. You use, yes, it's perfect.
Okay. Is that okay?
Yes, okay. Yes, okay. Please go ahead.
Thank you. First of all, I would like to thank the organizing committee for giving us the opportunity for attending to this wonderful meeting. I would like to talk about a new generalization of inverse, that is the group inverse of like complex matrices. That is, okay, my talk is has three parts: motivation, introduction, and main results. Okay, the motivation of this study is to establish the representation for the group inverse of a 2 by 2 black complex matrix as this matrix, where A is an square m by m matrix, B is a rectangular m by n matrix, C is a rectangular n by m matrix, and D is an square n by n matrix. All matrices have complex entries. We establish the necessary and sufficient conditions under which M has group inverse. This is a generalization of inverse that we have before. The explicit representation of M hash, I mean the group inverse of M, in terms of the individual blocks is also given. Okay, if we want to talk about the history of the generalized inverse, maybe we can point out to the more permanent inverse. The study of a generalized inverse of elements in rings and Banach algebras has a rich history. Let X belongs to M and C, I means that let X be an squared complex matrix. So in 1955, Penrose established the existence and uniqueness of a matrix like B satisfying this equation, where Xt denotes the conjugate transpose of X, the matrix being known as the Penrose inverse, which is a generalized inverse of a matrix X. With some modification of the Penrose inverse, in 1958, Rosin introduced the concept of a new kind of inverse and called it a pseudo-inverse in associative ring and semigroups. Okay, the definition of the pseudo-inverse of Rosin and the group inverse. Let A be a Banach algebra and let A belongs to A. We say that A has Rosin inverse, provided that there exists some B belongs to A, such that B is equal to BAB, AB is equal to BA. It means that B commutes with A, and A power n is equal to A power n plus 1 multiple to B for some natural number n. The preceding B is unique if it exists, and we do denote it by A power D. The smallest n which satisfies the above condition is called the Dirac index of A and is denoted by end of A. If end of A is equal to 1, then B is called the group inverse of A and is denoted by A hash. Okay, to clarify this definition, we use a now theorem from this reference, and this helps us to find a better way to define the group inverse. The theorem is that let A be an algebra with unity and A belongs to this algebra, then the following conditions are equivalent. 1, there exists a unique idempotent P such that A plus P is invertible and AP is equal to PA is equal to 0. And the second one is that A has group inverse or A is belonging to A hash. That means that the set of all group invertible elements in an algebra A. We have the definition of group inverse in complex. We say that A has group inverse provided that there exists some x, some square complex matrix x such that this equation holds. Ax is equal to xa, x is equal to xax, and A is equal to axa. Such x is unique and if it exists, and we denote it by A hash. Okay, as the group inverse is a special case of Dirac inverse, and you know that the Dirac inverse has several applications, so the group inverse also has several applications, maybe more than the Dirac inverse. If we want to talk about some applications, we can talk about in system of differential equations, also in Markov chain, in iterative methods, and so on. Most works in the literature concerning representation for the group inverse of partition matrices or black matrices were carried out under certain restriction of their blocks. As it is really a hard problem, there are several works to study this problem. Our work is again about this problem. Now we have the main result. The aim of this section is to establish the representation for the group inverse of the partition complex matrix in terms of individual block A, B, and C, and D. Let A and D have group inverses. A power P and D power P are spectral idempotents of A and D respectively. An expression. A power P is equal to IN minus A hash, and D power P is equal to IN minus D hash. We know Derive. It is one of the main theorem in this talk that introduce how we can compute the group inverse of a black complex matrix. Let A and D have group inverses. If we have this condition, first, B, D power IC is equal to 0 for every non-negative integer number.
I think there is some internet connection problem. Professor Abdulusufi, can you hear me? Let's wait a couple of minutes, please. Now, Professor Abdulusufi is not online. We will wait for. Professor Abdulusufi, can you hear me?
I'm sorry, as I have lost the internet. I'm really sorry.
Yeah, don't worry. Please continue your presentation.
I'm really sorry, just a moment.
Yes.
Okay, just a moment, please. Is that okay?
Yes, it's okay.
Can I continue?
Sorry, can you make it full screen, please?
Yes, just a moment. Maybe I can start from the main result. Am I right?
Yes, you can start it.
Is that okay?
Yes, it's okay. Thank you.
Okay, I'm really sorry as I have lost the internet. Okay. This is our main result. Our main
I think again, Professor Abdulusufi having internet trouble problems. So we have to break about 6 minutes for the next session. Thank you for your contribution. See you later. Professor Abdülüstefi, if you present your study in 10 minutes, please continue. Otherwise, sorry, we have to continue with the next section.
I'm sorry. Can you hear me?
Yes, we can hear you. If you present your study in 10 minutes, please continue. Otherwise, we have to continue with the next session.
Okay, I can continue. I hope it is okay. I hope it is okay.
Okay, please go ahead.
Maybe I had better not share my video. Maybe my internet is better. I'm really sorry. Can you hear me?
Yes, we can hear you.
Okay, the main result is about the group inverse of the black complex matrices. The aim of this section is to establish the representation for the group inverse of the black complex matrix and in terms of the individual blacks. Let A power P and A power P are spectral idempotents of A and D, where A and D have the group inverse. In expression, we have A power P is In minus A hash, and D power P is equal to In minus D hash. We know Derive. Our main result, one of our main theorem is that let A and D have group inverses. If B D power IC is equal to 0, then the following are equivalent. First, M has group inverse, and second, we have this equation. A power P, B, D power P is equal to 0. D power P, C, A power P is equal to 0. And CA plus DC multiple to X plus CBD hash plus D power 2Z is equal to 0, where X, Y, and Z are defined in this way. Also in this case, fortunately, we can compute the M hash in this way based on the A hash and D hash. Also, we define X, Y, and Z in this way. By this theorem, we can conclude two corollaries that are the main theorem of two references. One corollary is that let M be this partition matrix. If BC is equal to 0, DC is equal to 0, then the following are equivalent. One, M has group inverse. Second, A power P, B, D power P is equal to 0, and C, A power P is equal to 0, CAX plus CBD hash is equal to 0, where X, Y, and Z are defined in this way. Also in this case, we can compute M hash. This is the main result of a reference, but we can conclude it by our main theorem as a corollary. The other corollary is that let A and D have group inverses. If BC is equal to 0, BD is equal to 0, then the following are equivalent. One, M has group inverse. Second, A power P, B is equal to 0. D power P, C, A, P is equal to 0. C, A hash B plus DC, A hash power 2B plus D power 2Z is equal to 0, where we have X, Y, and Z in this way. Also in this case, we can compute M hash. Now, we come to demonstrate the dual of theorem 1 as following. Let M be a partition matrix. If C, A power A, B is equal to 0 for such I, then the following are equivalent. 1, M has group inverse. Second, A power P, B, D power P is equal to 0 and the other conditions where X, Y, and Z are defined as below. Also in this case, we can compute the M hash. Also by this theorem, we can conclude two corollaries, which are the main result of some references, which is first, let M be this partial matrix. If AB is equal to 0, CB is equal to 0, then the following are equivalent. First, M has group inverses, and second, we have this equation. Also, in this case, we can compute M hash. I mean that the group inverse of M. Finally, we give a numerical example to illustrate this theorem, especially theorem 1. This example is that let M be this partition matrix where A, B, D, and C are defined as below. Then M has group inverse, and we can compute M hash. This is our references. Thank you for your attention. I'm really sorry for this problem. Thank you very much for your time and attention. I'm sorry for this problem. I'm in my office and I don't know why the internet is so bad in this time.
Thank you for your presentation, Professor Abdul Yusufi. Is there any questions? I think there is no question. Thank you again, Professor Abdul Yusufi, for your contribution. Now we will take a break about 5 minutes. Thank you for your contribution again. Professor Abdul Yusufi, please turn off your screen share.
Okay, thank you again. I'm sorry.
Hello, everyone. Good morning, good afternoon, good evening for all of you. Welcome to the second day of the webinar. In this session, I will kindly invite Professor Çisem Güneş Aktaş, first of all, to present his talk on real structures in singular models of K3 surfaces. Please, could you share your screen, Professor Aktaş?
Okay, I will share it now. I think it's okay right now, right?
Yes, the microphone is yours. You can go on, please.
Before I start my talk, let me introduce myself. You already did, but I am Çisem Güneş Aktaş from Abdullah Gül University in Kayseri. I want to thank the organizers for giving me the opportunity here to talk about my work. So here is my title. I will talk about real structures in real models of K3 surfaces. And this is the agenda for today. First of all, I will start with talking about projective models of K3 surfaces, concentrating on eco-singular strata. Then I will move to a detailed explanation of K3 surfaces, mainly focusing on quartics. Then we will talk about arithmetical reduction, and in the final part, in the conclusion, I will try to explain real models. What's a projective model of a K3 surface? It's in fact a map like this. Here, H belongs to a second homology group, and we call this H as the polarization. And projective models can be studied into two groups, like birational models and the hyperelliptic projective models. We can divide the birational models into three cases like this, where this polarization, square of it is 4. If square of H is 4, then the image of this map inside the projective space of dimension 2 is a quartic surface. If H square is 6, we obtain the image as a sextic, and if H square is 8, the image is an octic surface. When we come to hyperelliptic models, we can look at these two particular cases where H square is 2. In this case, the map is a degree 2 map ramified at the sextic curve, and in the second case where the square is 4, we obtain this map as a 2 map ramified at a curve C like this. Okay, let's talk about equisingular strata a bit. The equisingular strata is here, this space, and the M is the space of all projective models that I mentioned in the previous slide. We can collect all such models in this space M, which is a space of all models. And inside here, we have this smaller family, and it is the equisingular strata with a certain singularity set S. And this can be divided into its connected components that corresponds to equisingular deformation classes. And I restrict my attention in my work to this family, where I denoted by this sub-index 1. It is the space of all non-spatial quartics. So I reduced my attention to this family. I will explain what non-spatial means soon. And this family lies inside this equisingular strata space. If we want to look at the general picture again, here it is. The non-spatial quartics are this space. This non-spatial quartics lies inside the equisingular strata, and this space is inside the space of all simple models, which lies in the biggest space of projective space of dimension n. So this is the general diagram for us. Next, my main contribution is the classification of simple quartics. So I study quartic surfaces with simple singularities. What's a quartic? A quartic is a surface in a projective space of dimension 3 of degree 4. And a quartic is called simple if all of its singular points are simple. I gave a classification of simple quartic surfaces up to equisingular deformations. And crucial thing that enables us to study this classification problem was the fact that simple quartics are in fact K3 surfaces. So what are they and what are special about K3 surfaces then? Here is the definition for a K3 surface. It's a compact, complex, smooth manifold of dimension 2, which is simply connected and whose canonical class is 0. And if you look at the spatial properties of them, these two items summarizes what K3 surface, why they are spatial. So first of all, second homology group is isomorphic to this spatial lattice. So here U is the hyperplane and E8 is the famous root lattice. They are both even unimodular lattices and they have such signatures. And in total, they gave us this spatial lattice, which we denote by L, which is a unique even unimodular lattice of such a signature. And its rank is 22, which is the sum of these two numbers. And second thing that makes K3 surfaces as spatial is the fact that they cannot have singularities other than simple ones. Now, let's look at quartic surfaces as K3 surfaces. So I am working with a quartic surface X, which has singular points. So it is a singular surface. Well, when we blow up its singularity points, we obtain a smooth surface, which we denote by this. And this resulting smooth surface is in fact a K3 surface. So this is our main crucial motivation. And since quartics turns out to be K3 surfaces, we can study them by means of the tools coming with the K3 surfaces. And the most important tools are here, global theory theorems, surjectivity of the period map. These are two strong tools coming with the package of K3 surfaces. I am working with quartic surfaces with simple singularities. So let me talk a bit on them. What are simple singularities? They are of this type, ADE type singularities. And the most important thing about them is the following: they can be identified with the irreducible root lattices. And what is a root lattice then? It is a negative definite lattice generated by the elements of square minus 2. And since we can identify irreducible root lattices with the simple singularities, we will use the same notation for them as the simple singularities. Next, so I used arithmetical reduction to handle my classification problem. So my problem lies on the geometric side. So I have a quartic surface which has singularity points. This is my problem on the geometric side, and I found a way to transform my problem to an arithmetical word. So each singular point here give rise to an irreducible root lattice on the arithmetical side, and these irreducible root lattices lies in this spatial lattice that I mentioned before, which is of this signature. Here I emphasize the number 19 for some reason, we will understand soon. And here S is the singularity set, meaning that on my surface X, I have many singularity points. So this is the sum of all singularity points as a set. And in the arithmetical side, this is the corresponding part. That's why I denote it by the same letter. And this S, the lattice S, is the orthogonal sum of the irreducible lattices coming from each singular point. So this is the correspondence between the geometric problem and the arithmetical problem, and how we did the arithmetical reduction. And here, the minor number of our surface is defined as the rank of this root lattice on the arithmetical side. And since this root lattice is inside this spatial lattice L, its rank should be less than 19, because this is the negative definite part which corresponds to this. So that's why this minor number, which is the same as the rank of S, should be less than or equal to 19. And if it is 19, we call our surfaces as the maximizing surface. Here is more setting to understand how I handle my classification problem. So this is our sublattice on the arithmetical side. Then on this lattice L, we have also this hyperplane section. Then we will consider these two as together like this. And I will be dealing with this lattice now. And yeah, my surface X is called non-spatial if this embedding is primitive. So now I am restricting my attention to the non-spatial quartic surfaces. Okay, and yeah, this is my problem, classification of non-spatial simple quartics. And on the arithmetical side, I have the corresponding problem. So I reduce my problem to the arithmetical side, which is purely lattice theoretical. And this problem is the same as enumeration of primitive embeddings like this up to isometries of L. And this gives the arithmetical reduction of my problem. So instead of dealing with the classification problem on the geometric side, I will deal with the enumeration of such lattices, such embeddings up to isometries of L in the arithmetical world. So this is the same as the enumeration of all finite index extension like this, where T is the orthogonal complement of this lattice. And here is more details about the strategy of how I did the arithmetical reduction. Yes, we come up to this point. I am interested in their enumerations of all finite index extensions like this. And to enumerate them, first of all, we need to consider the existence of this orthogonal complement. This is what we need to do on the arithmetical side. And this part corresponds on the geometric problem, finding all realizable sets of singularities S. And then once we handle the existence problem, to enumerate them, of course, we need to look at the uniqueness of the orthogonal complement, and the corresponding part on the geometric side means that we find the connected components of the equisingular strata of non-spatial quartics. After we handle the existence and uniqueness part, which corresponding to these two parts on the geometric world, then finally we also look at the existence of real representatives in the real components of this strata. And we contributed two new examples to the literature of real strata without real representatives. So in fact, this page is the summary of the total summary of what we did, what I contributed to the literature. Let's talk a bit on real components. If a component D in our equisingular strata contains a real surface, then for sure it's a real component, but the reverse direction is not always true, meaning that there may be real components without any real surfaces. So this sounds a bit strange, but that in the literature, there can be found examples showing that the reverse direction is not true. Up to our work, this was the only example of a real component without any real surfaces. This example is given by Alexandrov and Ayşegül Akyol in 2015. And what we did, in fact, we developed an algorithm, a general algorithm, which can be applied for all models of all K3 surfaces.
Sorry interrupting you, dear professor, sorry interrupting you. Could you accelerate a little further, please?
Sorry? Yes.
Could you accelerate a little further, please? Your time is running out. Please.
Okay. This is my main result. So it works for all projective models, and we apply this algorithm to quartics and sextics. And in the quartics part, I find two new examples which has real components without any real surfaces. And in the cyclic part, this was the already known example, but I gave a simpler proof to this example by applying the algorithm that we obtained. And I thank you. I stop here and thank you for your attention.
Thank you very much for your exceptionally good talk, dear Professor. Çisem Güneş Aktaş from Atlak University of Turkey. Is there any question or remark regarding the talk of the professor? Please prefer the question and answer button below. Any? Since no question, then thank you, Professor Çisem Güneş Aktaş. You can.
I thank you for the
Yes. Thank you. You can close your screen share and video also. And I kindly invite Professor El-Hindi Hisham from University of Tahrir Mohammed of Algeria to give his excellent talk on harmonic maps between burger type deformed Sasaki metric. Professor Hisham, could you hear me?
Hello. Can you hear me?
Welcome, Professor. Could you please open your camera and share your screen?
Oh, yes, I am trying. Can you see the screen?
Yeah, excellent, Professor. Thank you.
Okay.
Now microphone is yours, Professor. Please go on and give your excellent speech. We are listening to you.
Okay. So I start. Okay. Hello, and I thank the committee for accepting my participation into this seminar. So our work is about harmonic maps between Berger type deformed Sasaki metric. So we are gonna start with some important definition about harmonic map. Then we go to the structure and the geometry on tangent bundle and defining the main two metric that we use, which are the Sasakian metric and the Berger type deformed Sasaki metric. Then we give some result about harmonicity of the map capital Psi between a tangent bundle equipped with the Berger deformed Sasaki metric and the tangent bundle equipped with the metric with the Sasaki metric. Then we do the opposite, which means we study the harmonicity of the map Psi between the tangent bundle equipped with the Sasakian metric into the Berger into a tangent bundle equipped with the Berger deformed Sasaki metric. Finally, we study the harmonicity of a map between two different tangent bundles, both equipped with the Berger deformed Sasaki metric. So, well, we start with the definition about what's a harmonic map. We first introduce the energy functional, which are given by E Psi, which is the integral of the norm of d Psi squared. And we also introduce a harmonic map, which is a critical point of the energy functional E in or Ek, which in this case K is a compact subspace of N. We also for a smooth variation Psi T, we give the definition d over dt of the energy functional is given by minus the integral h, which is the metric on the N, on the space N. And we give the tension field of phi as tau phi equal the trace of nabla de phi. So map is said to be harmonic if tau psi, if its tension field is equal to 0. Here we give the structure of the geometry on the tangent bundle for Riemannian manifold MG, an n-dimensional Riemannian manifold, and the Tm Pm is the tangent bundle, where P is the projection from Tm into M. We have the local chart U, Xi is a local chart on M. It induces a local chart on Tm, which is given by the reciprocal of the projection. We denote as a capital gamma the Christoffel symbol, and we have two complementary distribution on the tangent bundle, which are the vertical and the horizontal space, which are they are defined by the vertical subspace is given by the curve of dp. P is the projection map, and it is given by this formula. The same thing for the horizontal space. The direct sum of both space give us the second tangent bundle, the tangent bundle of order 2. We also define what is a vertical lift of a vector field X and the horizontal lift of vector Y, vector X. So now Sasaki defined the metric on such a tangent bundle, which is given by this definition. Here P is the projection as we saw before. And here we have the Levi-Civita connection on the tangent bundle. Here the hat nabla is the connection on the tangent bundle, and nabla is the connection, is the Levi-Civita connection on the Riemannian manifold. We have those results that are well known. Now, in our work, we equipped the Riemannian manifold M with a paracomplex structure. M must be even dimensional. It means that it has 2k, its dimension is written as an even number. So we can equip it with a paracomplex structure. A paracomplex structure is given by those definitions, is defined as phi square is equal to the identity, and the eigenbundle T plus M and T minus M are associated to the eigenvalue +1 and -1 of the paracomplex structure phi. A well-known result is also that a paracomplex structure becomes integrable if its non-genus tensor is equal to 0. The non-genus tensor is given by this formula. And we also need that the paracomplex structure must be compatible with the metric, which is defined as J phi x. Phi y is equal to Jxy, or equivalently, Jx phi y is equal to J phi x y. So these are the main definition that we are gonna use, main definition and proposition used in this work. Now, we equipped the Riemannian manifold with the almost anti-para-Hermitian, with the almost paracomplex structure, which give us an anti-para-Hermitian manifold, and Tn is tangent bundle. Here, the Berger-type deformed Sasaki metric is a deformation of the metric we saw before, which is the Sasakian metric. The horizontal here, it doesn't change. The change is in G, XV, YV, which before was equal only to XY, X, JXY, JXY. We added this deformation for delta is a constant, and U is the second coordinate of the point in Tm. A point in Tm is given by Pu, where U is the vector at the point P. And this metric is called the Berger type deformed Sazakian metric. The connection, the Levi-Civita connection in this tangent bundle, in the tangent bundle Tm, is given by those formula, where nabla tilde is the Levi-Civita connection on Tm, and nabla is the Levi-Civita connection on M. Here, alpha for the last equality, alpha is equal to J UU, which is the norm squared of U of the at the point PU. Now we go to the harmonicity, to the study of the harmonicity between the tangent bundle and equipped with the Berger deformed Sazaki metric, and the tangent bundle equipped with the Sazakian metric. So after calculation, we got that the top C is given by this formula. Here, top C, we have top C. We have a capital Psi, which is the map between Tm and Tn equipped with the Sazakian metric. Here we have that this Psi, the map between the two remaining between the two manifold, Psi is equal to capital Psi. So in order to study the harmonicity of capital Psi, we have to calculate the tension field of this map. And the formula is given as follows. Here, top C is the tension field of Psi, the map between the two between the two manifold. Rn is the Riemannian curvature in the space N. Div is the divergence of the second fundamental form of Psi. Here the notation, the trace between the trace of the map of the metric G, which is the metric on the first space. So the result is given by, we say that if a little Psi is harmonic, then the curvature, the Riemannian curvature is equal to 0. And also we have the second fundamental form is equal to 0. In this case, the only result that is important is that this value here is equal to 0 in order for capital Psi to be harmonic. Now we go to we studied also the harmonicity between the tangent bundle equipped with the Sazakian metric and the tangent bundle equipped with the Berger deformed Sazakian metric. And we got this result. Here, as before, top C is the tension field of the map C between two manifolds. And here it's supposed to be Rm, which is the Riemannian metric on M, not N. So we have this, the horizontal part is given by this formula, and the vertical form is given by this. Here, the nabla, Psi, is the second fundamental form of the map Psi. In order for capital Psi to be harmonic, we must have that the horizontal part and the vertical part are both equal to 0. So this is the result in order for capital Psi to be harmonic. So the horizontal part must be 0, and the vertical part must also be equal to 0. Last, we have we study the harmonicity between two tangent bundle and both equipped with the Berger type deformed Sazakian metric. Calculating the tension field of capital Psi, we got this result. Here, we divided it in three parts. The first part is the horizontal part. with the torsion field of psi, the may between the two manifold, and Rn is the Riemannian curvature in M. The horizontal part, the vertical is given by this. The two vertical parts. The first vertical part is for the metric G, and the second one is related to the metric H on N. So the first is G for the first space, and H is the metric in the second space. So we obtained this result for the tension field. And as before, in order for this capital Psi, the may between the two tangent bundle equipped with the Berger deformed Sasaki metric, here we have phi and phi prime, which are two different paracomplex structure in each space. In order for this map to be equal to 0, we must have that the horizontal part equal to 0, the vertical part with the G metric must be equal to 0, and also the second vertical part with the metric on the second space must be equal to 0. And here are some how do we say it, reference that we use it in our work. Thank you.
Thank you very much for your informative talk on the special harmonic maps, dear Professor Hisham. Is there any question or comment regarding the presentation of the professor? You can use the question and answer button below on your screen.
How do we skip?
Since there is no any question or
it's the first time
comment.
I use Zoom, so I don't.
I will close your share, I think, Professor Hisham. Thank you a lot for your contribution, Hisham.
Thank you. You're welcome.
Thank you. Now, I can invite Professor Rafael Lopez from University of Granada of Spain to do his excellent talk on singular minimal surfaces and perfect domes in architecture. Professor Rafael Lopez.
Okay.
Can you hear me?
Okay. Do you hear me?
Yes, Professor. Could you please share your screen?
Okay. Please a moment.
By the way, it's a great pleasure and honor for all of us to have you here, Professor.
Okay.
Maybe you can share full screen.
Now, I don't know if I begin now or not because the time is.
It is not full screen, but you can make it full screen by pressing Ctrl and L. Please, Professor.
Then now I begin. Do I begin?
Yeah, Professor.
Okay.
You can go on, please.
Okay. Thank you. Okay. Good morning, everybody, and thank you to the organizers to give me the opportunity to participate in this seminar.
Sorry, Professor, interrupting you. Could you please share your screen, full screen?
Now it's better.
Control L, I think.
Okay, it's okay.
No, it's not full screen at the moment. As far as I see.
Moment, please. Don't know how to. Sorry. Please.
Maybe you can use the Control and L at the same time.
Control
L. Lopez, L. Control L.
A moment, please. Now is okay now?
No, Professor. Please Control and L at the same time. Please. Control and L. Anyway, I think it is readable, your slide. You can go, Professor, please. Thank you.
Now, it's okay?
It's not full screen, but I can read your slides, Professor. No problem. You can go on, please. The microphone is yours now.
Yeah, but
thank you.
Okay. Moment, please. Okay. Well, I begin with the question is what the shape of a hanging chain? The answer is known, is the catenary. Here you fix the curve, the length of the curve, and also you fix the endpoints of the curve. And this is the equation of the catenary. The catenary is the model for the construction of arch. Why? Because here the forces on the curve are tangent to the curve. And then when we turn upside down the curve, then these forces, these tangent forces transforms into compression forces. And then this gives rigidity to the arch. This is equivalent to say that the catenary is the curve with the lowest center of gravity among of curves with the same endpoints and the same length. Okay, and now this is the shape of catenary. This is electric cable. In this case, it's different. It's not this curve is not a catenary, it's a parabola, because in this case, the curve is holding the rod of the bridge. This is a difference between both curves, between catenary and parabolas. And now I ask, what is the two-dimensional problem? Now the initial data is a given closed curve and a given area. And then the question is, what is the shape of a hanging surface with this boundary curve and with this area?
Sorry, interrupting you, Professor Lopez.
Yes.
I'm seeing your fourth slide only. It's not moving in my screen.
The previous slide.
Maybe you can check the slide. I'm only seeing your fourth slide. It's not moving at the moment.
It's okay?
No, still the fourth slide is on the screen.
Sorry.
Maybe you can close and reshare. You can reshare, please, Professor. Sorry, interrupting you.
It's okay now?
Can you move forward or backward, please?
Sorry?
Can you move the slide forward or backward, please? Thank you. It's correct now. Thank you, Professor.
Okay. Okay. And now, okay, the question is, what is the shape of a hanging surface? Okay. This is the energy of the surface. I explain why. This part is the weight of the surface. Z is the height with respect to a reference plane. In this case, is the plane of equation Z equals 0. Sigma is the density per unit of area. And in this part, this is the Lagrange multiply given by the prescribed area of the surface. And now I use calculus of variation. Because the problem is local, then I consider surfaces which are graphs of a function u defined in a domain of the xy plane. And now here I consider a variation of the surface. Phi is a function vanishing along the boundary of the domain. This is the energy. This is, I assume that the density is 1. du is the gradient of the function u. And now I consider the critical point of the energy. And then this is now is in some sense is typical in calculus variation. This is the Lagrangian of the energy. And then this is the Euler-Lagrange equation of the surface. The subscript means the derivative with respect to the variable x and y. Okay. After a vertical translation, I assume that lambda is 0. Okay. And this part is the divergence of the gradient divided by this function. And now I can give a geometric interpretation of this equation. This part, the left-hand side, is two times the mean curvature of the surface. On the right-hand side, u is the third coordinate of the position of a point of the surface. And this part is exactly the third coordinate or the unit normal vector of the surface. And now this is the equation of the critical point of the energy. And then I call these surfaces singular minimal surfaces. The problem is possible that the problem has no solution because the problem of to find minimizer is hard. Here, this is one example. I fix the boundary. The boundary is the unit cycle, and the area is 2 pi. And now I consider a uniparametric family of surfaces like this. Is the surface part? This is the boundary. The surface is a cone with this boundary, and the height is so the area is exactly 2 pi. And now I reduce the radius of the cone. I increase the height of the cone, and the surface is this annulus together the cone. And then the area is 2 pi. The boundary is the same, is the unit cycle, but the center of gravity goes to minus infinity. In this case, there is no minimizer of the problem. Of course, people could think that there are many cupula that don't satisfy the singular minimal equation. I mean, this equation. Okay, this is the ideal model from the mathematical viewpoint. But in architecture, there are other problems in the construction, not only about the design of the beauty, and also, for example, about the elasticity of the material. Okay, this is famous cupola, and here there are other using minimal surfaces, and here surfaces with constant mean curvature, because in this case, for the Eskimo, the igloo, the volume is fixed and the area must be minimum. Then the solution is the half sphere. Okay. And now I ask about example of singular minimal surfaces. For this, I consider two types of geometry: cylindrical surfaces and rotational surfaces. This is in this case, for cylindrical surfaces, V is the direction of the ruling of the surface. And then if you suppose that the surface is singular minimal surface, then the rulings of the surface must be orthogonal to the direction of the gravity. And this is the equation of the generating curve. In this case, this equation is exactly the equation of the catenary. The Spanish architect Gaudí used catenary arcs to construct corridors in different buildings. In this case, this is the catenary curve. Okay, of course, you have to turn upside down the catenary. Okay. For rotational surfaces, the result is, in some sense, is surprise, because people could think that the rotation surface the rotation axis of the surface must be parallel to the gravity. Of course, this is one type of the solution. And there are two types also of rotational surfaces and singular minimal surfaces. One case is that the rotational axis must be parallel to the gravity. And this is the equation of the generating curve. But also there are other kinds of surfaces. In this case, the rotation axis is horizontal. In some sense, opposite to the mind of the people who think about the cupola, because the people think the rotational axis must be vertical. But also there are rotational singular minimal surfaces where the axis is horizontal. And this is the equation of the generating curve. It is similar that the catenary, but the only difference is that here appears the number 2, not 1, like in the catenary. This is the description of the rotational surfaces of the first type when the rotation axis is parallel to the gravity, and this is the shape of the curves. Okay, and also in this case is when the rotation axis is horizontal. This is the generating curve of the surface. This is the solution of this equation. In this case, the curve is defined in a bounding in a bounding interval, and the curve is asymptotic to the end of the interval, go to infinity. And this is, I think, this is the surface, the rotational surface. And then when we turn upside down the surface, then here I obtain the ideal model of the cupola. The difference is that here the rotation axis is horizontal. Now I ask about is it possible to use other surfaces to be useful to the construction of cupola, not being singular minimal surfaces, because rotational singular minimal surfaces are difficult to design because we only have numerical approximation of the solution of the equation. This idea was thought by Gaudí because Gaudí, in the construction of cupola, he thought that the solution is not easy in some sense. And then he used models of cupola to construct real cupola, in this case, in the Sagrada Familia. Okay, but for people who think that there are two candidates to be model of cupola, no singular minimal surfaces, okay? One of the surface is I call catenary rotation surface. The catenary rotation surface is only to rotate a vertical catenary, okay? And the other, okay, why? Because if the catenary is the model for curves, people could think that is the model for the two-dimensional case. The other surface is the paraboloid. You rotate a vertical parabola. The advantage of paraboloid is because the paraboloid is given by polynomial, and then it's easy to construct from the architect viewpoint. Both surfaces are not singular minimal surfaces, okay? And then I ask, what is the difference between the center of gravity with respect to the ideal model? And then this is the equation of the rotational singular minimal surface. Okay, and then here I impose the initial condition. This is the lowest point of the surface, and this condition means that it's orthogonal to the rotation axis. Okay, and then I fix the boundary, and also I fix the area of the surface, and then I compute the height of the center of gravity. And now I do the same with the other two candidates. The first candidate is the catenary rotation surface. This is the profile of the surface, and then I impose the boundary condition. I compute the area. It's possible to compute the area explicitly, and also the height of the center of gravity. Okay? And the same with the paraboloid. This is the parabola. I impose the boundary condition. I compute the area, and also I compute the center of gravity. And now I want to compare the center of gravity of the three surfaces: the ideal model, the catenary rotation surface, and the paraboloid. And then this is the table of comparing of these values. And here there are different radius of the boundary. This is the area of the surface. These data are given, are prescribed. This is the height of the center of gravity of the ideal model, and here of the catenary rotation surface and of the parabola. If you look, the difference is nothing, or is very, very, very small. How to measure this, the difference? Now here is the percentage of the difference between the height of the center of gravity with respect to ideal model with respect to the height of the surface. And then the percentage is less than 1%. 1%. This is the computation for the catenary rotation surface. In this case, is for the paraboloid. Even more, you look that the height of the center of gravity of the paraboloid is less than the catenary rotation surface. It's curious because in the one-dimensional case, the catenary, the height of the center of gravity is less than the parabola, because the catenary is the ideal model. Then the conclusion is, of course, the center of gravity of the model is less, but of the paraboloid is less than the catenary rotation surface. And the deviation is less than 1%, and is better in the case of paraboloid. Also, this deviation is no increase with respect to the area of the radio, because here increase until some value and after decrease. Okay, and here you can look the catenary rotation surface, the ideal model is the blue color, and the paraboloid. And be careful because here the difference between the lowest point is high, but we are comparing the height of the center of gravity. It's not the lowest point of the surface. And now, to finish the talk, I asked the problem about the stability of the singular minimal surfaces. In this case, about cylindrical singular minimal surfaces. The problem is motivated by the theory of surfaces with constant mean curvature, because if you consider a cylinder of given radius, if the length is large, then the surface is unstable, and then in this case, it appears liquid drops. And then I asked the same problem for cylindrical singular minimal surfaces. If you recall, the generating curve is the catenary, okay? And then this is the parametrization of the surface. A is the amplitude of the surface, and L is the length of the surface. And then the problem is I fix A, then it is possible to find L such that if L is bigger, then the surface is unstable. Okay. The definition of stability is that the second derivative of the energy is non-negative. Okay. And now we need to compute the second derivative, and then the second derivative is this integral. Okay. Where L is the Jacobi operator is given by this part, okay? This is the Laplacian on the surface, and this is the gradient on the surface. Phi is a function vanishing along the boundary. A is the second fundamental form, okay? This expression is difficult to compute, but if now I consider phi by separation of variable, then this part reduces a lot. This part is exactly this function where h is the hyperbolic cosine, is the generating curve of the surface. Okay, and now I had to impose that this function vanishes along the boundary, and then for t is the length of the surface, then I consider the sign of this function. This g vanishes on t equals 0 and t equals L, and then I put in this integral, okay? And then this is the integral. This is minus, this part is positive. Because I ask about instability, I need that this part is positive, okay? And now the other function f, I consider a translation of the hyperbolic cosine, okay? To vanish along the boundary. And now I put here, and now I have to compute this integral, okay? This integral is separated in two terms. One term depends on the function of the value a, and here of a and L. This is the explicit computation of the integrals. The second here, if you fix a and L go to infinity, then this part go to 0, okay? And then this is the theorem. The theorem says that if you fix the amplitude after this value, then if the length is bigger, then the surface is unstable, okay? The proof is the following. After this value, the first integral, the first integral, this is the function. If a is bigger, then it's positive, okay? But the second integral, if L is big, then it goes to 0, and then when you sum, is positive. For this reason, the surface is not stable. Okay, I finish the talk. Thank you.
Thank you very much for your interesting and stimulating speech, Professor. I would like to ask our distinguished audience, is there any question or remark regarding the presentation of Professor? Professor Eren Aydın, thank you for the nice talk.
Okay, thank you.
Thank you, Professor Lopez. Thank you for your contribution.
Okay.
You can stop your screen share, please. Now, I'd like to invite Professor Osman Alagöz from Bilecik Şeyh Edebali University of Turkey to give his excellent talk on approximation by sampling control series in weighted space of functions. Professor Osman Alagöz, do you hear me?
Yes, I hear you. Thank you very much.
Yes, Professor. Could you please share full screen?
Yes.
It's okay, Professor. The microphone is yours now. You can continue your presentation. Thank you a lot. Please go on.
I thank you so much. Thank you so much. Hi again, dear participants. My name is Osman from Bilecik Şeyh Edebali University from Turkey. Before starting my presentation, I'd like to make an explanation. Normally, this work would be presented by Metin Turgay, one of the collaborators of this work. But since he got COVID and have some health problems, as one of the co-authors from of this work, I will talk about today for you. The main topic is approximation properties, approximation behaviors of generalized sampling series and sampling control-which, especially sampling control-which operators, such as pointwise and uniform convergence properties and rate of convergence and a Voronozhskaya type formula are the main titles of this presentation. Let me talk about something in introduction. Sampling operators are very useful tool in order to provide an approximate version of the classical sampling theorem. This version mainly depends on generalized sampling series defined by in the equation 1, as you see. Here, f is a function from R to R, and chi is the kernel function. Satisfy some certain condition. Here we show the relation between the generalized sampling series and their Kantorovich forms. How we construct this relation, you see on the page. This is the page why we use generalized, why we use sampling Kantorovich operators in weighted spaces. Because we are enlarging the class of functions instead of the space of uniformly continuous and bounded functions. So this is an important step. Okay, let me give you some basic definitions and notions about the study. Firstly, I want to give the definition of the kernel, which we use very much. A function chi is from R to R is called a kernel function which satisfies some certain conditions, chi1, chi2, and chi3. These are about absolute and algebraic moment of this kernel. And here is a useful lemma we use in the main theorems. As you see, there is a limit here, and this limit goes to 0 if the kernel satisfies chi1 and chi3 conditions for every delta when is bigger than 0. And here we have a condition also such that absolute moment of chi is finite. You see, it's finite. And the definition of weight function, it is also very important concept for our study. Here, the function omega tilde is called a weight function. On the whole real axis, it is continuous, of course, and positive. We consider our weight function as 1 to 1 plus x square, as you see, where x is a real number. And here you see some related function spaces in weighted function spaces. And the norm of about the space. Okay, let's continue. Here, again, there is an important concept for us, modulus continuity, weighted modulus of continuity, and the definition of is given in 5, as you see, and some properties about weighted modulus of continuity was given in this lemma. As you see, it is monotonically increasing function of delta. There is a limit goes to 0, and there is a special inequality. In this remark, using the inequality 6 with lambda, taking absolute value of y minus x to delta, we can get an other inequality in the bottom of the page. You see, we use this in the next page. Especially in the details of the proof. A useful result for us. If we choose delta less than 1, then we obtain this inequality difference between fy minus fx. Okay, let me go on. Let's give the main results. Here, there is a theorem shows us generalized Kantorovich operator is a linear operator. And the form of the norm of operator. And the details of the proof here. I will skip these pages. Okay. The main theorem of this section can be stated as follows. Convergence results are given, and we omit the details of the proof. Okay, let's talk about rate of convergence for our operator, Kantorovich operator, via modulus of continuity. To do this, we need to give a lemma. Firstly, this lemma gives us some results about weighted modulus of continuity. Here are some results. Here is one of the main theorems of this section helps us considering the rate of convergence. And this is another one. Yes, this is another main theorems. Determines an upper bound for difference between the operator k and function of f. The next theorem determines an upper bound for difference of operators, generalized sampling operator and Kantorovich operator, and presents us an estimate for difference of the operators. Now, I want to show the Voronovskaya type formula, but firstly, I need to give the definition of algebraic moment and algebraic moment of order J of a kernel G by small m G, as you see, the definition. And we also need these two extra conditions on our kernel, varphi 4 and varphi 5. Now, let's give the definition of the known Taylor expansion with its remainder function. Here, we give an estimate about the remainder, which is given in 16. And here is our Voronovskaya type formula. Yes. And these are our references which we used in this work. Thanks for your attention.
Thank you very much for your exceptionally good talk, Professor Osman Alagöz. Is there any question or remark regarding the presentation of Professor? I think there is no. You can close your screen share, Professor.
Okay,
next,
thank you.
Thank you, Professor, for your contribution.
Not at all,
next,
I think.
Thank you, Professor. And now, I kindly invite Professor Bilgilali Gerici from University of Meshkara of Algeria to give his excellent talk on three-dimensional C2 manifolds. Professor Gerici, do you hear me?
Yes, I'm ready.
Yes. Could you please share your screen? It's okay. See, at the moment.
It's okay now.
No, Professor. I couldn't see your screen at the moment.
Okay.
You can use the green button below your screen. Green one. At the middle bottom of your screen.
It's okay now?
No, Professor. I'm seeing only you at the moment. I couldn't see your screen. There is a green button at the below of your screen. Share screen.
It's okay now?
No, Professor.
You listen to me?
Yeah. I see only you on my screen. It's okay now, Professor. And could you please make it full screen? Thank you, Professor. It's excellent now. Now the microphone is yours, Professor. You can continue your speech. Thank you, Eda.
I can start now?
Yeah, yes, Professor, please. Yes, please.
Okay. Bismillah. Assalamu alaikum. My name is Beljilali Ghrisi. I am from University of Mascara, Algeria. My presentation is about a class of almost contact metric manifolds called by us corner manifolds. In this work, we present the class of three-dimension C12 manifolds, which are non-normal almost contact metric manifolds. Almost contact metric manifolds are odd-dimensional manifolds, unlike complex manifolds, which have dimensional. In this talk, firstly, we give definition and we study some fundamental properties. Secondly, we show there is one-to-one correspondence between C12 manifolds and Kählerian manifolds. Thirdly, we construct some relations between C12 and other well-known manifolds as cosymplectic and Kenmutsu manifolds. Finally, as an application, we study such structures on three-dimensional Lie groups. And almost contact metric manifolds consist of a global vector field Xi and one form eta, such that eta Xi equal 1, and one tensor field Varphi, such that Varphi square x equal minus x plus eta x Xi. In addition, if Varphi is G compatible, it means that for all x and y vector field on M, G Varphi x Varphi y equal G x y minus eta x eta y. In this situation, we say that Varphi G eta G is an almost contact metric structures on M. Any almost contact metric manifolds has a fundamental two form. We denote phi, and this fundamental two form defined by this formula. the normality of such structure of almost contact metric structure is measured by the tensor N1 defined by this formula. And for the integrability, we say that the structure is integrable if and only if the Nijen-Hayes tensor field vanish. Metric structures. There are a lot of classification of almost contact metric structure. Classification of Chinia-Gonzalez is one of the most important classification. In this classification, there are 12 classes of almost contact metric manifolds. But in dimension 3, these 12 classes, reduce to only 5 classes. Class of cosymplectic, class of beta-Kenmutsu manifolds, class of alpha Sasaki manifolds, and C9 manifolds, and C12 manifolds. All this, most of research related to almost contact metric structures is concerned with the normal ones. It means the first 3 ones. For the last 2 classes, we can never be normal. There are only few papers on this subject. For our subject, 3-dimensional C12 manifolds, in classification of Chinia-Gonzalez, C12 manifolds are defined by this formula. And this one is equivalent to this formula. If we put omega equal nabla she eta and psi equal minus nabla she, the formula 4 becomes like this. We notice that psi is orthonormal to she. And this structure, C12, the class of C12 manifolds, is never normal because nabla she no 0. We have this definition. An almost contact metric manifolds is said to be a C12 manifolds if and only if this formula satisfies with omega equal minus nabla she eta and psi equal minus nabla she. This definition is true for the dimension 2n plus 1. If we put y equal she in the formula 6, we get this equation. And if we replace the 7, the formula number 7 in 8 and 9, we get d phi equals 0 and d eta equal omega wedge eta, which give d omega equal 0. D is the exterior derivative. And we can give another definition by using the one form and the second form, the fundamental form. An almost contact metric manifold is said to be C12 manifolds if there exists a closed one form omega which satisfies d eta equal omega wedge eta and d phi equal 0. In addition, if the Nijen-Hayes tensor vanish, we say that M is a C12 manifold. Okay. Notice that psi here is perpendicular to xi, and psi is not necessarily a unit vector field. We get immediately that the set xi psi Vafi psi is an orthogonal frame, and these three vector fields is global. That is why we call this manifold the corner manifold. It's like the corner on the football stadium. That is why this classes of manifolds is called by us corner manifolds. Okay, for the three-dimensional now, we have this theorem, this main theorem. Any three-dimensional almost contact metric manifolds is a corner manifolds if and only if nablash x xi equal minus eta x c. For the proof, suppose that M var phi xi eta g is a corner manifold, then we have this formula from the definition, first definition, putting y equal xi, we get this formula. Conversely, suppose that x xi equal minus eta x psi, and we know that Orszak prove that in three-dimensional almost contact metric manifolds, the formula 13 holds for every three-dimensional almost contact metric manifolds. Just replace this supposition nabla x xi here and here, we get this formula. Okay. We give now some examples. The first examples related to the Kählerian manifolds. We use the product, warped product metric. We give, firstly, we give some notion about on the Kählerian manifolds. G is a tensor, a one-one tensor field, such that G square equal minus identity, and H is a Riemannian metric compatible with the structure G, and the Kähler form omega defined by this formula is closed, plus the Neugenheis of structure, complex structure is 0. For these four conditions, we say that N, G, H is a Kählerian manifold, and it's an space known in the complex geometry. We have this theorem. Let NGH be a Kählerian manifold and rho a non-zero function. Then the warped product space M equal N product L, real line, have corner structure. For the proof, just putting this deformation or this this structure on Kählerian manifolds. Suppose that we have a Kählerian manifold and GH. We define a new metric on the product N times R or L. G equal H, please, exponential 2 rho dt square and xi eta var v x equal gx and var v partial t equal 0. We can prove that var v xi eta g is an almost contact metric manifold, and we have directly d eta equal d rho wedge eta. which implies omega equal d rho. And notice that the omega equals 0 is exact. Also, the fundamental to form phi of almost contact metric structures is defined by this formula, and we get phi equal omega, to form of almost contact metric, equal to form of scalar. Since the omega equals 0, then the phi equals 0. With this condition, d eta and d phi equals 0, we conclude that var phi c eta is an almost corner manifold. In addition, since NGH is Kähler manifold, it means NG equals 0, which implies that N phi var phi equal 0. And then the structure and var eta G is one parameter family of corner manifolds. The second set of examples are closely related to beta Kenmutsu. Beta Kenmutsu is an almost contact metric manifold characterized by these three conditions: d eta equals 0, d phi equal d phi equal to beta eta wedge phi, and n1 equal 0. With this deformation, var phi tilde equal var phi, she tilde equal this function she, and eta tilde equal exponential rho plus tau eta, the new metric defined by this formula, where rho and tau is two functions on M. One can check that this is an almost contact metric structure. The new structure is an almost contact metric structure. So the fundamental to form phi tilde is given by this equation. We can prove it. Phi tilde equal exponential rho phi. So we get the eta tilde equal this expression, and the phi tilde equal this expression. Therefore, if the initial structure is beta Kenmutsu, we can use this condition here, and here. We get this system, the eta tilde and the phi tilde. Just to get a corner manifold, just the eta tilde b equal omega wedge eta tilde and the phi tilde equal 0, which implies the theorem, the following theorem. Let M var phi she eta G be an almost contact metric manifold. If M var phi she eta G is a beta Kenmutsu manifold with eta equal -1 over beta d rho, then the new manifold is a corner manifold with omega tilde equal d rho d tau, and psi tilde is gradient rho. Secondly, if M var phi xi eta is a cosymplectic manifold, theta, it means that beta equals 0, and rho is a constant, then the new manifold is a corner with omega tilde and psi tilde equal d rho and grad rho respectively. So for the last section, we find the corner structure on three-dimensional Lie groups. In this section, we study corner or three-dimensionally algebra. Here is the list of non-abelian three-dimensional algebra along with their defining Lie bracket equation given by Patera and Sharp in reference 3. We have 9 algebra non-abelian. So we know that psi is not necessarily unitary. Putting V equal psi over norm of psi, we get immediately that chi V var phi is an orthonormal frame. We refer to this, we call this basis as fundamental basis. Any any three-dimensional corner manifold has a fundamental basis like this. Using this frame, one can get the following proposition. Nabla is the Levi-Civita connection. For any 3D corner manifolds, we have the complement of Nabla. It means that the 3 corner manifold is completely controllable. We will investigate the existence of corner structure on each Lie algebra A3I, and it's sufficient here to find the Xi and V. For instance, an almost contact metric structure on a Lie group G is said to be corner structure if and only if nabla x xi equal minus eta x xi equal minus exponential rho eta x v. We conclude that the existence of the corner structure is equivalent to this 3 conditions. Nabla xi equal minus psi and nabla v xi equal nabla va phi v xi equal 0. So for the first algebra A31, we have the bracket from by Kotzil's formula. The covariant derivatives of the basis element are as follows. So we can find this condition. Nabla xi. It means nabla ei. For nabla e1 equals 0, nabla e2 equals 0, nabla e3 equals 0. It means that there is no corner structure on this algebra. For the second algebra, from this complement, nabla e1 equal minus e3, it's possible to get a corner structure with psi equal e3. Also here. So nabla e2 e1 is not 0 and e1 e2 is not 0. Then there is no corner on this algebra 2. For the third algebra A33, we have the covariant derivative of the basis elements. So here we have 2 corner structure. The first is for xi equal a1 and the psi equal e3. The second is for xi equal e2, psi equal e3 here. Others equal 0. So algebra 33, on this algebra there exists 2 corner structure. For the fourth one, with the same method, there exists 2 corner structure. for this algebra, A3, 5, also there exist two corner structures. Notice that here psi is not unit vector field equal A, E3. So for the rest of the algebra, there is no corner structure. This is some reference used in this presentation. And thank you for listening.
Thank you for your notable talk, Professor. I would like to ask the distinguished audience, is there any question or comment regarding the presentation of Professor? Please prefer the question and answer button below. Seems there is no question, Professor. Thank you a lot for contribution, Professor Gage. Now you can close your screen.
Thank you.
Dear participants, now we will have a break of approximately 8 minutes. And in the next session, Professor Ramazan Yaşar will moderate the session. Thank you a lot.
Dear participants, welcome to session 16 of our webinar. I am Ramazan Yaşar, the moderator of this section. Now, I would like to invite the next speaker, Professor Busra Mertci from Mascara, Algeria, to do her talk.
Thank you, sir. I will.
Wait a minute.
Yes.
Could you please open your
Yes.
presentation, first of all?
Yes, of course, sir. Yes.
And
is it clear?
Yeah, it will be full screen.
Yes. That's it.
Okay. The link and other facilities for the online presentation seems to be okay. It is a really great pleasure for all of us to have here Professor Mertci for the noticeable talk on new type of matrix deformations and applications to biharmonic maps. Professor Mertci, do welcome to your presentation, please.
Thank you, sir. So before I start, I would like to say to the committee, thank you so much for giving us this opportunity. And now I will present my work, which is new types of matrix deformations and applications to biharmonic maps. And it's my work, me and my supervisor, Professor Ahmed Mohamed Sharif, and we both are from Mascara University of Algeria. So the summary contains, first of all, an introduction where I will define the harmonic and biharmonic maps. Then I will go to the deformations of the matrix. And finally, we will see all of us the applications to biharmonic maps. So an introduction. So we have two Riemannian manifolds, M equipped with the metric G and N equipped with the metric H. And the energy functional of a map varphi, a differential map varphi, is defined by the equation number 1, which is equal to 1/2 integral on M, the squared norm of the differential of the map varphi Vg, where this is the Hilbert-Schmidt norm of the differential of the map varphi, and Vg is the volume element on the manifold M. So a map is called harmonic if it is a critical point of the energy functional, that is, if it is a solution of the Euler-Lagrange equation associated to 1, which means that a map is harmonic if it satisfies this equation, which is number 2. That means that the tensile field of the map varphi, which is given by the trace of nabla d varphi, is equal to 0. It vanishes, where this frame is an orthonormal frame on the manifold M equipped with the metric G. Nabla M is the Levi-Civita connection of M equipped with G, and Nabla varphi denote the pullback connection on the inverse tangent bundle of the manifold N. So harmonic maps are solutions of a second-order nonlinear elliptic system, and they play a very important role in many branches of mathematics and physics, where they may serve as a model for liquid crystal. One can refer to these references for background on harmonic maps. A natural generalization of harmonic maps is given by integrating the square of the norm of the tension field. More precisely, the B energy functional of a differential map varphi is defined by this equation. E2 applied to varphi is equal to 1/2 the integral of on M of the squared norm of the tension field of varphi Vg. So now we go to biharmonicity of any differential map. So a map varphi is called biharmonic if it is a critical point of the B energy functional, that is, if it is a solution of the Euler-Lagrange equation associated to 3. So we have the B tension field of varphi is given by this equation. It is equal to minus the trace of the curvature tensor of the manifold N applied to tau varphi, d varphi, minus the trace of nabla varphi squared applied to tau varphi. So a map is biharmonic if this bitangential field, vector field, is equal to 0. So clearly, harmonic maps are biharmonic. And then G.Y.Jiang proved that if M is compact without boundary and the sectional curvature of N is negative, then any biharmonic map is harmonic. So it is interesting to construct biharmonic non-harmonic maps, and we refer the reader to these references for other examples and different approaches to their construction. Now we move to deformations of metrics. So we have M is a Riemannian manifold equipped with a Riemannian metric G, and F is a smooth function on N, such that G tilde is equivalent to G minus dF. Tensorial product dF is a Riemannian metric on N. We have G tilde applied to X comma Y is equal to G applied to X comma Y minus X applied to F, Y applied to F, where X and Y are vector fields on the manifold M. So note that if M is a connected M-dimensional manifold, a continuous function F defined from M to R is called proper if the inverse image of K by the function F is compact for every compact K in M. A Riemannian manifold M is complete if and only if there exists a proper smooth function F, such that this formula is this deformation metric, which is given by G minus dF, tensorial product dF, is positive definite. In the seminal work, we obtain the following results. So the first theorem, we have always M is a Riemannian manifold and F is a smooth function on M. If the squared norm of the gradient of F is equal, which is equal to G applied to gradient F is smaller than 1 on M, where the gradient F is the gradient vector of F with respect to the metric G, then the deformation metric G tilde is a Riemannian metric on M. Moreover, if nabla tilde denotes the Levi-Civita connection of M equipped with the metric G tilde, we have the covariant derivative on the manifold M equipped with G tilde is given by this equation, where nabla is the Levi-Civita connection of M equipped with G, and Hess F is the Hessian of F with respect to the metric G. Now we consider the curvature tensor R tilde, respectively the Ricci tensor Ricci tilde of M equipped with G tilde, and then writing R for the curvature tensor, respectively Ricci for the Ricci tensor of M equipped with G. So we have the following results. Theorem number 2. So M equipped with G is a Riemannian manifold, and F is a smooth function on M, such that the norm of the gradient of F is smaller than 1 on the manifold M. For every vector field X, Y, Z on the manifold M, we have that the tensor curvature R tilde on the manifold M is given by this equation, equation number 7. And as you can see, there is a relationship with the tensor curvature R tilde and the tensor curvature R. And to obtain this result, we have a simple calculation. We use the property of the definition of the tensor curvature and the definition of the deformation metric that we have mentioned before. So we have the theorem number 3. M equipped with G is a Riemannian manifold, and F is always a smooth function on M, such that the norm of the gradient of F is between 0 and 1 on M. Then the Ricci tensor of M equipped with G tilde is given by this equation. And the same thing, the Ricci tensor tilde applied to X has a relationship with the Ricci tensor applied to X for all X vector field in the manifold M. So the main idea of the proof of the previous theorem or the above theorem is to compute the Ricci tensor of MG tilde is that we need to compute this the following equation, And we use two orthonormal frame. We have this one and this one with some characteristics. And by using theorem number 2, we obtain the above result. So it's so simple. Now we move to the last section. This is the most important section of our work. Here we will consider the effects of the deformation of the codomain metric as regards harmonic and biharmonic mappings. And we will try to construct new examples of biharmonic, non-harmonic maps. So we have theorem number 4. We have Varphy is a map between the manifold M equipped with the metric G and N equipped with the metric H. So here we assume that this map is harmonic. And then we give the deformation metric of the codomain H tilde, which is equal to H minus df tensorial product df. And f is a smooth function on the manifold N, such that the squared norm of the gradient of f, which is equal to h applied to gradient f, comma, gradient f, and equal to 1/2. So we have, if the function Laplacian of f circle Varphy is a non-null constant on M, then the map, the new map, which is given by, which is defined from the manifold M equipped with G to N equipped with the new metric H tilde is proper biharmonic if and only if the gradient vector of f is a Jacobi field along Varphy, which means that the gradient of f circle Varphy is an element of the kernel of the Jacobi operator corresponding to Varphy. And what we mean by proper biharmonic map is that this map is biharmonic, non-harmonic. So we have as an example a map defined from a manifold M, which is equal to Rn, and Rn is equipped with the usual metric, to the manifold N, and the manifold N is equal to the n-dimensional hyperbolic space. And this is how we construct the construction of this map. And we have the function f applied to y1 until yn, which is equal to the root of 2/4 yn squared. So a straightforward calculation shows that, so after some computation, we find that the squared norm of the gradient of f is equal to 1/2, and the Laplacian of f circle Varphy is equal to n-1 over the root of the squared root of 2. And then the gradient of f circle Varphy is equal to this vector field. So this vector field, all the components vanish except the last component. It's different from 0. And the Jacobi operator of corresponding to Varphy of gradient of f circle Varphy is equal to 0. Thus, with respect to Riemannian metric, we find the deformation metric, which is given by h tilde equal to h minus df tensorial product df, and equal to this. So as you can see, this map is biharmonic, non-harmonic, and here we have the tension field of this. It is obvious that the tension field of this map is not null, because we have the last component is equal to minus the root, the squared root of n-1 over xn squared plus 1. So this application is biharmonic, non-harmonic. We have as a remark, Varphy, this application or this map Varphy is harmonic, and h tilde is equal to h minus df tensorial product df. F is a smooth function, this time on n, such that the gradient, the norm of the gradient of f is smaller than 1. Then the map, the new map, which is defined from the manifold M equipped with G to n equipped with the metric h tilde is harmonic if and only if f circle varphy is harmonic on the manifold M equipped with G. So for finishing, we have corollary. We have M equipped with G is a Riemannian manifold, and let F is a smooth function on M, such that the norm of the gradient of F is equal to 1/2, and the Laplacian of F is equal to a constant K. Then the identity map from M equipped with G to M equipped with G tilde is biharmonic if and only if it is harmonic. So that's it. These are our references. And thank you for your attention.
Okay, we thank to Professor Mehdi for her nice presentation. If there is any question or comment, please use the question and answer button. Let me check. Okay, there seems no question or comment. So we thank again to Professor Mehdi. Stop your screen sharing, please. Okay, now I kindly invite the next speaker, Professor İbrahim Gökçen from Artvin, Turkey, to do his presentation. Could you please open your video? And your microphone, please. Professor Gökçen, do you hear me? Open your microphone and video, please.
Can you listen to me?
Okay, I'm hearing you. And
hello.
Full screen sharing, please. Could you know with is it Word? Yeah, this is okay. Okay, the link and other facilities for the online presentation seem to be okay. It is a really great pleasure for all of us to have here Professor Gökçen for the noticeable talk on an investigation on the vertices of FUN obtained from Lucas numbers in hyperbolic geometry. Professor Gökçen, do welcome to your presentation, please.
Thank you. Can I start?
Of course.
Thank you. Hello, I am İbrahim Gökçen. I attend the webinar from Artvin University. I thank TÜBİTAK for giving me the chance to present in the webinar. The name of our work is an investigation on the vertices of Fn obtained from Lucas numbers in hyperbolic geometry. In this presentation, we gave some historical information about non-Euclidean geometry and graph theory. We investigated elements of graph theory in hyperbolic geometry. We optioned a value of vertex with Lucas numbers and some identities with related to these numbers. Fibonacci and Lucas number sequences, we know that the Fibonacci sequence is known as 1, 1, 2, 3, 5, 8, 13, and it continues like this. The name of the series was given by the French mathematician Lucas in 1876. The recurrence relation is defined as in the equation. In other words, we say that the sum of two consecutive terms gives the next term. The Lucas sequence is known as 1, 3, 4, 7.
Professor Gökçen, sorry, I'm interrupting you. We couldn't see the slides. Could you please press F5?
I don't understand.
F5, F5. Could you please press F5? Hocam oradaki başlat mı var? Ona da basabilirsiniz.
Hocam F5'e bastım ama oradan
görünmüyor değil mi?
İyi hocam ya. Tabii birkaç tane bastım ama hatta yine basıyorum.
Hocam slaytları değiştirerek gitmelisiniz. You should change the slides.
Ne hocam?
Maybe
Şu anda,
by clicking.
Şu anda görülebiliyor mu hocam?
Sadece ana sayfayı görüyoruz hocam.
Peki hocam ben bunu Word'de PDF'e çevirsem görülür acaba tekrar?
Hocam mouse'la bir tıklar mısınız hocam? Bir sonraki slaytınızı görebiliyor muyuz? Mouse'unuzu bir tıklayın.
Tıkladım hocam. 2 defa tıkladım hocam.
Yok göremiyoruz hocam.
Hocam istiyorsanız PDF'e çevirip oradan anlatayım.
Okey. O zaman bir sonra sizi alayım hocam ben.
Tamam.
Hocam,
tamam hocam ben bunu bekleyeyim hocam o zaman. Bir sonraki soru
Sayın
için.
hocam, ben Murat hocam. Birden fazla sunum açmış olabilir misiniz? Yanlış sunumu
yanlış ekranı paylaşıyorsunuz. Evet hocam.
Şu an kapak sayfası görünüyor şu an.
Biraz evvel değişti hocam.
Şu an gelmedi galiba.
Hocam yön tuşlarına bir basın. Yukarı aşağı. Yani ikinci ekranınızda var galiba hocam. Bir ekranınız daha var mı?
Hocam ben tek bağlantı yaptım ama.
Şu an göremiyoruz hocam onu. Hocam sharing'i kapatın isterseniz bir sonrakiyle devam edelim.
Hocam
sizi en son alayım ben.
Şöyle bir şey yapsam olur mu hocam? Başka bir PDF versiyonu var. Ondan alsam olur mu acaba? Farklı versiyon var.
Olur hocam.
Bir dakika hocam. Bunu kapatayım.
Önce sharing'i kapatın hocam.
Bir dakika hocam. Şu an görülüyor mu hocam?
Evet hocam. Ctrl L yapın.
Ctrl L.
Full screen.
Şu an görünmüyor değil mi hocam yine?
Okey.
Şu an görülebiliyor mu hocam?
Görünüyor hocam.
Tamam o zaman devam edeyim hocam eğer sizin için de müsaitse eğer.
Okay.
The class sequence is known as 1, 3, 4, 7, 11, 18, and it continues like this. The recurrence relation is defined as seen in the equation, such as the Fibonacci sequence. Hyperbolic geometry, Euclid is known as the founder of geometry. The geometry created on the postulates in the elements he wrote in Alexandra in the 300s BC has been studied for years. It can be said that the word postulate corresponds to the word axiom today. The word axiom is used for propositions that do not need to be proven, but which we can observe to be true. The word axiom has a general usage, and the word postulate has a field-specific usage. Euclid's first four postulates are easy to understand. The fifth postulate is more difficult to understand than the others. Proving this fifth postulate occupied mathematicians for a long time. Knowledge progressed cumulatively. In the Middle Ages, elements books were translated in the Arabic in the Islamic world and studied by Muslims for many years. And commentaries were written on the works for the book. One of the concepts studied in the Islamic world was the concept of infinity in the fifth postulate. It was in the 18th century that studies on Euclidean geometries came to the fore, agent after a long time. Girolamo Sacchari is accepted as the founder of non-Euclidean geometries. Girolamo, by putting forward the hyperbolic parallel postulate, tried to prove that this postulate was in conflict with the first four postulates, and thus tried to show that the fifth postulate was correct, but his studies were inconclusive. Studies on non-Euclidean geometries began to increase in the 18th and 19th centuries in the Western world, especially Carl Friedrich Gauss, Nikolai Ivanovich Lobachevsky, and Jonas Bolyai conducted studies on the subject. The acceptance of the new geometries was not easy. In such geometries as an Euclidean geometry, they had to be consistent within themselves and give answers to the questions that Euclidean geometry answered. The existence of elliptic and hyperbolic geometries, for which the fifth postulate was not true, aroused serious suspicion agents of the light truths in mathematics. Poincaré and Beltrami worked on the visualization of hyperbolic geometry. The Poincaré circle model and the Poincaré upper half plane model are the most common modeling examples used to represent a hyperbolic plane. Graph theory and elements defined on hyperbolic geometry. It is generally accepted that graph theory started with an event based on the ascent of people to Goros according to a certain rule over 7 bridges built on the Prega River, which passes through the town of Kaliningrad in Belarus. The event is to test whether it is possible to reach the same corner by starting from any corner and crossing the bridge only once. Swedish mathematician Leonard Euler brought the subject to literature with his work 7 Bridges of Königsberg published in 1736. However, the first examples of graph theory can be traced back to the works of Pythagoras and his students. The Pythagoras admitted that there are only 5 smooth objects. As a result of planar expansion of these 5 regular objects, vertices and edges connecting the vertices are formed. The result is planar simple graphs. Graph theory has focused on different problems over time. One of them is the color problem. In the following years, graph theory began to be studied on the hyperbolic plane. G1, F1, and especially Fourier graphs are defined. From here, starting from infinity, the values of the graph at extended numbers are considered as vertices. The hyperbolic geodesic consisting of the lines perpendicular to extended numbers between the vertices and semicircles whose center is on extended numbers are considered as edges. You can see a diagram about several triangles created with the Fourier sequences with these vertices. These are vertices and these are edges, and we let these edges as hyperbolic geodesics. Suborbital graphs, graph theory is defined on this set with for these elements. The orbitals of this transformation are called suborbitals of G. O alpha beta represents the suborbital graphs alpha beta. The suborbital graphs G alpha beta can be obtained from the suborbital O alpha beta. If this exists with gamma and delta vertices being elements of extended rational numbers, the orbit represents a directional edge from gamma to delta and is denoted by this. This edge can be drawn as a hyperbolic geodesics. We know that Möbius transforms are represented with elements of modular groups. The modular group is section group. In particular, if the modular group is denoted by gamma, it is written as. And in other words, we can show gamma with this set. Gamma 0 and a subgroup of gamma, and we can show with this set. The moment of gamma on extended rational numbers is transitive. Therefore, each suborbit contains the pair for this. If these conditions are provided, we denote the suborbital by ON and the suborbital graphs corresponding to the suborbital as GN. F1 is the subgraph of GN consisting of the belong if. Thus, GN consists of the discrete copies of F1. If these conditions are provided, we can say this graph is directed. And if these conditions are provided, we can say that this graph is left directed. In addition, gamma 0 and transitively parameters the vertices and edges of F1. Lemma. If this is provided, there is an integer k that satisfies the congruence equation. For these values, this matrix, which the element of an equivalent subgroup of the modular group, connects the vertices respectively on an infinite minimal length path in suborbital graphs F1, and each vertex form a continuous fraction structure. Continuous fraction is defined as this continuous fraction can be written as, however, nth approach for continuous fraction is denoted by Fn, and it is written as recurrence relation. Let the nth numerator of the continuous fraction be Pn and the nth denominator of continuous fraction be Qn. Recurrence relation can be defined as with initial conditions. If we take these values in this recurrence relation, we take this recurrence relation. Nth value of the continuous fraction can be written as, and we know that Möbius transforms are represented with elements of a modular group. If we take k equality 0 in this equation, we find this vertex. And if we take k equality infinity, we find this vertex. If this recurrence relation is examined, we optioned these equations. In particular, if this is applied in the equation, we found this equation for k greater than 2. If the equation is solved, we found Pn as. In particular, if we take k equality 2, we find Pn as relation between spatial vertex values of suborbital graphs and continuous fractions. Cn is a series. Tn Cn can be written as, and if we take Cn equality 0, we find this vertex. And if we take Sn equality infinity, we find this vertex. Anti-vertex in the path with minimal length in the suborbital graphs F1 with the recurrence relation, we can write as, from here we obtained this matrix, and it is an element of a modular group. From here we found this equality. Relation between vertices of suborbital graphs and Fibonacci numbers. If these conditions are provided, we obtain Pn as. From here, we obtain lemma and theorem. Relation between vertices of suborbital graphs and Lucas numbers. If these identities are taken into account, we obtain it Fn as approximation value. If the last approximation value is substituted in the identity, it becomes. From here, we obtain it Pn as approximation value. From here, in the suborbital graphs F1, the representation of this vertex with Lucas numbers is found as, on the path with minimal length starting with the vertex, with this vertex, then these identities are found for the matrix, for this matrix. And if the values are written into the matrix, we obtain it this matrix with Lucas numbers. Using this identity, these numbers can be written as, if we take these values, we obtain it this matrix with real numbers. If we take these values, we obtain value of the 15 vertex with real numbers. Lemma, in this lemma, we obtained determinant of this matrix, and we found one proof. In this lemma, we obtained a determinant of this matrix proof. In this lemma, we found in this lemma, we obtained a value of vertex with locus numbers by using this equality. In this lemma, we obtained this identity by using this equality. In this lemma, we obtained this identity by using Pn. Proof ln is obtained from Pn. From here, we obtain these identities. Then L to n is found as lemma. In this lemma, we obtained this identity by using these identities. These identities are obtained from Pn. There, if we add these identities, we found this value, and we know that this identity is provided. As a result, Fn is obtained as. In this lemma, we obtained in this identity by using these identities. In this lemma, we obtained this identity by using approximation value of Fn, and we obtained 0. In this lemma, we obtained it in this identity by using approximation value of Fn. These are references. Thank you for your patience.
Okay, we thank you, Professor Gökçen, for his nice talk. If there is any question or comment, please use the question and answer button of Zoom.
Thank you.
Let me check the question answers session. Okay, there seems no question or comment. So we thank again to Professor Gökçen. Stop your screen sharing, please. Professor Gökçen, stop your screen sharing. Thank you. Okay, now I kindly invite the next speaker, Professor Aybala Sevde Özkapı from Konya, Turkey, to do her presentation.
Hello.
Hello, could you please open your presentation in full screen? Okay, the link and other facilities for the online presentation seems to be okay now. It is a really great pleasure for all of us to have here Professor Özkapı for the noticeable talk on a result for F contraction on orthogonal matrix space. Professor Özkapı, do welcome to your presentation, please.
Thank you. Hello, everyone. Firstly, thanks for this great organization for TÜBİTAK. I am Aybala Sevde Özkapı, a master student at Selçuk University, Department of Mathematics. In this talk, I will tell you some fixed point results in orthogonal metric space. Let's start by talking about the historical development of fixed point theory. A fixed point problem, it asserts that under certain conditions where t is a function of the form t x from x, the solution set of the equation tx minus x equal to 0 is a non-empty set. Here x is any set with its structural features, the tx minus x equal to 0 equation has many applications in the literature, especially when searching for a solution method for equations such as differential equations, integral equations, and fractional differential equations. The problem of finding the fixed point of some mappings can be formulated. Fixed point theory is generally examined under three main topics: topological, discrete, and metric fixed point theory. These three main topics were defined by the discovery of three great and important theorems listed below. Firstly, Brouwer fixed point theorem. Secondly, Banach fixed point theorem. Thirdly, Tarski fixed point theorem. The generalization of the contraction condition and the metric space has been of great importance in the fixed point studies since Stephen Banach. Banach fixed point theorem maintained that let XT be a complete metric space and every self-mapping T satisfying following contraction condition as in 1 has a unique fixed point, and for every x0 in X, a sequence T over n x0 is convergence to the fixed point. This theorem, given in 1922, has been an important role model for many researchers working on fixed points. The existence of contraction conditions that produce a fixed point has been studied extensively on metric and different types of metric space. In their fixed point study, Das and Gupta extended the Banach contraction mapping by introducing the concept of rational expressions in contraction mappings. Let Xt complete metric space and a mapping Tx from X such that, as in 2, for some x0 in X, the sequence of iterators has a subsequence with Z. Then Z is a unique fixed point of T. Later, Jaggi and Das proved that the unique fixed point for any continuous mapping Tx from X on a complete metric space Xt that satisfies the rational type contraction conditions as in 3 for all xy in X. One of the most remarkable generalizations of the Banach fixed point theorem was given by Twardowski in 2012, defining the concept of contraction F. Let big F be the set of all functions F satisfying conditions F1, F2, F3. Big F be the set of all functions F satisfying F1, F3. Now B give the definition of F contraction. Let Xt be metric space, T be a self-mapping, and F in big F. T is called F contraction if there exists tau greater than such that, as in 5. We can give some example of F contraction, such as F1 alpha is this, F2 alpha is this, F3 alpha is this, F4 alpha is this. From F1 and inequality 5, every F contraction is a contractive mapping, EA, as in 10. Thus, every F contraction mapping is a continuous mapping. Einstein's fixed point theorem means that every contractive mapping on a compact metric space has a unique fixed point. While passing from Banach to Einstein fixed point theorems, the mapping classes expand with the condition of contraction, while the structure of space is limited. Twardowski, on the other hand, proved the following theorem without limiting the structure of space. Let Xt be a complete metric space and let a mapping Tx from X be an F contraction. Then T has a unique fixed point Z in X, and every x0 in X, a sequence T over an x0 is convergent to Z. One of them, generalizations of contraction mappings, is given by Arshad et al. And for other examples, you can see. Theorem, Let XD be a complete metric space and Tx from X be generalized F contraction of rational type A. Then T has a fixed point in X. Lately, for the first time, Gage et al. Introduced of an orthogonality in metric space and proved the fixed point result for contraction mappings in metric space endowed with this of orthogonality. Also, they gave the application of this result for the existence and uniqueness of the solution of a first-order ordinary differential equations. Let X be a non-empty set and perp be a binary relation defined on X. If binary relation perp fulfills the criteria, as in 14, then pair X perp known as an orthogonal set, the element X0 is called an orthogonal element. We denote this O set or orthogonal set by X perp. Let X perp be an orthogonal set. Any two elements x, y in X such that X perp Y, then X, Y in X are said to be orthogonally related. A sequence Xn is called an orthogonal sequence, as in 15. Similarly, a Cauchy sequence Xn is said to be a orthogonally Cauchy sequence if, as in 16. Let X perp be an orthogonal set and D be a metric on X. Then X perp D is called an orthogonal metric space. Let X perp D be an orthogonal metric space. Then X is said to be an O complete if every Cauchy O sequence is convergent in X. We can give some examples of orthogonal metric space. Let X and define X perp Y if X smaller and equal to Y, then by putting X0 equal to 2, X perp is an O set. This is the case in other examples. Every continuous mapping is perp continuous. However, the converse is not true. Every complete metric space is all complete metric space. However, the converse is not true. Every contraction mapping is perp contraction mapping. However, the converse is not true. Let us now consider the real extension of the Banach contraction principle given by Gage et al. Let X perp D be an O complete orthogonal metric space with an orthogonal element X0 and a mapping Tx from X satisfying the following conditions. T is perp preserving, T is a perp contraction mapping, T is perp continuous. Then T has a unique fixed point in X. Also, T is Picard operator. Looking at the proof, let X0 in X be an orthogonal element. It is shown that the sequence created with the orthogonal element as in 18 is an orthogonal sequence. It is obtained that Xn is a Cauchy orthogonal sequence. Since X is orthogonal complete, the existence is a point where Xn converges in X. Also, T is a perp continuous, the existence of a fixed point is shown. For uniqueness, it is assumed that T has two different fixed points and uniqueness is obtained with the triangle inequality. Finally, it is shown similarly that T is the Picard iterate. Another new fixed point theorem in orthogonal metric space given by Konakwan et al. First, let's give the definition of F contraction mapping in an orthogonal metric space. Let X perp D be an orthogonal metric space. A mapping Tx from X is called orthogonal F contraction mapping if there are F in big F and tau greater than 0 such that the following condition holds. As in 30. Let us now give the first F contraction fixed point theorem proved in orthogonal metric space. Let X perp D be an O-complete orthogonal metric space with an orthogonal element X0 and T be a self-mapping on X satisfying conditions 1, 2, 3. Then T has a unique fixed point in X. Also, the Picard sequence converges to the fixed point of T. Now we give our main result this talk. We consider rational type F contraction on orthogonal metric space and establish the existence of fixed point of such mapping. At the end, we give an example. Let X perp D be an orthogonal metric space. We say that Tx from X is an orthogonal rational type F contraction if there are F in big F and tau greater than 0, such that the following condition holds: every x, y in X with as in 1. Let X perp D be an O-complete orthogonal metric space. X0 is an orthogonal element of X and T be a self-mapping on X such that T is perp preserving. T is an orthogonal rational type F contraction. T is perp continuous. Then T has a unique fixed point in X. Looking at the proof, let X0 in X be an orthogonal element. It is shown that the sequence created with the orthogonal element is in 33. It is obtained that Xn is a Cauchy orthogonal sequence. Since X is orthogonal complete, the existence is a point where Xn converges in X. Also, T is perp continuous, the existence of a fixed point is shown. For uniqueness, it is assumed that T has two different fixed points and uniqueness is obtained with the triangular inequality. Corollary, let X perp D be an O-complete orthogonal metric space with an orthogonal element X0 and T be a self-mapping on X satisfying the following conditions. T is perp preserving. T is an orthogonal F contraction such that, as in 41, T is perp continuous, then T has a unique fixed point in X. Let XD be a complete metric space and Tx from X be a mapping such that for some, as in 42, for all xy in X, then T has a unique fixed point in X. In this example, X and D be a mapping defined by for all xy in X. Consider the sequence Sn defined as define a relation perp on as in 45. Then X perp D is an O-complete metric space. Now we will define a mapping like this T. Then T is perp continuous and X is perp preserving. So we consider that all the condition of theorem 9 is satisfies if alpha equal to alpha plus ln alpha and tau equal to 1. Then T has a unique fixed point. That's all I have to convey to you. Thank you for listening to me.
Okay, we thank to Professor Özkapı for her valuable presentation. If there is any question or comment, please use the question and answer button. Let me check question answer section here. Okay, there seems no question or comment. So we thank again to Professor Özkapı.
Thank you.
Stop your screen sharing, please.
Çok özür diliyorum ama bilgisayarıma bir şeyler oldu.
Okay. Now I kindly invite the last speaker of this session, Professor Pablo Gomez Nicolas from Santander, Spain, to do his presentation.
Okay, thank you very much.
Could you please open your presentation in full
Yes,
screen mode?
of course. One moment. Can you see it now correctly?
Okay. The link and the other facilities for the online presentation seems to be okay. It is a really great pleasure for all of us to have here Professor Gomez Nicolas for the noticeable talk on induced structures on generalized geometry. Professor Gomez Nicolas, do welcome to your presentation, please.
Okay, perfect. First of all, I want to thank all the organizers for giving me the opportunity to talk here. I am going to present a joint work with Fernando Tallo and Rafael Santamaria. First of all, I think I should define the generalized tangent bundle or big tangent bundle. And this vector bundle is defined as the Witnessium of the tangent and the cotangent bundle of a manifold. And it was introduced by Nigel Hitching in 2003 and later studied by Gualtieri in 2004. The rank of this vector bundle is 2 times the dimension of the manifold, and the section of this bundle can be seen as sums of vector fields and one forms. One question that may arise when we present this bundle is the following: why should we study it? Well, when it was presented, it could be seen that this bundle is related with the development of other science fields, such as string theory, and lately it has been useful in order to construct geometric structure in other vector bundles. For example, Nanitsyn in 2019 used it to construct an Norden structure on the cotangent manifold. The first studies of this vector bundle focused on generalized complex structures by Gualtieri and generalized paracomplex structures by Wade. These 2 structures can be defined as endomorphisms of the sections of this bundle, such that if we square this endomorphism, we get plus or minus identity. These structures are also asked to be integrable with respect to a bracket that can be defined in this bundle, and they are also asked to be compatible with a canonical metric that will be presented later in this talk. However, later studies suggested that this compatibility condition with the canonical metric may be omitted in order to get more examples that can be interesting to study. If we omit this condition, we can see that the definition of a generalized almost complex and a generalized almost paracomplex structure are very similar to the definitions of complex and paracomplex structures defined on a manifold. Therefore, our perspective here is to omit this condition of compatibility with the metric. We will define geometric structures in any vector bundle E, and we will compare the 2 situations when E is the tangent bundle and when E is the big tangent bundle. In the first case, we will obtain the usual structures defined for vector fields. And in the second case, we will obtain generalized structures defined for sections of the big tangent bundle. Okay, so we can take now any vector bundle E over a base manifold M. And in this case, of course, we define a metric as it is usual, a differentiable morphism G that is bilinear, symmetric, and non-degenerate. We know that if the metric is positive definite, we use the Riemannian name, while if it is not positive definite, it will be called pseudo-Riemannian, and the signature of a metric is defined as the number of vectors with positive length and the number of vectors with negative length of a basis of a fiber in the vector bundle. If we change the symmetry condition by an anti-symmetry condition on the definition of a metric, we obtain the definition of a symplectic structure on the vector bundle. Of course, when we work with the tangent bundle, we recover the usual concepts of metrics and almost symplectic structures on a manifold. We know that in order to talk about symplectic structure on a manifold, the omega must be a closed form. When we are using the generalized tangent bundle, we will talk about generalized metrics and generalized symplectic structures. If we take now any symplectic structure on a vector bundle, as it is a non-degenerate structure, we can define isomorphisms between the module of sections of the bundle E and the sections of its dual bundle E star. These isomorphisms will be called musical isomorphisms, And we have two, the flat isomorphism and the sharp isomorphism associated to omega. In the case of the flat isomorphism, we will take sections of the bundle E to sections of the dual bundle E star using the definition shown in the screen. And the sharp isomorphism will be defined as the inverse isomorphism of the flat isomorphism. This section morphism can also be seen as a bundle morphism over the identity map of the manifold, such that their corresponding diagram must commute. For example, this is the diagram associated to the flat isomorphism of omega, and this diagram must commute. Of course, we can do this. We can define this musical isomorphism for a metric G, and the notation will be the one shown in the slide. Now I'm going to define the main focus of this talk, the polynomial structures. These structures will be defined as section endomorphism. In this case, I will denote them with the letter J. And they will have a minimal polynomial associated P such that P of J must be equal to 0. We want to focus on two minimal polynomials. The first one is x squared plus 1. In this case, the polynomial structure must be j squared equal to minus the identity map. And we will have an almost complex structure on the vector bundle. When the polynomial is x squared minus 1, we will have that j squared is equal to the identity map, and this structure will be called an almost product structure on the bundle. When the eigenbundles associated to the eigenvalues plus 1 and minus 1 of j have the same dimension, we will use the notation almost paracomplex structure. And in a similar way than the musical isomorphisms, these section endomorphisms can be seen as bundle endomorphisms over the identity map on M, such that this diagram must commute. One important characteristic is that each polynomial structure can induce a dual structure on the dual bundle E star with the same minimal polynomial P, and is defined as it is shown here for each alpha section of E star and for each xi section of E. When we work with the tangent bundle, we will recover the usual concept of almost complex, almost product, and almost paracomplex structures on a manifold. When we work with the big tangent bundle, we will talk about generalized almost complex, generalized almost product, and generalized almost paracomplex structures. It is worth noting that we are not going to focus on the integrability of these structures, so we will always use the adverb almost. To end this introduction, I want to talk about the concept of alpha epsilon metric structures for alpha and epsilon taking the values plus 1 or minus 1. This structure is composed by a polynomial structure J such that J squared is alpha times the identity map, and a metric G that is compatible with the polynomial structure in a way that J is isometric or anti-isometric with respect to the metric G. The value of epsilon will determine if it is isometric or anti-isometric. Depending on the values of alpha and epsilon, we will use different names for these structures. For example, if alpha and epsilon are both equal to plus 1, we will talk about almost product Riemannian structures. In this case, we will require the metric to be Riemannian. And when the structure is almost paracomplex, when J is almost paracomplex, we will say that we're working with an almost paranorthern structure. When alpha is plus 1 and epsilon is minus 1, we will have an almost parahermitian structure. When alpha is minus 1, epsilon plus 1, we will talk about Hermitian structures. In this case, we will force the metric to be Riemannian. And when both alpha and epsilon are equal to minus 1, we will have almost northern structures. Now we are ready to talk about generalized structures or polynomial structures. Generalized structures in the big tangent bundle. We're going to show first 3 canonical structures that can be found without adding more structure on the base manifold M. The first one is, as I said before, the canonical generalized metric G0, such that for each pair of sections of the bundle, say for example x plus xi and y plus zeta, we have the value xi of y plus eta of x divided by 2. This canonical generalized metric is a pseudo-Riemannian metric with neutral signature. And if we change just one sign on the definition of the metric, we obtain a different structure called the canonical generalized symplectic structure. The third canonical structure that I want to introduce is the canonical generalized almost paracomplex structure. In this case, for each section x plus xi, the canonical generalized almost paracomplex structures gives the result minus x plus xi. From now on, I will use this matrix notation that is very intuitive to refer to polynomial structures on the big tangent bundle. It is easy to check that the eigenbundles associated to the eigenvalues plus 1 and minus 1 of F0 are respectively the cotangent bundle and the tangent bundle of the base manifold. One property that can be easily checked is that these three canonical structures are related between them with this nice expression. The omega 0 can be obtained using the G0 and the F0. Another property that can be easily checked and that can sound strange is the following: that the generalized tangent bundle is canonically isomorphic to its dual bundle. In this case, we have a lot of isomorphisms, but some canonical isomorphisms are given by the musical isomorphisms of the canonical metric and the canonical symplectic structure. This is something that is very different in comparison to the tangent and the cotangent bundle. We know that both the tangent and the cotangent bundle are isomorphic between them, but we need to define a metric on the base manifold in order to have an isomorphism between these two bundles. In this case, the isomorphism is canonical. Until now, we have talked about structures that arise naturally in the big tangent bundle. However, when the base manifold presents more structure, we can induce different generalized structures. For example, the first examples shown are these two generalized almost complex structures. The first one is induced by an almost complex manifold, and the second one is induced by an almost symplectic manifold. Using the matrix notation, the first one takes each section x plus xi to the section jx minus j star xi, and the second one takes x plus xi to minus sharp of omega xi plus flat of omega x. The interesting thing about these two structures is that we can see as the same type of structures, in this case an almost complex structure or an almost symplectic structure on the manifold. We can see them as the same type of generalized structures. They are both generalized almost complex structures on the big tangent bundle. These two examples satisfy the isometry relation with the canonical metric, as I said in the first slides of this talk. However, we said that we were going to omit this compatibility condition with the canonical metric. Therefore, from an almost complex manifold, we can obtain two generalized almost complex structures on the generalized tangent bundle. The only thing that we have to do is to change the sign of G star. We can put here a lambda that can take the value +1 or -1. This structure is generalized almost complex, and the eigenbundles of this structure can be seen as Whitney-sums of the eigenbundles associated to J and J star. Depending on the value of lambda, these expressions will be different. We can do something similar for an almost product manifold. In this case, we can induce two generalized almost product structure depending on the value of lambda, taking values +1 or -1. And analogously, we can obtain the eigenbundles of these generalized almost product structures. They are also given by Whitney-sums of the eigenvalues of F and F star. And in this case, we have that for lambda equal to +1, the generalized almost product structure induced will be almost paracomplex if and only if the F structure on the manifold is almost paracomplex. However, for lambda equal to -1, this structure will be always generalized paracomplex, whether F is almost paracomplex or just almost product. If we have a different structure on the base manifold, we can generate different generalized polynomial structures. For example, from a Riemannian or pseudo-Riemannian manifold, we can generate a generalized almost complex structure that is very similar to the definition that we gave before for the one induced by an almost symplectic structure, and a generalized almost paracomplex structure, just changing one sign here. Analogously, if we take an almost symplectic manifold, we can induce the generalized almost symplectic, almost complex structure that we showed before, and a generalized almost paracomplex structure that is very similar to the one induced by a metric, just changing the sign. Now we want to check what structures can be induced if we have in the base manifold a polynomial structure and a metric that are compatible. That is, we have an alpha epsilon metric manifold. Nanitsini showed that when we have an almost northern manifold, we can, that is, we're taking the values alpha and epsilon equal both to -1, we can induce a generalized almost complex structure in the big tangent bundle. We want to propose a similar structure, similar almost complex structure for other alpha epsilon metric manifolds. We are going to take first the values for, we are going to take the manifolds for alpha equal to -1. And in this proposition, we show that when we have an alpha epsilon metric manifold with alpha equal to -1, we can induce these two generalized almost complex structures. They are both, in our matrix notation, they are both triangular. In this case, we use the flat isomorphism, and in this case, we use the sharp isomorphism. Of course, we take the epsilon value corresponding for the alpha epsilon metric manifold. This can also be done for an alpha epsilon metric manifold with alpha equal to +1. Idan Manea showed proved that when we have an almost parahermitian manifold with F being almost paracomplex, this structure is generalized almost paracomplex. And if we do a similar proposition that the one that we have before for an alpha epsilon metric manifold with alpha equal to +1, we can induce two generalized almost product structures. In this case, they are also triangular. The first one uses the flat isomorphism, and the second one uses the sharp isomorphism of the metric. The epsilon value is the corresponding to the alpha metric manifold. And in this case, we have that these two structures will be generalized almost paracomplex if and only if the F structure on the manifold is almost paracomplex. Now to end the talk, I want to present more complicated generalized structures. If we have an alpha epsilon metric manifold with alpha equal to -1, now we have induced two generalized almost product structures, the one induced by the metric and the one that can be induced with this omega structure that is obtained using G and J. We want to induce now a generalized almost product structures that in the matrix notation has the J directly in its description. In this way, we have that this proposition, if we have alpha epsilon metric manifold with alpha equal to 1, we can induce the following generalized almost product structure, of course, for the corresponding value of epsilon. We have here two square roots of 2, and this is a more complicated structures than the ones that we have seen before. Of course, and as we have done before, we can obtain a similar results for the case of alpha equal to +1. Now we want to obtain a new generalized almost complex, not manifold, structure using F, the structure F on the manifold. We have this proposition. this generalized structure is almost complex. We have in the principal diagonal the structures f and minus epsilon f star, and here we have the square root of 2 and the two musical isomorphisms of the metric. So that is all I wanted to talk about. I have here some bibliography that I have used. We have used to do the talk from the classical works of Hitchin and Gualtieri and Wade analyzing this vector bundle to more modern works like the one by Nannicini, Weissman, Fernandez-Kulma, Godoy-Salvay, and Ideimanea. And that is all I wanted to talk about. Thank you very much, and I will gladly answer every question that you may have.
Okay, we thank to Professor Gomez-Nicolas for his valuable talk. If there is any question or comment, please use the question and answer button. Let me check. I think there seems no question or comment. So we thank again to Professor Gomez-Nicolas.
Thank you.
Please stop your screen sharing, please. Okay. I would like to thank all participants for their patience and attending session 16 of our webinar. Now, the next section will be moderated by Professor Uğurcan Eser. Thank you.
Good evening, everyone. I am Uğurcan Eser. Ladies and gentlemen, now I kindly invite Professor Hristo Manev from Plovdiv, Bulgaria, to do his presentation.
Hello to everyone.
Welcome.
Thank you. Should I wait for 5:20 or?
You can start immediately. You can start.
Okay. Well, I'm sharing my screen.
Okay.
I hope it's okay.
Yes. Today's topic is parallel-like solitons with arbitrary potential or Paris-Saseki-like Riemannian manifolds. Please go ahead.
Hello again to everyone. Firstly, some introductory words about the problem that I'm going to talk about. The concept of Ricci solitons was introduced by Hamilton in his work from 1982 as a special self-similar solution of Ricci flow equation. In other words, Ricci solitons represent a generalization of Einstein metrics on a Riemannian manifold, being generalized fixed points of the Ricci flow considered as a dynamical system. After that, a detailed study on Riemannian Ricci solitons can be found in the work number 9 here in my references from 2009. The study of Ricci solitons, just a second, sorry, began in 2008 by Sharma in his work. After that, the investigation of the geometric characteristics of the Ricci solitons hence continued on different types of almost contact metric manifolds. For example, you can see these works that I have put here. The notion after that, a generalization of this notion of Ricci soliton, the notion of eta Ricci soliton, is introduced by Cho and Kimura in 2009. Sorry, because this panel of the second. Yes, the investigation on eta-Ricci solitons in the context of paracontact geometry were made by Dara Bwaga, for example, and Prakash Higman. Recently, various geometers have extensively studied the properties of Ricci solitons in pseudo-Riemannian geometry and their generalizations. This interest is also based on the growing interest of this geometry of theoretical physicists and its relation into string theory. For further references of pseudo-Riemannian Ricci solitons, you could see these works that I have put it here. The object of our focus here in this work is the geometry of Riemannian manifolds with enormous paracontact structure corresponding to enormous paracomplex structure. This type of structure we call briefly here a pi structure, and these manifolds respectively Riemannian pi manifolds. In these manifolds, the induced almost product structure on the paracontact distribution is traceless, and the restriction on the paracontact distribution of the almost paracontact structure is an almost paracomplex structure. In the work of Manchumanev and Maria Staikova from 2001, these manifolds are introduced and classified. Their investigation is continued after that from Manchumanev and Tavkova. In the present paper, due to the presence of two associated metrics, we introduce and study our further generalization of the notion of a Ricci soliton and an eta-Ricci soliton. Namely, we study para-Ricci-like solitons with arbitrary potential and para-Sasaki-like Riemannian pi manifolds. Let me show some introductory words, preliminary words about the studied structures. By M phi psi G, we denote a Riemannian pi manifold, where M is a differentiable odd-dimensional manifold, G is a Riemannian metric, and phi psi eta is an almost paracontact structure. Phi is tensor of type 1, tensor field type 1, psi is a Riemann vector field, and eta is its dual 1 form, and identities 1 are satisfied. Consequently, the following properties are immediately derived from these basic identities, the properties 2. And as I said earlier, we have here associated metric G-tilde of G on the manifold M, which is determined by equation number 3. G-tilde is an indefinite metric of signature n plus 1 n, which is compatible with M, just like G. The Riemannian pi manifolds are classified in the work of Manev and Staikova. This classification contains 11 basic classes denoted there by calligraphic F1 to 11, and it is made with respect to the fundamental tensor F defined in 4 and having the properties 5. The intersection of these basic classes is the class with condition f equal to 0. Also, we have the one forms associated with f, called Lie forms, which are defined in 6. Object of interest here in our work is the class of Parasaki-like spaces, which are defined in work number 16, our previous work with Stefan Ivanov and Manchumanev. We obtained this set of Riemannian pi manifolds from a specific cone construction, and these spaces are determined by a condition number 7. Let me remark that Parasaki-like Riemannian pi manifolds form a subclass of the basic class F4 of the classification of the considered manifolds. In the same cited work, the truthfulness and the following basic identities for this class of manifolds are proved, number 8. And here we prove the truthfulness of proposition 1,1, which contains properties for the Ricci operator Q of arbitrary Parasasaki-like Riemannian pi manifold M phi excited G. Let me recall some definitions from our previous work with Manchumanev. A manifold M is said to be para-Einstein-like with constants ABC if the Ricci tensor satisfies the following equality, and in the case when B vanishes or B and C vanishes, we call the manifold eta Einstein or well-known Einstein manifold. And if in the respective cases when A, B, and C are functions on M, we use the word almost before the definition. Also, let me recall a proposition for my previous work in symmetry about Parasasaki-like Riemannian, arbitrary Parasasaki-like Riemannian pi manifold. If this manifold is almost para-Einstein-like with functions A, B, and C, the scalar curvatures tau and tau tilde are constants, and tau tilde is equal to -2 times n, and the manifold is eta Einstein with the respective constants. Also, let me remark that tau and tau tilde stands for the scalar curvatures regarding the two associated metrics, respectively. Now, let me focus on para-Ricci-like solitons on these manifolds. In the previous work 17, the notion of para-Ricci-like solitons with potential psi, the Reed vector field psi, and constants lambda mu nu is introduced by 12. And as I explained before, it is a generalization of eta Ricci soliton and Ricci soliton for mu equal to 0 and mu nu vanishes. We have these definitions, and here we have for functions lambda mu nu, the solitons are called in the respective cases with the word almost before. In the next work, work 18, we define the notion of para-Ricci-like soliton with vertical potential, and we study it. This is a more general case when the potential is pointwise collinear with the Reed vector field psi. And now the aim of our work is to generalize this concept even more. When we can consider the potential to be arbitrary vector fields as follows. This notion of para-Ricci-like soliton with arbitrary potential vector field V and constants lambda mu nu is defined by it is a Riemannian pi manifold M admits this type of soliton if the Ricci tensor satisfied the equality 13, and we prove a theorem for these spaces. Let them be arbitrary Parasasaki-like Riemannian pi manifold, and it admits para-Ricci-like soliton with arbitrary potential V and constants lambda mu nu. Then the identities for the constants number 14 are valid, and the covariant derivative of the vector field V with respect to psi is equal to phi V. Also, we proved the proposition 2.5 about the same structures if the manifold admits a para-Ricci-Weich soliton with arbitrary vector with arbitrary potential V, then rho tau and tau T satisfies equality 15. And combining these two, this theorem and this proposition and the proposition 1-1 that I recalled earlier, we formulate the following theorem 2-6. Let M phi xi G be on-dimensional para-Einstein, 2n plus 1, sorry, dimensional para-Einstein-like para-Sasaki-like Riemannian pi manifold. If it admits a para-Ricci-Weich soliton with arbitrary potential V, then the following identities are valid. Number 16. After that, we prove assertions about the lowest dimension of the considered manifolds and their sectional curvatures. We have the definition of, we recall the definition of sectional curvature for an arbitrary non-degenerate two-plane by 17. And as I explained, in the lowest dimension of the considered manifolds, we distinguish two special types of two planes alpha with respect to the structure, respectively a phi holomorphic section and a xi section. And every phi holomorphic section has by the basis of the form phi x phi squared x. And as I explained, we prove the following assertions. Let M phi xi G be a three-dimensional para-Sasaki-Weich Riemannian pi manifold. If it admits a para-Ricci-Weich soliton with arbitrary potential V, then the sectional curvature of its phi holomorphic sections are equal to 1, and the sectional curvature of its xi sections are equal to -1. And at the end of my presentation here now, I want to illustrate this theory with an appropriate example. Let M be a set of points in R3 with coordinates x1, x2, x3. We equip this set with the Riemannian pi structure, phi x eta G, determined by 18. The triplet of vectors E1 to E3, determined in 19, forms an orthonormal phi basis of the tangent space. Therefore, we easily could calculate that 20. Then we have 20, and we could obtain easily the commutators of EI, put it here in number 21. The Lie algebra determined by these commutators 21 is proved in the work number 22 that the corresponding solvable Lie group of this Lie algebra equipped with Riemannian pi structure phi x eta G is para-Sasaki-Weich Riemannian pi manifold. Moreover, in this cited work, obtained the components of the Levitsky connection number R, rho Ig, as well as the values of the tau tilde, and the sectional curvature chi Ig. Here in the equalities 22, 23 are given their values. And from the first equality of 23, we get the form of the Ricci tensor 24. So the manifold is a para-Einstein-like, para-Sasaki-Weich Riemannian pi manifold with constants ABC equal to 0, 0, -2. And these results support theorem 2.6 and theorem 2.7 given here. And now let us consider vector field V determined, as you can see here, 25 for arbitrary constant C1, C2, C3. By virtue of the respective equalities, we obtain equalities 26, and using them we could calculate the basic components of the Lie derivative of G with respect to V, and the non-zero ones are given here at the bottom of the list. And using them, the tensor LG has the following form given in 27, and we could deduce that the manifold M5 G admits a parallel H-like soliton with potential V determined in 25 and constants lambda, mu, and nu given here, which results are in accordance with the proved theorems in this work.
Professor Manev,
thank you for
okay.
your attention.
Okay.
Thank you.
Thank you very much. Dear attendees, is there any question? Okay. Professor Manev, someone asked your presentation. Can you share your presentation?
Yeah. Yeah.
Email address or
my presentation?
In PDF file. Someone asked it.
In question, answer. Sorry.
Yeah.
Share PDF file with. How could I put it a PDF file in here, or I could email?
Okay.
But Makarakush, please put your email here, and I could send you my presentation.
Okay. Thank you, Professor. You can close your screen sharing.
Yeah. Thank you.
Thank you. Thanks so much. Hello again, dear attendees. I kindly invite Professor Mohammed Vasila from New Delhi, India, to do his presentation. Can you hear me, Professor Vasila?
Yes, sir. Yes, sir.
Okay. Please, can you share your screen?
Is it visible, sir?
Okay, everything is okay. Can you full screen your presentation, please? Make full screen. View section, maybe. Okay.
Is it okay, sir?
Okay, everything's okay. Please go ahead.
Okay. First of all, good evening. Myself, Muhammad Wasiullah. I am from Jamia Millia Islamia, New Delhi, India. My topic is application of mixed generalized Cauchy-Einstein space-time in general relativity. These are overview of my paper. First one is introduction, and second one is mixed generalized Cauchy-Einstein manifold with the recurrent fields generators. And third one is mixed generalized Cauchy-Einstein manifold with the concurrent vector fields generators. And fourth one is mixed generalized Cauchy-Einstein manifold with Einstein's field equation. And last one is mixed generalized Cauchy-Einstein space-time admitting a space matter tensor. Introduction. An Einstein manifold is a Riemannian or pseudo-Riemannian manifold whose Ricci tensor, which is denoted by Ric of type 02, is non-zero and proportional to the metric tensor. Einstein manifold form a natural subclass of various classes of Riemannian or semi-Riemannian or pseudo-Riemannian manifold by a curvature condition imposed on their Ricci tensor. Also, the Einstein manifold play a very important Riemannian geometry as well as in general theory of relativity. MC Chaggi and Argymet in 2000 introduced and studied the Cauchy-Einstein manifold. An unflat and dimensional Riemann manifold MNG and its dimension, which is greater than 2, is said to be a Cauchy-Einstein manifold if its Ricci tensor of type 02 is non-zero and satisfy the following condition: Ric xy equal to agxy plus baxay, where a, b are scalar and a is non-zero one form, which is defined by gx rho equal to ax and g rho equal to a rho equal to 1. Rho is vector field called the of the manifold, and one form is also called the associated one form. And from one, it follows that every Einstein manifold is a Cauchy-Einstein and is denoted by QEN. A non-flat Riemann manifold MNG is greater than n is greater than or equal to 2 is said to be a generalized Cauchy-Einstein manifold if its Ricci tensor Ric of type 02 is non-zero and satisfies the following condition, which is 3, where ABC and AB are non-zero one form associated with the two orthogonal unit vectors rho and sigma are defined by 4. And generalized Cauchy-Einstein manifold is denoted by GQEN. A. Bhattacharya and Tide in 2007 introduced the notion of mixed generalized Cauchy-Einstein manifold. A non-flat Riemann manifold is said to be a mixed generalized Cauchy-Einstein manifold and denoted by MQEN if its Ricci tensor Ric of type 02 is non-zero and satisfy the following condition, which is given by 5, where ABCD are non-zero scalar and A, B are non-zero one form, which is defined by 6. Cauchy-Einstein manifold has importance in cosmology and general theory of relativity. Yusude HK Said and in 2021 studied about mixed generalized Cauchy-Einstein work product manifold, and in Svan B. Bhattacharya they are also discussed on multiplied work over products Cauchy-Einstein manifold with quarter symmetric connection. After studying this paper, we are investigated to study about mixed generalized Cauchy-Einstein spacetime. In equation number 5, putting x equal to y equal to ai an orthonormal basis of tangent space at each point on the manifold and taking summation over I, and I is between 1 and n, and contracting over equation 6, we get the equation number 7 are equal to na plus b plus c, and contraction is the reduces the rank of the tensor, where R is the scalar curvature of the manifold. A space-time is a time-oriented four-dimensional manifold M4 with Lagrange metric whose signature is +2 minus. A Lagrangian four-dimensional manifold is said to be a mixed generalized Cauchy-Einstein space-time with the generator rho as the unit time-like vector field if it non-zero Ricci tensor of type 02 satisfies the equation 9. If rho is the time-like unit vector, then we say that the mixed generalized Cauchy-Einstein manifold is said to be mixed generalized Cauchy-Einstein space-time. And A and B, two non-zero one forms such that rho sigma is the heat flux vector field perpendicular to the velocity vector field rho. And therefore, for any x, we have equation number 8. Further, we know that if the Riemann curvature K bar of type 04 has the form is 9, then manifold is said to be a constant curvature K. The generalization of this manifold is the manifold of Cauchy constant curvature, and in this case, the curvature tensor has the following form, which is 10, where GK XYZW equal to K bar XYZW, and K is the curvature tensor of type 1-3, and A, B are scalar function of which B non-zero and is non-zero one form defined by 11. A. Bhattacharya and Pide in 2007 defined a new type of Cauchy constant curvature, which is called the mixed generalized Cauchy constant curvature, defined as follow, which is given 12, where F1, F2 are scalars, of which F1 to F4 are non-zero, and A, B are two non-zero form defined earlier, rho, sigma being two unit vector fields, such that rho sigma is equal to 0. Such manifold is denoted by MGQCN. Next section is mixed generalized Cauchy ST manifold with the recurrent vector fields generators. Let us consider the generator rho and sigma corresponding to the associated one form A and B are recurrent. Then we have eta and psi are non-zero one forms. A non-flat Riemannian or semi-Riemannian manifold MNG n is greater than 2 is said to be a Ricci recurrent manifold if its Ricci tensor Ric of type 02 is non-zero and satisfy the following condition. Is question number 13. Alpha is non-zero one form, and we know that question number 14. And comparing 14 and 13, if follows it, we get 15, and using 5 in 15, we get equation number 16. If we put y equal to z equal to in previous equation 16, we obtain the equation 17. Since dx rho equal to 0, rho is the, and using 6 in 17, we have equation number of 18. So dx sigma equal to 0 if and only if x a plus b minus alpha x a plus b equal to 0 implies that either dx sigma is perpendicular to rho or sigma is parallel vector field. Again, we putting y equal to z equal to sigma in question number 16, we have 19, and since b dx sigma equal to 0 and using equation 6 in 19, we have 20. So b dx rho equal to 0 if and only if x a plus b minus alpha x a plus b equal to 0 implies that either dx rho is perpendicular to sigma or rho is parallel vector field. Hence, we can state the following theorem. If mixed generalized Cauchy manifold is recurrent, then x a plus b minus alpha x a plus b equal to 0 if and only if either dx sigma is perpendicular to rho or sigma is parallel vector field. And second, x a plus b minus alpha x a plus b equal to 0 if and only if either dx rho is perpendicular to sigma or rho is a parallel vector field. Next one is a vector field phi is said to be concurrent if it satisfies the following conditions. Which is given 21, where xi is constant. Consider the generator rho and sigma corresponding to associated one form and B are concurrent. Then we have 22 and 23. Lambda and mu are non-zero constant. And taking the derivative of equation number 5 with respect to z, we obtain equation number of 24, and using 22 and 23 in 24, it follows that which is 25. And now contraction of 25 over x and y, we have 26, and from 7 we get r equal to n a plus b plus c, and r is a scalar curvature since a or b in real number, therefore derivative of scalar curvature is 0 for all x. And using drx is equal to 0 in 26, we get equation number 28. By virtue of 28 in 25 in 5, we have equation 29, which is a Cauchy-Einstein manifold. Hence, we can state the following theorem. If the associated vector fields of a mixed generalized Cauchy-Einstein manifold are concurrent vector fields and the associated scalar are constants, then manifold reduces to a Cauchy-Einstein manifold. Next section is mixed generalized Cauchy-Einstein manifold with Einstein's field equation. The Einstein field equation is xy minus r by 2 gxy plus lambda gxy equal to kappa txy. R and k and lambda are scalar and gravitational constant, and lambda is cosmological constant. If lambda equal to 0 in 30, we get the equation number 31, and it is called the Einstein field equation without cosmological constant. Using 6 in 31, it follows that it is 32, and covariant, taking the covariant derivative of equation 32 with respect to z, and we give 10, 33.
Thank you, Professor. Please summarize your presentation.
Okay, sir.
Couple of minutes left.
Okay.
Thank you.
Hence, we state the following theorem. If the associated one form A and B in a mixed generalized Cauchy-Einstein manifold are covariant constant, then the energy momentum is also covariant constant. Next section is mixed generalized Cauchy-Einstein space-time admitting space matter tensor. To introduce the space matter P bar of type 04, the space matter tensor is defined as follow, which is 34, where P is the space matter tensor of type 04 and K bar is curvature tensor of type 04. T is the energy momentum tensor of type 02 and kappa is the gravitational constant, nu is the energy density. And G and G, which product T are defined as 35 and 36 for all x, y, z. In chi-m is the set of all differential vector fields using 35 and 36. In 34, it follows that 37. If P bar equal to 0 in 37, we get 38. And using 5 in 31, we obtain 39. From 38 and 39, we get 40. Where F1 equal to the F2 minus B by 2 and F3, F4. Hence, we can state the following theorem. A mixed generalized Cauchy-Einstein space-time satisfying Einstein's field equation with 0 space matter tensor is mixed generalized Cauchy constant. Cauchy constant curvature is space-time. Next, we investigate the existence of sufficient condition under which mixed generalized Cauchy-Einstein space-time can be divergence-free space matter tensor. From for derivative of curvature, scalar curvature is equal to 0, and using in 37 we obtain 41 and 42. Hence, we can state the following theorem. The energy density is constant in a mixed generalized Cauchy-Einstein space-time, satisfying the Einstein's field equation with divergence-free space matter tensor. Now, using 5 in 42, we get 43. Consider the equation are constant, and general rho is called rho is parallel vector field dx, that is dx rho equal to 0. Therefore, we get 44, and in view of we derive 45 using 44 and 45 in 5, we obtain divergence p x y z equal to 0, and hence we can state the following theorem. If the energy density are associated scalar are constant in a mixed generalized Cauchy-Einstein space-time with parallel vector field rho satisfying Einstein field equation, then the space matter tensor divergence is vanished. These are references of my paper. And last is thank you, sir.
Thank you, Professor Vasiula. Dear attendees, is there any question or comments? Please can use question answer section. I think there is no question and comments. Thank you again, Professor.
Okay. And am I in the picture?
Yep, you are in the picture.
So let's see.
And then I'll join.
Yeah, yeah, that's great. And you'll control everything.
Yes.
Yeah.
Welcome, Professor. Dear attendees, the current session will continue under the moderation of Professor Hande Uslu. Thank you.
Hello, everyone, again. First of all, we want to apologize from all participants from this interruption. As you know, yesterday, Professor Gilbert Strang could not attend the webinar as scheduled due to some technical problems, but now he is ready to participate. So our schedule reorganized to welcome the professor. I would like to announce that the program will continue after the presentation of the invited speaker in the scheduled order with 20 minutes periods, regardless of the time. Thank you for your patience and understanding. Now, I give the microphone to my colleague, Tahir Coşkun, to introduce dear Professor Gilbert Strang. Thanks.
Thank you, Efendi Hocam. Good morning, good afternoon, good evening, ladies and gentlemen. Now, I kindly invite Professor Gilbert Strang to do his presentation. Professor Strang is coming from MIT of United States, and he published a lot of peer-reviewed articles in highly reputable journals, and also he has several books. He is known as one of the pioneers of open science and particularly open learning. Dear Professor, it is a really great pleasure and honor for all of us to have a professor for a very informative and useful talk on linear algebra and deep learning. Now, all technical facilities seem to be okay. Professor Strang, welcome to your presentation. If you can, I will help you to change your slides.
Right. So thank you very much for inviting me and introducing me. It's a pleasure. I'm sorry that yesterday my computer went down, but it's now I'm back at MIT today, and my assistant is going to control the slides, which we will see in a minute, I hope. Yeah, he's in the next room. Yeah, so we'll see. And I'll wait for him to put up the slide. So it's a great pleasure to.
I'm sorry. So I need to be promoted to panelist.
Go ahead. He needs to be promoted to panelist.
So Murat, so if you see Andre Dixon in the participants, I need to be promoted.
Can you allow Andre Dixon to be a panelist?
Dear Murat Hocam, can you promote Professor Andre to the panelist as a panelist, please?
Right.
Tahir'cim, onların paylaşımına izin verir misiniz?
Tabii hocam.
So I will go back to my computer.
So Professor Dixon, you can go back to your computer and accept it.
All right.
Yes, I sent the invitation, Professor.
You can see that I'm not a professor of computer science. I always need help. So I was planned to speak a little bit about deep learning, about machine learning. That's so the course I started yesterday here in a lecture in the MIT classroom is linear algebra and also machine learning. So, oh, good. And these are the slides for linear algebra, and then you'll see some machine learning in action. Okay, so that's me, and I'm at MIT today. Finally, thank you. And okay, Andre, we could go on to the next slide. Shows maybe the two books or three books. Actually, the most known maybe is the first one, Linear Algebra, Introduction to Linear Algebra. It's now the 5th edition, and that's the textbook for the Math 18.06 at MIT and the videos. And then the next middle book there is the newer book that includes learning from data. So that will be part of today's presentation. And then I just, you see on a third book is a shorter linear algebra book that I wrote during COVID. So I had a good time. I was, of course, only at home every day. So I thought, what can I do? I'll write a more interesting, a new linear algebra book. So the video lectures, maybe you know the URL is OCW for opencourseware.mit.edu course/courses, and then you go to the course that you choose, engineering, math, everything. MIT has like 2,000 courses available. Okay, and then for the books themselves, you could email me about the book, yeah, if you wanted a copy. So there's only hard copy, no. I'm sorry, there's not a ebook. Okay, ready for mathematics now. Okay, so let's see. So starting with the learning function, just for a few lectures. Now, maybe you know how learning functions work. They involve matrices, so a lot of linear algebra, but they must use something nonlinear. And that's this simple nonlinear function, piecewise linear. It's 0 for negative y, and it's equal to y for positive y. And for some reason, it's called ReLU, is the nonlinear thing that's used at every level, for every neuron in the neural net. So let's see a picture of the neural net, or part of the neural net in the next slide. Yeah, the next slide has, yeah. So here's only one hidden layer. So the inputs are on the left, V1 to VP. Those are the, if you, suppose we're trying to recognize a handwritten number. Suppose a number is written 0, 1, 2, 3, 4, up to 9, one of those numbers, and we're trying to find which number it is. So the V's are the from the pixels of the image. So we have an image of a number like 3, and we divide that image into pixels, and their strengths are V1 to VP. Now comes the matrix. So a matrix A multiplies V. Maybe it's a 4 by 3 matrix, let's say, or 3 by 4. Yeah, and we get AV, A times V. And now comes this ReLU, this nonlinear step. And actually we add a vector B as well as multiply by A. But anyway, that's the step. And now with only one hidden layer, we go to the output. So that's a very short neural net, and many of you will know much more about that. Okay, so let's now take go to the next slide and see what. Oh, this is good. This is really what I want you to see. It's a Google person who works at Google near MIT created this interesting way to have some experiments, real experiments with a neural net. And over on the left you see a little box around one picture. So that's the input. The input is blue dots that are +1 and orange dots that are -1. And we're looking for a function. a function of x and y, which will give us plus on the blue dots and minus on the orange dots. Okay, and that function is created by those matrices. So Andre has pressed start, and so already it's done 300 iterations. Soon will be 1,000 iterations, but it has already done the job. You see in the big picture on the right, you see it's really the graph of the function. It's showing where the function is positive, where the function is negative, and in between where the function is 0. So it's exactly right. It separated the blues from the orange. It's plus for blues, minus for oranges, just what we want for our function. So now we've trained it, and now we would use that same function for new data that the system has not seen. So, but let me just repeat the URL, because you can do all this yourself. playground.tensorflow.org. Okay, now let's do one more example. So let's go to the next example, which is much more difficult. Okay, now look over at the far left. You see it's a lot of spirals now. It's orange spirals are going inside blue spirals. So it's very hard to create a function. There you see it. We now want a function created by our neural net. So it's only going to be a linear function, piecewise linear, which has the opposite sign on the blue and the orange. So now we're only using 2 hidden layers, not enough. So if Andre could add another 2 hidden layers, you see, Andre will just click on the picture there up at where it says hidden layers. Yeah, right there. Let's do plus, do some more layers, and then maybe put more neurons, more points. So just below that, where you do another plus, good, and another plus maybe, and another one on the next one, just to give some. Now it's a bigger, of course, everybody knows the real systems have thousands and often millions of neurons. Here we have 4, 8, 11, maybe 13 neurons. Well, now let's push start on this one. Okay, start. So now it's trying, has a little graph of the error. You see it's trying in the picture on the right. It's taking steps. It's doing a minimum. This is a big minimization problem. Minimize the error. Minimize the difference, what we want from what we have. Yeah, so it will struggle. And now it's already done 1,000 iterations, and it's trying its best. I always feel sad about it, because we have, it might, if we keep going, it might get, do you see that it hasn't done very well. So this is for you to go yourself to playground.tensorflow.org, give it more layers, give it more neurons on each layer, and watch, and then you have the good feeling of seeing the function that you want, separating the blue dots from the orange dots. I hope that's interesting. So now we're up over 2,000, but oh, well, yeah, that looks pretty good. Oh, that's almost success, isn't it? At 10,000, 10,000 iterations. It's almost successful. Yeah, I see a few blue dots still in the orange part. Okay, back to mathematics. That was the fun. Okay, and back to linear algebra. So I have a matrix. I want to understand the matrix A. It has m rows, it has n columns. It could be big, it could be small. There are small matrices here on the slide. And I want to understand that matrix. So a good way to understand it is to understand its column space and its row space. So the column space is all combinations of the columns. Those columns are vectors. You can take combinations. So you can take 2 of 1, 2 times column 1, minus 5 times column 2, plus 11 times column 3. And so you get a whole lot of vectors. They fill a plane in some, maybe a high dimensional plane, but it's linear algebra, so the plane is flat. And yeah, so I'll just read the line. The column space contains all combinations of the columns. And the column space is a whole lot of vectors, a whole lot of column vectors. All this, it's a flat plane or a 3-dimensional surface or just a line. Let's see, look at the end of this slide, you see some examples. So the column spaces of the identity matrix, well, that's all combinations of 1, 0 and 0, 1. So we will get any vector xy, we'll get the whole xy plane. And 1, 2, 3, 4, that will also give us the whole xy plane because 3, 4 is in a different direction from 1, 2. So they're independent. Now, the next line has a 1, 1, 2, 2 matrix. Well, that matrix, the column, the 2, 2 column is dependent on the 1, 1 column. It's in the same direction. It's just 2 times as long, but the direction's the same. So when we take combinations of 1, 1, 2, 2, we just stay on that line. So the column space of those matrices are lines, one-dimensional subspaces. Oh, and then finally at the bottom, I put the 0 matrix. And of course, the only combination of those columns is the 0 vector. So that's 1 point. Okay, so those are column spaces of very small matrices. Okay, but we need to understand column space. Okay, on to the next slide. Yeah. So the row space is similar, but it has all combinations of the rows. And if I want to stay with column vectors, then I just would transpose the matrix, change A to A transpose, AT, make the rows into columns, and then I would do the column space of AT, A transpose. Yeah, so those are examples. Again, now we're up to 3 by 3. And you see the first 3 by 3. Yeah, do you see that only 2 columns are independent in that middle one? Because 1, 1, 1 plus 2, 3, 4, it equals 3, 4, 5. So 3, 4, 5 we already have, it's not new. So we only have 2 independent columns. And actually we only have 2 independent rows. That's the wonderful first great fact in linear algebra, that the number of independent columns, which is 2 for this middle matrix there, equals the number of independent rows. Now I don't really see that. I've got 3 rows there. I'm looking at the rows 1, 2, 3, 1, 3, 4, and 1, 4, 5. And I'm pretty sure those columns, those rows are dependent. I think that 3rd row is some combination, which I don't know, of the first 2 rows. If you might want to figure out what combination it is. Why do I think it is a combination? Because I know the theorem that the number of independent columns, which is definitely 2 there, that definitely has 2 independent columns, then it will have 2 independent rows. And so somehow only not 3. Okay, so you see the examples. Below that, the other 3 by 3 matrix, well, it's easy because it's triangular, and we can see that no column is a combination of other columns. Those 3 columns are independent. So a triangular matrix is good as long as you don't have any zeros on the main diagonal. So this is just fun with matrices, but I'm aiming to understand with these small examples the ideas. So what ideas do we have so far? Independent columns and dependent columns, independent rows, dependent rows. And now the word rank is the number of in one, for one matrix, the rank was 2. For the other matrix, the rank is 3. Okay, let's go on to the next slide and see more examples. Well, this is, we've understood this. This is dependence. Yeah, this is dependence. All those examples have dependent columns. The first, you see why. A1, column 2 is just 2 times column 1. And A2, oh, it has a 0 column, a column of 0. So that is the 3 columns don't go into 3 separate directions because 0, 0, 0 doesn't get started. And finally, A3, there will only be 2 independent columns in 2-dimensional space. Okay, ready for the next slide. These are examples that you know. Okay, and now, yeah, so this is saying what I've just already said. A key idea, there's a box around the key idea. Number of independent rows equal number of independent columns. That number is the rank. Yeah, and for that triangular matrix U at the bottom, the 3 columns are independent and the 3 rows are independent. So the rank is 3, full rank for that matrix U. So it has an inverse matrix. Okay, ready for the next slide. We're moving along. Okay, so here's how I find the independent columns. I start with column 1. I put it into the C matrix. C is the matrix of independent columns in C. And if column 2 is not a multiple of column 1, that column 2 goes into C. If column 3 is not a combination of columns 1 and 2, 3 goes into C, otherwise not. So you just go from left to right, and you end up with the matrix C, the column matrix, the independent column matrix, right? So here, now just let me say again. We're given the matrix A. It has some independent columns, but then it may have some dependent columns. So we construct C with, C is our column matrix with only the independent ones. So every column in A is some combination of the columns in C. C has all the good ones, all the independent ones. And the matrix R tells us what that combination is, because you know how to, well, I'm multiplying matrices now, C times R. So what that does is it takes combinations of the columns of C, and the columns of R tell me which combinations to choose. Okay, C times R. Matrix multiplication is more interesting than you think. Okay, let's go to the next slide. Yeah. Okay. So, there's a case of A equals CR. So this is what we need to know. You see the matrix with columns 1, 1, 2, 3, and 4, 5. Those 3 columns are dependent. The first 2 columns go into C, that's 1, 1, and 2, 3, 1, 1, and 2, 3. Those are independent. And now R tells me, the last matrix is R. R tells me how to get every A column from the C columns. So you see the first column of R, the first column of R has a 1 and 0, so that I take 1 of the first column to get the 1, 1 vector. The second column of R has a 0 and 1, so I take 1 of the second column, 2, 3, to get the 2, 3 matrix of vector in A. And then finally, the interesting one, the combination, I take 2 of the 1, 1 column plus 1 of the 2, 3 column. That gives me 4, 5, the dependent column of A. Do you see how A equals CR? It has to be, when we create it, it must work, because we put the independent ones in C, and then R tells us how to get all the columns from the independent ones. And because matrix multiplication, the number of columns in C equals the number of rows in R, 2 columns, 2 rows, 2 columns in C, 2 rows in R, then those are, C tells me all about the column space. R, the rows of R tell me about the row space. And I had 2 columns in C and I had 2 rows in R. So those spaces have the same rank, same dimension. So this is my lecture, full speed for my linear algebra class, and it would also be somewhere on the 1806 website. And actually, I'm teaching the class, my second, we just started the spring semester. Well, it's one foot of snow is outside here, so it's not spring, but we call it the spring semester. So I'm my second class in this semester, so I don't know the students yet, about 60 students. I'll be explaining A equals CR in that class. Yeah. Okay, so that's a wonderful thing. Now, then comes the big picture of linear algebra. In the next slide, maybe, might be, hope so. No, this is another review. We don't need a review. We understood the thing. Okay, so let's go on to the next slide. Yes, here's the big picture. Here's the big picture. So for any matrix. So let me take time on this one, because this is probably, this is on the cover even of the Introduction to Linear Algebra book, the 4 subspaces. And so we have a matrix. From the matrix, we find the column space. You see the column space over on the right there. And we have the row space. So the column space, again, is all combinations of the columns. And when we take all combinations, we get the whole space. And on the left, the row space is all combinations of the rows. And again, those spaces are the same dimension. That's what we just understood. That first great fact in linear algebra is, and if you had a matrix which was 1,000 by 2,000, well, to know that the number of independent rows equals the number of independent columns, that's not simple, but it's true. It's always true. So those 2 spaces, they account for the independent columns and rows. But now the other 2 spaces are the solutions to AX equals 0 for the null space, null meaning 0. So they're the solutions to, the vectors in that give combinations of the columns that produce the 0 vector, the 0 column. So that's the null space. You can see that it's sort of the opposite of the row space. From AX equals 0, the equation for a vector in the null space. So that vector X is in the null space. If you multiply A by X, if you multiply a matrix by a vector, then the usual way to do it is dot products of the rows with the vector x, right? When you multiply ax, you take dot products, inner products of the rows of A with the vector x. And here, the vector x is perpendicular to the rows, 90-degree angle, so we get 0. Yeah. So it's natural then that the null space, the x's, are perpendicular to the rows in the row space. Do you see the beauty of this picture? We have the 4, if we know those 4 spaces, then we know about the matrix, those 4 subspaces. We would need to know the rank, and we would need to know which vectors are independent to know which vectors are in which spaces. Yeah, that's a good picture to understand. And then then a big step is to choose basis vectors in those spaces. So do you remember the meaning of a basis? So let's look at the column space. So what is a basis for the column space? It's the independent columns. It's the R independent columns is a basis for the column space. And R independent rows are a basis for the row space. And the matrix A is behind everything. The matrix A is behind everything. This is the big picture of a matrix. Okay. By the way, here's my first homework problem. Suppose the matrix has, suppose there's only one independent column. Every column is a multiple of column 1. Okay, that's a very special, simple matrix, a matrix of rank 1. So every column is, so what's a matrix of rank 1? The columns might be 1, 3, and 2, 6, and 4, 12, and -5, -15, all in the same direction. Then the rows are in the same direction. That's a challenge. To prove the great fact of dimension equal dimension for column space and row space, when that dimension is just 1. So let me ask you the question. This is the homework question for fun, of course. For every linear algebra is fun. So that's the question is, prove if all the columns are multiples of column 1, then all the rows are multiples of 1 row. So an example would be to have the columns 1, 2, and 3, 6. So the columns are all in both columns in the direction of 1, 2, and 3, 6. And then the rows are in the same direction, 1, 3, and 2, 6. So for 2 by 2, my challenge is easy, but now prove it for any size matrix. Yeah, okay, good. So we're moving along. My lecture might not take all 50 minutes, but that's okay, I'm sure. So shall we go to the next slide? Not forgetting that big picture. Oh, and then that rank, the M and N and R, those are the key numbers. How many solutions to AX equals 0? In other words, how big is the null space? Well, the row space had dimension R, so the null space has dimension N minus R. That tells us how many independent X's, how many independent solutions to AX equals 0. And of course, if our matrix has many columns, so n is a large number, many columns, then there will be solutions, because the rank can't be greater than m. So if n is larger, then we have some solutions. Some n minus r would be a positive number, and we would have some solutions in the null space. Yeah. Okay. Now, so this is basic linear algebra about a matrix A. But now I want to jump to the end of the linear algebra course, which is about singular vectors and singular values. Everybody has, if you've studied linear algebra, you know about eigenvectors and eigenvalues. So eigenvectors and eigenvalues come from a square matrix. But in data science, matrices are not square. We have we have all the samples and all the observations. Two different rows and columns are different. And the number of rows is not the same as the number of columns in an experiment. So eigenvalues are not possible. If the matrix is rectangular, eigenvalues are for square matrices. So what do we do if the matrix is rectangular? It hasn't got eigenvalues and eigenvectors. And if you know the important idea of singular values and singular vectors, so those take the place of eigenvalues and eigenvectors. Yeah. And the singular vectors, they also fit the big picture, our four subspaces. The singular vectors are a good property of singular vectors is they're perpendicular to each other. We have a perpendicular basis, an orthogonal basis. The rows may not be orthogonal, but combinations will be the singular vectors. So this is the wonderful thing, that there's the four spaces have basis vectors that are perpendicular to each other. And the matrix A, acting on a vector in the row space, a singular vector in the row space, gives a singular vector in the column space. Yeah, let me try to give an example. So this is the singular value decomposition, and it tells you it tells you so much about the matrix. So let's look at the next slide. Maybe we see. Yes, good. This is a good slide to look at. Okay. So look at the equations at the top. You see the matrix A. So the matrix A is not symmetric. It's small, so I made it 2 by 2 to be so that I could show you an example. So it's the 3, 0, 4, 5 matrix. It's not symmetric. Well, so it would have eigenvalues 3 and 5 because it happens to be square, but I'm looking for singular vectors and singular values. That's different. Okay, so just to show, so if I multiply that 3, 0, 4, 5 by 1, 1, I get 3, 9. Okay. And then on the after that equation, I had another equation. I multiply 3, 0, 4, 5 times minus 1, 1, and I get, you see that multiplication, it gives minus 3, 1. Now, what is special about those two possibilities, A, V1? So what's special about V1? V1 was the 1, 1 vector, and V2 is the -1, 1 vector. And what's interesting about the vectors 1, 1 and -1, 1? They're perpendicular. They're orthogonal. So those two vectors, those were input vectors. They go in. And so I have orthogonal input vectors. Now, what vectors came out? Well, 3, 9 came out from the first one, and -3, 1 came out from the second one. And what's interesting about those vectors, 3, 9 and -3, 1, they're perpendicular. So I have this wonderful situation that the inputs V1 and V2 are orthogonal, and the outputs U1 and U2 are orthogonal. And that's what you want for the SVD, for singular values and singular vectors. So those are the singular vectors. Those are this is a big application is PCA, principal component analysis. And these are the principal components. These are the vectors you want. These are the vectors that take the place of eigenvectors. But now we have two families. We have V's and we have U's, because the matrix has M and N. It has an input space and an output space. So the great theorem is that every matrix has, for every matrix, there you can find U's and V's. The V's are orthogonal to each other. The U's are orthogonal to each other. And the AV is equal to the constant sigma, let's say sigma, the singular value, times U. AV equals sigma U. That's the equation we're looking for. AV equals sigma U. That's the equation that takes the place of AX equal lambda X. So can I just say that again, and then we're nearly at the end. So AX equal lambda X, that's the eigenvalue equation. Vector X goes in, a vector lambda X comes out. That's for a square matrix. Here we have vectors V going in, multiplied by A, vectors U come out, and the V's are perpendicular and the outputs are perpendicular. So maybe the next slide has a picture of this thing. Oh, no, this says more algebra. Yeah, this is a big part is played by A transpose A and AA transpose. Yeah. So there's more to say about the singular value decomposition, but let's go to the next slide with its picture. Yeah. So this is saying that every matrix, for every matrix, rectangular, there's a matrix V, a square matrix with orthogonal columns. That's called it's called an orthogonal matrix. And there's so every linear transformation, every matrix is a rotation followed by a stretch, followed by a rotation. That's, and of course, this audience may know all about the SVD, but that's the great result from a linear algebra course for data science, because these vectors are the principal components that give you the information you want, that the information hiding in the matrix is revealed by U and sigma and V. Yeah, so this is a great part of linear algebra. Good. Okay, let's just look at the last slides and then I'll, yeah. Oh, and the very special thing about these vectors is that if you just want an approximation, you just keep the biggest singular values. If you want the best approximation to the matrix A, you just keep a few of the singular values and the singular vectors and not the rest. Yeah, so that's a great fact. Okay. So now let's just look at the last slide. It's probably sort of, oh, yeah. This is a picture of the SVD for a 2x2 matrix. It's if you have data that's close to a line, that line is in the direction of the first singular vector of the first special component, right? So so here with linear algebra, we started with column space and row space. And then we found the perfect basis for it coming from the SVD, the singular columns, the singular vectors in the row space, singular vectors in the column space are the perfect vectors to be the basis for those spaces. Okay, that's a review of linear algebra. That's what maybe a first course in linear algebra would start with column spaces and end with SVD maybe. So thank you very much for inviting me to be here today. Thanks.
Thank you very much for your informative and exceptionally good speech, Professor. Also, I would like to say thank you, Professor Andrei, for his technical support. Now, is there any comment or remark regarding the presentation of the professor? Please use question and answer button below, if any. It seems there is no question.
That's
or
fine.
comment.
Yeah. So I hope you enjoy the whole conference, and I hope you enjoy linear algebra. Thanks.
Thank you a lot, Professor. Thank you.
My pleasure. Right.
And
have a good conference. Right. Bye.
Thank you, Professor.
Sure. Bye to everyone.
Now, Professor Talha will moderate the next session. And the microphone is yours, Professor Talha.
Okay.
So hello, dear participants. We have a delay in our schedule. We apologize for this situation again. Now we can continue with the regular schedule with a delay. I am Talha Arıkan, and I will moderate the next 6 talks. The first speaker is Professor Das. Professor Das from India. He is gonna talk about exploration of zero open sets in a fuzzy B topological space via operation approach. Professor Das, please share your screen.
Yes. Am I audible?
Yes, we can see you.
Okay. Wait. So is the screen visible?
Yes, please make it screen. Yes, it's fine. You can start. Thank you for your attendance.
Start? Yeah. So thank you very much, and a very congratulations to the authority and the Turkish Channel of Mathematics for organizing this international webinar. And it's a great privilege that you've given me this chance to present my talk, which is on the exploration of pre-open sets in a fuzzy bitopological space by operation space. Myself, Dr. Bijit Das, and I am from the Institute NIT Warangal from India.
Okay, so this is the outline of my today's presentation. At first, I will be discussing the introduction part of our research work, starting with the method of operation approach. In our study, we apply operation approach to fuzzy bitopological spaces. So I will be discussing the preliminary notions, some of the preliminary notions of fuzzy bitopological spaces, and then I will be discussing the main contributory research works, which are the I-star gamma operation and I-star gamma open set, and then from that I will be discussing I-star fuzzy pre-open set, and I will be discussing the characterization, some few characterization of those sets. And we have produced some results via minimality and locally finiteness, but in this presentation I will be discussing only the results on minimality. In our whole research paper, the results on locally finiteness are also there. And finally, I will be making the concluding remarks, and we'll be discussing some of the future scope of our study. So starting with the operation approach, the concept of operation in a topological space was first introduced by Kashihara back in 1979. And then throughout the next decade, several researchers has devoted their study in extending or developing results on operation approaches. Like Jankovic in 1983 introduced alpha closed graphs via operation approach, and then for via operation approach, open sets are introduced, and Riemann and Ahmad had introduced the concept of interior closure of those sets via operation approach in a topological spaces. Theoretical applications are shown by researchers like Wagata, etc. Throughout this days. Okay, then in the first decade of 21st century, various researchers or mathematicians extended these notions of operation approach in exploring different types of open sets. And by different types of open sets, I mean generalized version, that means stronger version or weaker version of open sets. Like pre-open sets was studied by Van et al. In 2008. Then semi-open set was studied through operation approach by Krishnan et al. In 2007. And beta open set, B open set, gamma open set, there are various types of open sets were studied by several mathematicians throughout those decades. Okay, so first of all, I will be discussing what is operation approach to a topological space. So suppose we are considering a non-empty set X and taking a topology A tau defined on that non-empty set X, and we call the members of the tau are open sets. So these are the usual notations, but through operation approach, another open sets are discussed in a different manner. So first of all, we have to define operation in a topological space. So the domain of a function, which will be called an operation, the domain of that function is the topology itself, and the range or codomain of that function is the power set of X. So a mapping, which we call gamma, from topology tau to power set of X is an operation if for any open set V, the image under that function F becomes a superset of that open set. If this condition is satisfied, then that mapping gamma is called an operation on that topology. And via this operation, open sets are defined as follows. That we consider a subset A of a topological space X tau, and this set A will be called an open set if for each element of that set, if there exists some tau open set U, such that the image of that open set is a subset of that set A. If this condition is satisfied, then the set A will be called an open set. And replacing that open set U by pre-open sets, semi-open sets, researchers have studied various types of sets like pre-open set, semi-open set in topological structure or in fuzzy version also. So we have gone through all these research articles available in the literature to study the whole things, and we found a similarity in whole studies. And we have found that those collection of pre-open sets, or maybe the collection of semi-open sets, beta open sets, B open sets, whatever you take, all these collections forms a supratopology therein. Now, what do we mean supratopology? Supratopology means the first condition is that that empty set phi is becoming a pre-open set via operation approach. If we consider pre-open set in this purpose, the whole set X is also becomes pre-open set via operation approach, and arbitrary union of pre-open sets via operation approach becomes a pre-open sets. So this collection of pre-open sets via operation approach becomes a supratopology. Also for the semi-open set, beta open set, B open sets, in all the cases, those collections forms a supratopology. Now, what I am saying this observation, because in our study, in our research work, we found a different result. That is why I am emphasizing on this result. Okay, now moving forward to the next slide, which is preliminary notions of fuzzy bitopological space. Now, what is a fuzzy bitopological space? Now, bi means two. That means we consider a non-empty set X and consider two topologies non-equal to, they are not equal to each other, tau 1 or tau 2, or we can say tau y or tau z. And together those topologies with non-empty set X, this structure we call a bitopological, fuzzy bitopological space. So in that fuzzy bitopological space, what are the open sets? So a fuzzy set lambda will be called a ij star fuzzy open set if it can be expressed as the union of two open sets, lambda 1 and lambda 2. Lambda 1 is the open set with respect to the topology tau y, and lambda 2 is the open set with respect to the topology tau j. So if a fuzzy set lambda can be expressed as union of two, one is tau y open set, another is tau j open set, then that set will be called ij star fuzzy open set. Now, this is the usual notation for ij star fuzzy open set. Via operation approach, we will be introducing the ij star fuzzy open set in a different manner, and then we will be discussing the interrelationship between those two notions. Okay, now for this ij star fuzzy open set, the complement of those fuzzy open set will be called ij star fuzzy closed set. And depending upon those open set and closed set, ij star closure and ij star interior operator is defined as follows. And also ij star fuzzy pre-open set is also defined by the usual approach, like a set fuzzy set lambda will be called a fuzzy pre-open set if it is less or equal to the closure and interior of that set. So these are the preliminary notations of fuzzy bitopological spaces which we have done and already published in an SCA journal called Computational and Applied Mathematics. So these are published journals, okay, published research work. Okay, so based on these preliminary notions, we will be introducing ij star gamma open set in a fuzzy bitopological space via operation approach. Now, how we define operation and how we define an operation in a fuzzy bitopological space? So the method is exactly same as Kashara defined in a topological space, but domain will be changed obviously, and codomain is also changing. Now, what is the domain in this case? In case of topology, the domain was the collection of all open sets. That means it is tau. It was tau itself. Now, where X, tau y, tau j means there are two topologies, and in our published research work, open sets are taking from tau 1, tau y in union tau j. So these ij star open set are considered here, and we are calling the collection of all ij star fuzzy open set as ij star f of x. So in this case, we are taking the domain of this function is the open sets, is the collection of all ij star fuzzy open sets, and the codomain of this function is ix, which are the mapping from x to the unit interval 0, 1. So okay, so these are the domain and codomain of that function. Now, when this function will be called an operation on that fuzzy bitopological space. So that here we have we did not change anything on the original structure. That means a function f will be called an ij star gamma operation. We have given this notation ij star gamma. So we are calling this function a ij star gamma operation if the functional value of any open set is a superset of that set. So we have taken the original structure as like this, okay, and then we'll be defining I just are gamma open sets in a fuzzy bitopological space in the following way. Like we are taking a fuzzy set delta, and it will be called a I-star gamma fuzzy open set if we take any fuzzy point from that set, and then we can find another I-star fuzzy open set mu containing that point, and it satisfies the condition that the image set of that fuzzy open set mu is less equal to the original set delta. And if this condition is satisfied, then delta will be called an I-star gamma open set. Now we know I-star gamma open set, so the complement of that I-star gamma open set will be called I-star closed set, I-star gamma fuzzy closed set. And based on this, in the usual manner, interior operator, closure operator is defined. Then how we define I-star gamma fuzzy pre-open set? So this is exactly same as the previous definition of I-star gamma open set. Here just we'll be replacing the I-star open set mu by an I-star fuzzy pre-open set. You can see in the definition, a fuzzy set delta will be called a I-star gamma fuzzy pre-open set if for all fuzzy point xp from that set delta, there exists I-star fuzzy pre-open set containing that point, and such that the condition is same, f of mu less equal to delta. Now here comes the interesting properties of I-star gamma fuzzy pre-open sets. We have found, like in the case of fuzzy topological spaces, that the empty set 0x and the whole set 1x are both I-star gamma fuzzy open set. This is same. But in case of union of two, that means we are considering finite only, union of two I-star gamma fuzzy pre-open set are not is not a I-star gamma fuzzy pre-open set. In general, this is not true. The example supporting this claim is provided in our original research paper, which will be submitting 2-3 days later. So we have found that finite union of I-star gamma fuzzy pre-open set is not a I-star gamma fuzzy pre-open set. And also in the case of intersection of two I-star gamma fuzzy pre-open set, it is not I-star fuzzy pre-open set. So that means it is neither closed under finite union or and it is not closed under finite intersection also. So we can say that the collection of all I-star fuzzy pre-open set not forming supra-topological space in the same environment. So this is the different result we have found, and rather it forms a generalized fuzzy topological space. As we know that if 0x and 1x is there in the collection, then it is called it forms a generalized fuzzy topological space. So we can call that I-star gamma fuzzy pre-open set does not form supra-topological space, but it forms generalized fuzzy topological space. Okay, now
2 minutes left, Professor Das.
Yeah,
2 minutes left.
Okay, I will be finishing within 2 minutes. Okay, and also we have found another interesting result that every I-star gamma fuzzy pre-open set is a I-star fuzzy pre-open set, but the converse case is not true, and supporting example is provided here. We have also defined another type of operation which is called a regular I-star gamma operation. I am not going to details. If someone needs, I will be providing the PDF of this presentation. Now here we see that if an operation is regular, then finite intersection of pre-open set becomes a pre-open set. That was not true in the earlier case. So in case of regular operation, we can say that the collection satisfies three conditions: 0x is there, 1x is there, and also finite intersection is also closed. So we can say that the collection of all fuzzy pre-open sets forms a fuzzy infi topology. Three condition is satisfied means it forms fuzzy infi topology. Also we have provided some results on minimal fuzzy pre-open set, and results were established via locally finiteness also. So moving towards the concluding remarks, here I will be taking only 1 minute. Here we have extended our own work, which have published from 2 Scopus journal and 1 SA journals. So here we have extended those works by considering operation approach in a different manner and tried to find some comparative result. Characterizations were made for pre-open sets by operation approach, and the results obtained were we have seen that these are slightly different, and new results were also established. And also theoretical applications were described by using minimality and locally finiteness also. And if I want to say the future scope of the study, I can say that via continuity and irresoluteness also this study can be extended. And also in a fuzzy topological space, operation approach can be extended by considering, here we have considered free open set, so we can extend it also by considering semi open set, B open set, and like other stronger on weaker forms of open sets also. These are the references we have gone through to prepare this research. And thank you very much.
Thank you, Professor Das. Is there any question or comment for Professor Das? So I think you have no question.
Thank you, my PC, Dr. PC.
So thank you again for your contribution.
Yeah, thank you. Good night from here.
For the next talk, I would like to invite Professor Delium from Algeria. Are you there, Professor Delium?
Hello.
Hello.
Hello. Okay.
Please open your video. Professor Delium is gonna talk about new methods of construction for rich solitons.
Yes.
Please share your screen.
So can you see the screen?
No, there is a problem. Please try it again.
Okay.
So it's fine. Yeah? Please make it full screen. So it's okay. You are welcome to present your study. You have 15 minutes.
Okay, so hello everyone. My name is Delum Adel. I am a PhD student from Algeria, and today I'll be talking about a little work I've done with my supervisor concerning new methods for building up Ricci solitons in Riemannian manifolds. So the plan for my presentation will be divided into 4 parts. We start off with an introduction, then we'll talk about a deformation of matrix, and we introduce our new methods, and then we will conclude our presentation. So the notion of Ricci soliton is basically a generalization of Einstein manifolds. It was appeared by Hamilton, and basically a Ricci soliton is a fixed point solution for the Ricci flow. Ricci soliton have been studied extensively nowadays, and they've been applied basically a lot in contact geometry, because contact geometry is, like everyone know, the manifolds are classified into 12 classes, where each class is by certain relation, which really helps in computations. So a Ricci soliton is basically a Riemannian manifold associated with a vector field at the constant lambda, which is by the following equation. So we'll talk about, so what have we